Dr. N.K. Mehra, Vice President, Indian National Science Academy. Dr. G.K. Rath, ex-Chief, IRCH, All India Institute of Medical Sciences. Honorable Founder President, Dr. Ashok K. Chauhan, sir. Honorable Chancellor of Amity University, Uttar Pradesh, Dr. Atul Chauhan, sir. Respected Vice Chancellor, Dr. Balvinder Shukla, ma'am.
We also welcome our Honorable Vice Chancellor P.V. Sharma ji. Give a big clap for P.V. Sharma, our Honorable Vice Chancellor from Haryana.
The Vice Chancellors from all Amity campuses, esteemed invited speakers, respected dignitaries, campus heads, deans, directors, head of the institutions, faculty members, students, conference participants, the participants who have joined us online. On behalf of Amity University, Uttar Pradesh and Global Cancer Consortium, I, Dr. Sonia Kapoor, extend a very warm welcome to you all to the 5th International Global Cancer Consortium Conference on the theme Advances in Cancer and Cancer Immunotherapy, being organized jointly by Amity University and the South Asia chapter of GCC. The conference is being organized to provide a platform where leading national and international scientists will deliberate on the frontier areas of immuno-oncology and will provide a glimpse of what future beholds for healthcare. I humbly request all the dignitaries to be kindly seated on the dais. Please give a big round of applause and welcome all the dignitaries on the dais, please. Light is a symbol of brightness and prosperity. To make this conference a blessed one, we commence the event by lighting the lamp, accompanied by an invocation dedicated to this light in our life. May I request our esteemed guests on the dais to please participate in the ceremonial lighting of the lamp before starting today's proceedings. I request everyone to please join in light lamp.
मां सरस्वती शारदे, मां सरस्वती शारदे, पूर्ण इस अज्ञान उदधि से, पूर्ण इस अज्ञान उदधि से, वीणा पाणी तार दे, तार दे, तार दे, मां सरस्वती शारदे, मां सरस्वती शारदे। सूर्य ब्रह्म शिव विष्णु गजानन, जिन चरणों को सेवते, सूर्य ब्रह्म शिव विष्णु गजानन, जिन चरणों को सेवते, हम शिशु है अज्ञानी माता, तेरे चरणों का प्यार दे, वीणा पाणी तार दे, शारदे मां सरस्वती शारदे.
Thank you all, and thank you for this beautiful rendition. As a tradition at Amity University, we welcome our esteemed guests with Tulsi sapling symbolizing purity, positivity, and happiness. May I request Honorable Vice Chancellor Ma'am to please present the Tulsi sapling to Dr. G.P. Talwar. Please give a big round of applause. Dr. B.C. Das, sir, to present the Tulsi sapling to Dr. N.K. Mehra, sir. Dr. B.C. Das, sir, to present the Tulsi sapling to Dr. N.K. Mehra, sir. Dr. Chandradeep Tandon, sir, to present the Tulsi sapling to Dr. G.K. Rath. Dr. W. Selvamurthy, sir, to please present the Tulsi sapling to Dr. Vivek M. Rangnekar, sir. Please give a big round of applause. Dr. Hidesh Prakash to present the Tulsi sapling to Honorable Vice Chancellor Dr. Balwinder Shukla, ma'am. Dr. Subhrajit Bishwas to please present the Tulsi sapling to Dr. W. Selvamurthy, sir. Please give a big round of applause. Dr. Monica Bhardwaj to please present the Tulsi sapling to Dr. Chandradeep Tandon, sir. Dr. Tanvi Navid, sir, present the Tulsi sapling to Professor Bhudev Siddhas, sir. Dr. Nav Kiran Kaur to present the Tulsi sapling to Dr. Subhajit Biswas. Dr. Manoj Garg to present the Tulsi sapling to Dr. Hidesh Prakash.
Let us welcome our Honorable Founder President, Dr. Ashok Chauhan, who have joined us from 9:30 onwards. Let's give a big clap to Founder President. Thank you, Founder, that you have been the architect of this whole program. Welcome to this program for the inaugural session. And also Dr. P.B. Sharma, our one of the veteran Vice Chancellor and who is contributing in the Amity University, Haryana in a significant way. Let's give a big clap to Dr. P.B. Sharma. Thank you.
It is my immense privilege to humbly invite Professor B.C. Das, the chairperson of the conference. Professor B.C. Das is the chairman, Amity Institute of Molecular Medicine and Stem Cell Research, Dean of Health and Allied Sciences, AUP, chairman, University Research Council, and vice president of Amity Science Technology and Innovation Foundation to deliver the welcome address. So, please.
Very good morning to one and all. At the outset, hearty welcome to the 5th Global Cancer Consortium International Conference on Advances in Cancer and Cancer Immunotherapy at Amity University, Noida. On behalf of our most respected and great visionary Founder President Dr. Ashok K. Chauhan, our dynamic Chancellor Dr. Atul Chauhan, and Honorable Vice Chancellor Professor Dr. Balwinder Shukla, I welcome, first of all, our today's honorable and esteemed chief guest of the inaugural function, Dr. Rajiv Bahel ji, who is the hardcore clinician and medical scientist, Secretary, DHR, Department of Health Research, Government of India, and Director General of Indian Council of Medical Research, New Delhi, who will be joining soon online. Next, I welcome our Honorable Vice Chancellor, Professor Balwinder Shukla, who is the Vice Chancellor of this university. The next, I welcome our three renowned medical biomedical scientists as guests of honors. Professor Dr. Balwin G.P. Talwar, who is the biomedical scientist. He is the founder of the Talwar Foundation, Nepsarai. He is a great scientist. He is 98 years, 4 months old. So, welcome with greatest applause. Still, he is active in science. That's a great thing to know it. He is still practicing the science every day. He is a great biochemist and immunologist. And then I welcome Professor N. Mehra, who is the immunologist, the famous immunologist of this country and world over. And he is the Vice President of INSA, Indian National Science Academy, India, New Delhi. Then I welcome Professor Dr. G.K. Rath, who is the radiation oncologist and cancer specialist. He was the ex-head of IRCH, the research at AIMS, but he is now associated with the Department of Atomic Energy for the cancer research, all cancer research aspects. And then I welcome Dr. Vivek Ragnekar. He is the Secretary of the country president of GCC, Global Cancer Consortium. So, and now I have three my colleagues in the college, Professor Chandriti Tandon, who is the additional Pro-Vice Chancellor and Dean Faculty of Biosciences and Biotechnology, IIP. Then we have the Dr. Supratit Biswas, Director of Amity Institute of Molecular Medicine and Stem Cell Research and convener GCC 2025. And the most important person is the Dr. Hitesh Prakash. He is the organizing secretary of this meeting. He is an immunologist and also cancer biologist, and he is the head of the SCTR, the Amity Center for Translation Research. So this conference will encompass the preclinical and clinical models of cancer research and identify most effective diagnosis and treatment modalities of the various refractory cancers and other cancers which are highly prevalent or in rising trends due to changing lifestyles and environment. The conference has brought several national and international stalwarts in the tumor immunology and cancer biology to address the most challenging problem of the world today facing today. I am sure the intensive brainstorming and deliberation of the various important topics during this conference, would pave the way for forging bonds and of the corporations and undertaking joint research projects and publications and achieving the long-term goals, establishing significant collaborations. And I greatly appreciate, and then the organizing committee for organizing such a meeting, and I thank all the delegates to invited speakers. I welcome all the speakers from India and abroad who have come all the way from different places, and I welcome all the students and particularly the young scientists who have come from different parts of the country. So there are as many as almost 80 speakers, about 20 from abroad and 60 from India, and more than 200 participants. The conference participation is a galaxy of world-renowned speakers, and this 5th conference would be of the immense interest and for learning the value of all young researchers, scientists, and research scholars and other participants. Thank you all very much, and I welcome once again with these few words, I welcome everybody to this cancer conference. Thank you very much.
Thank you, sir. Thank you for extending a warm welcome to one and all. I now request Dr. Subhajit Biswas, the convener of the conference, to deliver his opening remark.
Good morning, everybody. It's a big pleasure to have you here, and it's 5th Global Cancer Consortium. I am really very happy because all of my teachers, Professor Talwar sir, Mehra sir, Roth sir, Bisida sir, Shivamukti sir, Balmita BC ma'am, all our mentor guides, Shantoda, all of you are here. So I am not taking too much time because we have to finish our session very timely manner. So thank you very much. So we'll talk in the several times in the 3D way and enjoy the conference. That's all. Thank you. Thank you.
Thank you for your address, sir. I now invite Dr. Videsh Prakash, Deputy Director, Amity Center for Translational Research and the Organizing Secretary of this conference, to give a brief introduction of the conference.
Morning, one and all, and Professor Das have already made my work a lot easier. And in fact, I must say that he has done my job, which I'm supposed to do. But to maintain the curriculum, I first and foremost welcome all of you here in India, all our international speakers. So this conference is all about cancer immunotherapy, which is a major challenge, which is a very important area of the research and need a lot of deliverables, a lot of deliberations. So particularly the theme of this conference is to discuss the new advancement and discuss the modalities for the treatment of the cancer patient, which are seeking our help. This is very important from the point of view of clinics. If cancer patients come to the clinic and go to the scientists with the hope that I will get some more life. So here, this is a very, very important wish of the cancer patient, and we have a lot of responsibility to cater this, small request of a cancer patient, which is immense. So I'm not taking much of time. So with this particular significance of this conference, I welcome all of you and have good time here, and we'll all take care of you. Goodbye. Thank you.
Thank you, Dr. Prakash, for a brief glimpse of what we are going to expect. This conference is being jointly organized by Amity University and the South Asia chapter of Global Cancer Consortium. We are privileged to have Dr. Vivek Rangnekar, the founding chair of GCC, with us today. Dr. Rangnekar is a professor at Alfred Cohen Endowed Chair at the College of Medicine, University of Caltech. He also serves as Associate Director at the Markey Cancer Center, USA. I now invite Dr. Vivek Rangnekar to brief the audience about Global Cancer Consortium.
Good morning, dignitaries on the dais, dignitaries in the audience, faculty, physicians, students, scholars, ladies and gentlemen. It is an honor to be here with you all. Many of you have journeyed from various states of India, and some have traveled long distances around the globe. On behalf of the Global Cancer Consortium, I extend a warm welcome to each one of you at this conference. This 5th International Conference of the Global Cancer Consortium is organized jointly with Amity University. Since the formation of the consortium in 2020, we have introduced a number of new academic activities that go well beyond the basics of cancer biology and therapy. Just to name a few, these include specialty areas of cancer immunology, cancer oncology, and cancer engineering that integrate cardiology, immunology, and engineering concepts in cancer. To promote regional collaborations, we started new GCC chapters in North America, Europe, East Asia, and South Asia. The GCC South Asia chapter is headquartered at Tata Memorial Center in Mumbai. Please visit the GCC website for our much talked about signature events, go create workshops, and inspire seminars that add a fresh new outlook to workshops and seminars and advance them for interinstitutional collaborations and joint publications. Now, this conference provides an opportunity to re-examine tumor immunology and immunotherapy. It is becoming increasingly clear that the patient's immune response plays a pivotal role in regulating tumor growth, and immunotherapies that are designed to enhance this response are showing promise in the clinics. Over the course of this conference, we will explore the intricacies and immune response that can be leveraged to make immunotherapy even more effective while mitigating its adverse effects. We hope this gathering will inspire new research initiatives that deepen our understanding of this critical area. We genuinely hope that you will enjoy the academic atmosphere and develop new professional connections throughout this conference. In particular, I want to thank the leadership of Amity University for their generosity in hosting this conference, and I want to acknowledge the tireless efforts of Dr. Videsh Prakash to make this conference possible here in Noida today. Thank you. Enjoy this conference.
Thank you so much, Dr. Rangnekar, for your address. I now request Dr. Chandri Tandon, Additional Pro Vice Chancellor, AUP, and Dean Faculty of Biosciences and Biotechnology to address the gathering.
Thank you and very good morning to all. On behalf of our most revered founder president, sir, our dynamic Chancellor, Dr. Atul Chauhan, our respected Vice Chancellor, Dr. Balwinder Shukla, I welcome all worthy scientists on the dais, off the dais, my esteemed colleagues, dear students. I know this is going to be a scintillating session these 3 days because the topic is so important. It's not just about the cancer biology. It is about the new innovative treatments in this field, which are not only going to be curing our cancer patients because cancer is on the increase, we know that, but I am very sure the discussion, the deliberations which are going to be taking place here in 3 days will definitely pave a way for the better treatments, and those treatments will be able to reach to the masses. With this, I welcome everyone once again. Thank you so much.
Thank you, sir. We are very honored to have joined by a very special guest today. Amongst us is one of the most eminent scientists in the field of immunology and vaccinology, Professor G.P. Talwar, as guest of honor. Professor Talwar is the founder director of National Institute of Immunology in New Delhi and director research at the Talwar Research Foundation, New Delhi. He held various reputed positions such as the professor and head of biochemistry AIIMS Scholar in Residence, National Institute of Health, Bethesda, and many more. For his immense contributions in the field of medicine, Professor Talwar has been conferred Padma Bhushan, the third highest civilian award by the President of India, and also Officier de la Légion d'Honneur by the President of France. With great pleasure, I invite Dr. Talwar to please address the audience.
First of all, let me thank you for holding a meeting on a topic which I think is important. Cancer is an enlarging burden in the whole world now and is taking its toll of mortalities. Issue is how can we control it? Of course, as you know, there are several drugs which are available, and physicians and surgeons and many cancers are also sort of surgically removable at least for a time, and then again they reappear all over the body. So therefore, it's something which is important to work on, and my current interest is to develop immunotherapeutic approaches for cancers, especially those cancers which are not treatable by drugs and which eventually lead to a guy going away. Sorry, how do I understand? But now you know there are strangely, I mean, it was almost a new finding for me to see that there are cancers. It is also ectopically human chorionic gonadotropin, which is normally a hormone which we use for diagnosis of pregnancy. You know all the time, please. Thank you. You see, HCP, and what is worse is that the cancers which express HCP, well, they do not last very long. There is no known drug which really handles it. I mean, there are a few of the publications I have mentioned in a slide. You cannot put all, but there are such a large number of publications which tell us that the tumors which produce HCP are not easily treatable. they are aggressive. And I have given here a few publications to show that, and it applies to cancers of all types, whether they are bladder cancer, whether they are exocrine tumors, pancreatic tumors, colorectal cancers, all types of cancers. That is, there are some which express रहने दो भैया क्यों फैलाती हो इसको हम आगे कर देंगे ऐसे इसको ये it so happens Nirupali but also to work on the licensing of the center to Messrs. Carter Barras. In 3 years, they sent him $750 million of royalty. And it is this royalty which enabled me to make a foundation. And that is where I continue to work these days. So, what I'm presenting to you today is the work done in that laboratory. तो भाई क्यों सारा एकदम निकाल दिए तो भैया ये क्या कर रहे हो What should do? Move on, please. भैया एक स्लाइड एट ए टाइम दीजिएगा That's all that I want. कहाँ दिया? So this monoclonal antibody, if you make it radioactive, iodinated, then if you inject into a nude mouse, as all of you perhaps know, you can give human tumors, and everything, and it doesn't react against. You can then conclude further. So let me then say that if you inject this antibody iodinated, at the left, the nude mouse has tumor, which is HCD expressing, and the antibody goes and only binds there. And then, on the right side, is the scan of a mouse with, so you see that goes all over. But an antibody is PIPP with the monoclonal antibody only goes where the tumor is. And here is, another tumor, the lung cancer. You see here that the antibody, if you inject, it kills the tumor. And the right up to 95% of the tumor can be killed by the antibody. You can also, see that in nude mouse, if you can also make an immunotoxin out of it. In other words, you can take off that is what we currently are doing. You take a single chain of PIPP and you link it up with a toxin, which in this case is alpha-sarcine, and it is non-immunogenic in humans. अगर आप कहते हैं तो माफ कीजिएगा.
We'll arrange this talk right after the inaugural program. Right. So you will continue.
मैं ज़्यादा वक्त नहीं लेता, मैं सिर्फ ये कह देता हूँ कि you see in the nude mouse, if you ये नहीं भाई दूसरा दिखा ये जो है in the nude mouse, if you inject the immunotoxin that we have made, you can reduce the tumor. On the left side is the tumor which is made in your mouse, and on the right side is the tumor where the injections have been given with the immunotoxin. And you see the tumor which has already grown, it can be killed by the immunotoxin. Therefore, we have proved that it is possible to reduce the tumor already formed. अच्छा मैं अभी बंद कर दूं.
Talwar sir's signs after the inaugural session. One second. So, we know indigenous scientist and
Talwar sir, we will give you complete a session. We'll have a detailed presentation. So since let's give a big clap to Professor G.P. Talwar, who is an icon in the field of immunology and who is FRS and also who is taken India to the global map. And we will listen to him at an appropriate time. Thank you so much, Talwar sir, for gracing the occasion. Thank you.
भाई अशोक चौहान बोल रहा हूँ. श्रीमती ने बोला. हेलो हेलो जी, क्या नाम है? अशोक चौहान जरा बोल रहा हूँ. हेलो वेट करना ना, जस्ट वेट. दुनिया जस्ट वेट, दुनिया जस्ट वेट. जीपी भाई से को अशोक चौहान बोल रहे हैं.
Most respected, honorable founder present, sir.
जीपी भाई बहुत बहुत
Very respected Chief Guest Dr. Rajiv Bahelji, Secretary DHR and Director General Indian Council for Medical Research, Government of India. A very esteemed guest of honors,
Dr. Shula, wait.
Dr. G.P. Talwarji, Dr. Henry Mehraji, Dr. J.K. Raji, and my esteemed colleagues on the dais, distinguished guests, participants. First of all, I, on behalf of Honorable Founder President, Honorable Chancellor, Additional Provincial Deans, Head of Institution, on my personal behalf, I extend very warm welcome to our Chief Guest, Dr. Rajiv Banerjee, and to our all the guests of honor. It is an honor to welcome you to the 5th International Global Cancer Consortium Conference, being organized by MIT Center for Translational Research in association with the Global Cancer Consortium. I would like to thank our Honorable Founder President, Dr. Ashok Chauhan, for his vision and leadership in promoting the excellence in education and research and beyond. The theme of the 5th GCC International Conference addresses a highly compelling and emerging field that culminated in the Nobel Prize in 2018, recognizing the groundbreaking work in harnessing the power of immune system to combat the cancer. This conference also offers a valuable platform to explore the integration of alternative and traditional medicines, which have demonstrated potential in reactivating the immune system alongside conventional treatments such as surgery, chemotherapy, radiotherapy to enhance the overall efficacy. This conference covers a wide range of topics, including tumor microenvironment, immunology, genetic mutation in tumor, and its burden, cancer immunotherapy, challenges in chemo and radiotherapies, and many more. And I've gone through the program schedule, and the galaxy of speakers have been invited from India and abroad, and who have really set the new benchmarks in the novel therapeutics, cancer vaccines, and other innovative treatments. Through this conference, we aim to achieve the 7 key objectives, including enhancing the scientific community's efforts to develop cost-effective indigenous immune therapies for the management and treatment of cancer. In line with the vision of Viksit Bharat 2047, where health and wellness are paramount, we are committed to advancing research and innovation in healthcare. Our focus on research is aligned with the government's initiative to promote health and wellness and make the Bharat to provide the universally accessible, high quality, affordable, and comprehensive healthcare. And our Honorable Founder President has established very specialized centers and institutions like MIT Institute of Virology, Immunology, MIT Institute of Molecular Medicine Studies and Cancer Research, and MIT Center for Translation Research for further the research in cancer and other related areas. I'm sure these deliberations which are going to happen during this conference is going to not only give what are the current researches, but also what is going to the future trends in this area. And our Honorable Founder President has given the Mission Connect, where so many scientists and researchers have come. And then the Mission Synergy, where the scientists and researchers can collaborate with each other. The research, the final mission, the mission outcome. So this collaboration, the research collaboration should bring the tangible results which help the society, which help the community to combat the deadly disease, cancer. I'm sure that after the deliberations, it will be setting the new synergies, new collaborations for the working jointly to achieve the Viksit Bharat goal, that the affordable healthcare solutions to all. And therefore, I once again extend all the esteemed scientists and the researchers the presentation which was being given by our esteemed guest of honor, Dr. G.P. Talwarji.
Madam, let us welcome DG ICMR who has appeared on the screen. Let's welcome Dr. Ajit Bahalji. And we are so delighted to see you on the screen. You are a great leader who is pushing the country to Dixit Bharat. Welcome, welcome. Thank you.
Ashok Chauhan, very proud to see you here. We welcome you. We are so proud of your coming. Ashok Chauhan speaking.
Thank you, Ji. Thank you, Dr. Chauhan.
Okay.
And I'm sure this conference is going to bring many collaborative research in time to come. So wish all the best to this wonderful conference.
Dr. Bahalji, the former president, greets you there on the screen with you. And he has come right from the beginning and he has been waiting to see you. Founder President, you wanted to say a few words about Talwar's lecture as well as...
Am I audible?
Yes, please. Yes.
भाई अशोक चौहान बोल रहा हूँ आपका लेक्चर सुन के मजा आ गया कमाल का अभी जो है ना कैंसर में बहुत काम करना है आपको कम से कम 120 साल तक मैं आपसे काम लूंगा 120 years you have to live okay I think Dr. Shukla somebody should tell him what I'm telling him then I'll talk to him later भाई great okay I think
अच्छा जी मैं ये कहूँगा
जी
कि पास एक ऐसी चीज है जो कि वो कैंसर्स जो कि ट्रीट होते किसी ड्रग से nor could be at a stage where can be surgically removed. उनके लिए हमारे पास एक इस वक्त पोटेंशियल इम्यूनोथेरेपी है और मैंने अभी सुना कि आपके यहाँ मेडिकल इंस्टीट्यूट भी है और अस्पताल का टाइप भी है तो अगर ये इंस्टीट्यूट which I have great respect for would like to have access to this therapy, I'll extend the possibility of its availability. We were normally going to restrict it to AIIMS and Tata Memorial Hospital, Bombay. But if you have also a good facility to take care of cancer patients, which are difficult to treat, I will make available my new discovery.
Thank you, Professor Talwarji. Let's give a big clap to Professor Talwar, a veteran scientist who is still driving research in immunotherapy in cancer. Thank you so much. Over to you, Founder President.
तलवार भाई तुसी हेल्प करो ਅਸੀਂ ਕੁਝ ਕਰਾਂਗੇ ਤੁਹਾਡੀ ਗਾਈਡੈਂਸ ਨਾਲ ਸਭ ਕੁਝ ਕਰਾਂਗੇ ਅਸੀਂ ਤਲਵਾਰ ਭਾਈ मैं मिलने आना हूं बैठ के गल करांगे थैंक यू
Sir, we are very privileged to have Dr. Rajiv Bahel, Secretary, DHR, Director General, ICMR, Government of India, as chief guest with us today, who has kindly consented to be present online. Dr. Rajiv Bahel is the Secretary of Department of Health Research, Government of India, and Director General, Indian Council of Medical Research. Dr. Bahel is a physician scientist with specialization in pediatrics from University of Delhi and PhD in public health from AIIMS. He has also received an honorary doctorate from University of Bergen, Norway in 2022 in recognition of his contributions to maternal and child health research. Dr. Bahel has been the head of the research on maternal, newborn, child and adolescent health at the World Health Organization, Geneva, for more than 10 years. Dr. Bahel has supported population-based multi-country research studies in over 20 countries in Asia and Africa and has contributed to strengthening the research capacity in over 50 institutions. A very few examples of public health impact of the research conducted under Dr. Bahel's leadership include policy of use of zinc in treatment of diarrhea early initiation of breastfeeding, outpatient treatment of antibiotic regimens when they cannot be admitted to a hospital, and immediate initiation of kangaroo mother care after birth in the mother newborn intensive care units. He has 30 years of experience leading the health research and translating research to public health policy, both in India at a global level. With this introduction, I feel honored and very privileged to invite Honorable Chief Guest, Dr. Rajesh Rajiv Behelji, to kindly address the August gathering. Please give a big round of applause.
Thank you and good morning. Respected Dr. Chauhan, respected Dr. Talwar, many other luminaries who are attending this conference, both physically and online. I'm very happy to be here and very glad that you are holding this international conference on advances in cancer and cancer immunotherapy under the ambit of Global Cancer Consortium. And there could not be a more opportune time for this type of conference. We all know how important cancer has become. There are several times too, I've worked with two health ministers over the last 2.5 years, and both have said that previously they used to have, and many ministers and MPs, they used to refer patients to AIMS or other places once in a month of a cancer patient. Now they refer 20 patients a day in every district. So we are seeing an increase in cancers, and there are many reasons for that, including our lifespan is getting higher, we are detecting cancer, but also that we are probably being exposed to a lot of environmental and other carcinogenic agents. However, we have to work on prevention of cancer in many ways. But here, our goal today is to see how can we best treat cancer. And immune therapy not only offers hope, but has actually led to about 25% of cancers globally becoming a very treatable disease. And understanding that cancer is largely an immune disease, where a carcinogenic cell is escaping in a way the body's immune mechanisms which can take care of these is such a key to thinking about cancer. And we are in particular very excited that India has its own two CAR T cell therapies for ALL and non-Hodgkin's lymphoma and other lymphoma, Hodgkin's lymphoma. So lymphomas and leukemias, we have two cancer therapies that have been two CAR T cell therapies that have actually been licensed for use in India by the Indian CDSCO. And one of them was a product of Tata Memorial and IIT working together, and the second one is an Indian company which has opened a subsidiary called Immunil, which has also developed a CAR T cell therapy. We also know that there are other possibilities like immune checkpoint inhibitors, and also recent news from Russia that they have developed some sort of vaccine where they take the material from the cancer and convert it into a secondary vaccine, which actually is working very well according to them. We don't know the details. It is certainly on the cards. So what is required at this moment in India is a lot of concentrated work around this where multiple groups need to come together for this cellular and gene therapy and other immune therapies, such that we are able to take this potential and now initiate initial treatment for some cases into hope for a lot of patients with cancer. And in that regard, I really would like to again congratulate Amity for holding this particular conference and to commit to working together. Many Indian entities should work together on making these therapies a reality. ICMR is fully committed to this. We have taken the issue of cellular and gene therapy to the principal scientific advisor and the PM Scientific and Technical and Innovation Council, Advisory Council, which has recommended that we should try and make a national mission for cellular and gene therapy. This is not only for cancer, but also for other rare diseases where gene therapy is effective. But cancer immune therapy is beyond even cell therapy. As I just said, these are immune checkpoint inhibitors, vaccines, many other possibilities. And we are very committed at ICMR to support such research and to particularly participate in clinical evaluations, preclinical and clinical evaluations, and support preclinical and clinical evaluations through the intent network that we have created, which is 75 different institutions in the country that can conduct clinical trials from phase 1 to phase 3. So with those words, I don't want to dwell too much on this issue of the importance. I think we know the importance, we know that it is very much feasible. At the same time, what it will require is a lot of collaboration, both nationally and internationally. We can make these products at an affordable cost. Even if they exist today in the West, they are just too expensive. For instance, I'll just give you the costs. If you go and buy CAR T cell therapy for leukemia and you want to get that therapy in the United States or in Europe, you will spend something between 300 to 400,000 US dollars. And that would roughly mean about 3 crore rupees. And the therapy that is being developed by ImmunoAct, which came out of the IIT Bombay and TMC collaboration, is currently costed at 42 lakhs. So compare 3 crores with 42 lakhs. And I am 100% sure that the cost can be further cut by about at least 80%, bringing the cost down to less than 10 lakhs. And making sure that it is now then available for all our patients, including those who are covered by Rashtriya Arogya Nidhi, or even at one point with the 5 lakh cover of Ayushman Bharat. That is the dream, that all these new therapies, whether they are CAR T, immune checkpoint blockers, inhibitors, or new vaccines that we develop, will be at a cost that is affordable to every Indian citizen. It is our mission at ICMR and Department of Health Research that for Viksit Bharat, the plan that we have prepared, affordable and frontier technologies is number 1 in that plan. Even though this will require beyond ICMR, the Department of Biotechnology, Department of Science and Technology, the Council for Scientific and Industrial Research, and DHR to come together, and that is where we are creating the national mission. However, we will do whatever we can, which is possible for us, to make this a reality that every Indian citizen has access to the best therapies available for treatment of cancer and treatment of rare diseases, which are at this moment not available to our citizens. And I think you all will contribute immensely by those discussions and decisions to move forward with research, development, and creating innovations, and then collaborating with companies and industry which will produce products that are not only available at a very low cost but also are of very high quality. And that is our modus operandi to become Viksit Bharat. And that's our contribution to become Viksit Bharat. Thank you. Jai Hind.
Thank you so much, sir, for sparing your time and gracing this occasion. It is an immense privilege for us to introduce our founder president, Dr. Ashok K. Chauhan, a larger-than-life icon. He had the will to sustain a dream, and God gave him the power to deliver and make that dream a reality. It is only because of his firm belief and unparalleled vision that Amity has reached the top positions with Amity campuses all over the world map. Today, Dr. Ashok K. Chauhan's vision has translated into the internationally benchmark campuses that have come to epitomize the Amity education group. I have too much words I cannot give for founder sir. It is my great pleasure to welcome him, and we request him to kindly address the gathering, sir. Over to you, sir.
My dear students, research scholars, fellows, faculty members, and all those present here, I must say you are witnessing a historical day of this century, because I have been in my lectures in West Germany always telling that for cancer we in India will find a solution. And I'm very much interested also and worried because in 1991 I took my mother and she was 4 times operated in West Germany, and her brother also died because of tongue cancer. So I know the results. So, but my faith that my brilliant minds from 140 crores people will find a solution, and people believe it. We have Ayush, we have Ayurveda, we have also homeopathy, we have Unani, we have yoga. So I will definitely find. And when I spoke to our Rajiv Bahelji yesterday, I was more motivated and more confident that with the help of DG ICMR, we are definitely going to found. I found in Rajiv Bahelji a person who is a go-getter. I have read about him, and more so I was motivated. If a person is holding a position at the chair of the DG ICMR, which has tremendous scope, and what I liked in the reading in the detail, he wrote research to public and many such things in his mind. And Sir Rajiv Bahelji, if you will agree, my people are warriors. They are go-getters. They are persuaders. And with your guidance and help with All India, other institutions, so I told to Rajiv Bahelji that first 2-3 meetings I will have with my people and people from all over India who can give some positive contribution to the cancer matter. And then I told Rajiv Bahelji that we'll request you to come for a while and guide us. And he was so kind. He told Dr. Chauhan, for that I will come definitely. I told him also that in Haryana University there is a convocation on 8th and we want to give you the honorary doctorate. He told Dr. Chauhan, 2 things I don't do. I don't go to convocation and hardly spare time for doctorate. But I must tell you, Rajiv Bahelji is coming today here, and GP Bahelji, and our J.K. Rathji, and our also there's Veraji, who very much helped us in the S20. So students, researchers, have faith have faith that you see the Indians who are successful outside. I still have to understand a lot what is going on in India, what is going on abroad, what can happen. Therefore, few meetings calling from all over India, 20-25 top people in this area, and also Talwarji. We will prepare a interactive meeting with Rajiv Bahelji, and he has agreed to guide us and come to us, because I am confident that we have to find a solution here. There is nothing in the world, if you are committed, if you are determined, you cannot file it. And students, you will remember in your life when the seed was sown of this pledge of Dr. Chauhan, founder president, you were there. My Dr. B.C. Das ji, Dr. Shubhjit Vishwas, Hridesh Prakash, and all organizing committee members, I really appreciate you for taking so much trouble and calling such a great personalities from all over the country. I would not take more time, but once again, you can see the expression of my faith, of my joy, my satisfaction that we will be finding a solution when such great leaders are ready to help me, help you, help MIT. Why should we not succeed? I will meet quite often personally all great personalities sitting over here, and also the founding secretary of the consortium, our Vivek Pandekar ji. I'll sit you also before this conference ends in the 3 days. I also want your advice. And this consortium, I've seen that there are a lot of very worthy members all over the world. We will also have contact with them, meet them. But I tell you, my dear student, we have to find from India, from Indian brain, from Indian scientists, definitely a solution. I don't want to go up by the blame that Dr. Chauhan wanted it, could not do it. I've never done it. And Rajiv Bahelji, once again, I'm so enthusiastic, so motivated, so inspired to listen you, and especially that you found your time. I know how busy you were today, but you told Dr. Chauhan, I'll come. I'm so grateful. And I once again appreciate Dr. Murthy ji, my Vice Chancellor, and also from my MIT University, Haryana, P.B. Sharma ji is sitting over here. On 7th January this year, Rajiv Bahelji had a big function at India International Center, and they gave the award of ICMR Collaborative Center for Excellence to Dr. Rajendra Prasad, who is also attending here, and under the leadership of P.V. Sharma. A large number of people, about 150 applications were there, but among these applications that I got an award, my university got award, this is something, a great compliment to all my MITians. Rajiv Bahelji, once again, and to all my regards and my thanks for coming. We'll be in contact with all so that we find a solution without any fail. Thank you, sir. Thank you.
Thank you, Ji. It was really a pleasure that they were one of the 20 selected centers of excellence, and we look forward to everybody's work together on this very important topic of this conference. Thank you.
सर मैं इसलिए बड़ा इंतुजियाज्म हुआ, राजेंद्र प्रसाद ने मुझे 15 मिनट सिर्फ आपकी तारीफ करी, कहने लगे बहुत ही determined है. So then I had dared to talk to you yesterday. So Rajendra sitting over here, sir, when you have this human approach, you win the heart of everybody. At least you won my heart. That gave me multifold enthusiasm. Thank you very much.
Thank you, Ji. Thank you all.
Ladies and gentlemen, let us please give a big round of applause. Thank you, sir. Thank you for your blessings and your guidance and the motivation. Your words always inspire us to do better and better. Dr. W. Selvamoorthy is President of Amity Science, Technology and Innovation Foundation, Director General for Amity Directorate of Science and Innovation, and Chancellor of Amity University, Chhattisgarh. He has served the Defence Research and Development Organization, Ministry of Defence, Government of India for more than 40 years. It is with great honor that I request Selvamoorthy sir to please share his thoughts about the conference with the audience. Please.
What a scintillating address it was, both from the great two leaders, Founder President Dr. Ashok Chauhan ji, and also a chief guest, Dr. Rajiv Bahel, the Secretary DHR, that is Department of Health Research, and also the Director General of Indian Council of Medical Research. Both of them have given a roadmap, the way ahead. How do we unite together to find a solution for early diagnosis of cancer and also find innovative methods for control, management, and also treatment of this very important disease, which is cancer, which is a major killer today, next to perhaps the cardiovascular disease. So thank you, Mr. President, and we assure you, and also the DG ICMR, that we will all unite together as a consortium, which is already existing, Global Cancer Consortium. We will join together, and we will make a global effort with ICMR and ABITI and all this, the Global Cancer Consortium together. We will certainly assure you the full efforts to find a permanent solution for this cancer of different types. And I had the opportunity of working with Dr. Rajiv Bahal for more than about 5-6 years, because I am closely associated with ICMR. And I see a new paradigm there in ICMR, where the whole focus is coming on the Viksit Bharat, Atmanirbhar Bharat, as well as Swasth Bharat. This is the three pillars on which he is driving the Indian Council of Medical Research and the Department of Health Research to give a focus to control both the communicable and non-communicable diseases. And he is now focusing on new diagnostics, new therapeutics, and deliverables, products, technology, processes. These are the three verticals on which he is focusing. Let's welcome Dr. Rajendra Prasad here, about whom Founder President was speaking. Let's give a big clap to Dr. Rajendra Prasad, who is an icon in the field of the cancer biology, molecular biology, omic studies, and also fellow of all the three academies, a great achiever. And welcome, Dr. Rajendra Prasad. Founder President was just mentioning about your achievement in the form of Center of Excellence being given by ICMR. And I want to thank ICMR because we have an MOU which is working with, this is the first MOU with the government department we signed. And this has worked very well with number of the collaborative R&D, the Center of Excellence, and also number of PhDs being done, mentored jointly by ICMR scientists and the ABITI faculties. So this is working, and we want to do many more. We want to strengthen, expand, deepen our relationship with ICMR. Thank you so much, Dr. Rajiv Bahal, for your wonderful address. The vision for the nation is very clear. The India has to become a developed India by 2047. From maybe about 20-25 years from now, 2047, when we celebrate 100 years of independence, we would have become a developed nation. That is the vision Honorable Prime Minister Shri Narendra Modi ji has given. So the whole system, the 1.42 billion people are geared up to achieve this vision of the Viksit Bharat, and wherein the self-reliance in technologies would happen, and ABITI is making a significant contribution in this transformation of India into a Viksit Bharat. And now coming to the focal theme of this conference, there are a lot of advances which have happened in the recent years in cancer diagnosis and cancer therapy, right from imaging modalities. Now we have positron emission tomography and also the CT scans and MRIs and many, many biomarkers, new biomarkers which can do the early diagnosis and prediction of susceptibility. So a lot of change, a lot of advancement is happening today. We are going to discuss all that. And also the artificial intelligence application in improving the accuracy and early diagnosis is also another dimension in which the whole focus is happening, which is also there in ABITI. Dr. M.K. Datta, we have put an AI facility of 10 petaflop computing capability today in the country. We're one of the largest in the university system. We are upgrading it to 60 petaflop here in ABITI University. And then we are focusing on health, particularly the cancer diagnosis. How do we assist as an expert guidance, even those, the technicians or those the PHCs, primary health centers in villages, to indicate that there is a possibility of cancer. So we are looking at those large-scale screening, mass screening at remote areas, villages, So AI application for screening as well as diagnosis accuracy is another area. Then we are also looking at prediction. Can you predict the susceptibility early so that we can take preventive measures? Instead of focusing only on the tertiary healthcare, can we look at the prediction and also prevention? CAR-T cell therapy, gene therapy, all this was mentioned. But I would like to also tell that the traditional system, how do we combine this complementary systems like yoga, Ayurveda, Siddha, Unani, homeopathy, even homeopathy? How do you bring that as an adjuvant in the control and management and also in prevention of cancer? So this is another important field in which Amity is also focusing, as was mentioned by Founder President. And Amity Education Group today is 12 universities in India, 18 campuses abroad, 28 schools, 250,000 students, and also 10,000 faculties, 5,000 PhD scholars. It's a research and innovation-driven university. We have filed more than 2,300 patents, and many of them are getting translated into product technology and processes. 35 technologies have been recently transferred to the industries, reaching out to the society. The focus is on translation. That is why we established, Founder President established Amity Center for Translational Research, which is giving focus on development of deliverables, product technology and processes to make Amity Education Group as a cradle of innovation. The focus is on translation. I mentioned two important initiatives in cancer from Amity. We are looking at a triple conjugate, a known synthetic anti-tumor agent, combined with curcumin and folate. We have already developed this triple conjugate because it's a Herculean task to combine a synthetic molecule with a natural molecule. We've done that, we've done the in vitro, in vivo studies successfully. Now we are looking for getting into clinical trials. So it's a great initiative, and we are attacking cancer stem cell. Let's give a big clap to Dr. B.C. Das and the whole team, Dr. Niswas, Dr. Manoj, Dr. Pallavi, all those were connected with this triple conjugate, which is very, very important. Then we are also looking at the early biomarkers. There's a big lead here in Amity University, which will be presented. And we are also looking at, can you predict a person getting into metastasis by survival was one of the biomarkers. So there is another research by Dr. Viswas himself, who is looking at survival. And in Unani medicine, Dawamul Kurkum, which is a medicine which is used, and Director General, the Central Council for Research in Unani Medicine has given a go-ahead and supporting the clinical trials. So we have already contacted institutions in government as well as private sector for carrying out. So this is again Amity's contribution. So there are a lot of activities happening in cancer biology as one of the important verticals. Finally, the carry home message, and let us unite together. Consortium means mind, body, and soul unite together as a consortium, not just only intellectual the consortium, but it is you are passionately involved in finding a solution for cancer. So let us unite together with Global Cancer Consortium, with ICMR, with all the experts over here, with Amity universities, together that we will be able to focus on prevention and aggressive approach. Aggressive approach is very important. If you have to find solution, the intent and the speed at which you have to work is very, very critical. And the final message will also be that integrative medicine can be a solution. A person can be diagnosed very early by the modern tools available in the allopathic system. And also he has an option to go for immediate surgical removal, chemotherapy, radiotherapy, and can we also have an adjuvant or complementary system of alternate systems of medicine to make the quality of life better, survival longer, and also quality of life better. So now with this, I would like to compliment Hitesh Prakash. Let's give a big clap to Hitesh Prakash for this wonderful initiative. And also Dr. Vivek Ragnikar, who is the president of this Global Cancer Consortium, and also the founder, who is here of this consortium over here. So we are so grateful that you gave this opportunity to host this. We look forward to work with you very closely, and I'm sure we will do together with you all. Amity University will make a significant, path-breaking, disruptive input into finding solutions for cancer. Thank you so much.
Thank you, sir. Thank you, sir. It's a big compliment. with your guidance, the hepatocellular carcinoma clinical trials. Thank you, sir.
But my special praise for P.B. Sharma because he also got this award. Am I loud?
So let's give a big clap to Amity University, Haryana, the Vice Chancellor, Dr. P.B. Sharma, as well as Dr. Rajendra Prasad. Can you stand up, Rajendra Prasad? Let's give a big clap to Rajendra Prasad. Thank you.
Great.
Thank you, sir. Our next guest of honor of the day is Dr. N.K. Mehra. Dr. Mehra is the Vice President of INSA and Honorary Emeritus Scientist at the Indian Council of Medical Research. He is the former Dean Research and founder head of the Department of Transplant Immunology and Immunogenetics at AIIMS, New Delhi. He has made significant contributions in the area of histocompatibility and immunogenetics and has identified the role of HLA-linked genes in the important diseases of India, such as leprosy, tuberculosis, diabetes, and rheumatoid arthritis. For his immense contribution, Dr. Mehra has been awarded Shanti Swarnim Bhatnagar Award, the highest Indian Science Award, Ranbaxy Science Foundation Award, and Chevalier of the National Order of Merit, France. With great pleasure, I invite Dr. N.K. Mehra to address the gathering.
Thank you very much. I'm so happy to come over there, and I want to thank the organizers for giving me this opportunity to come here. I always love to come here. This is a university which is driven by research and innovation. Not only this campus, but the campus that I go where Rajendra comes from, and he has invited me a couple of times there. And these universities very nearby in the NCR are doing extremely well. So it's always a pleasure to come to this university, and Kadesh has done extremely well by organizing this particular conference. I think this is the time, as Rajiv Bell said, that's the time for the immunotherapy in this health area. We need to develop these two sort of topics in India, and we've done fairly well so far. There are already 2 companies that are established. There's one company that I also mentor, where we are going to make CAR NK cells, natural killer cells. NK is also my name, so I'm very fond of the NK. And the NK cells would be very useful for solid cancers. Also, the government has the T cells. I think the field is growing very, very fast. We are already entering the stage of phase trials and all that. And I'm sure in 2 or 3 years' time, this will become one of the very common therapies with our friends. At the moment, we only have surgery or chemotherapy or RT. And my friend, Dr. Rakesh here, he is the doyen of radiotherapy in India, but we know the side effects of it and associated with it. Selva talked about the biomarkers. I'm sure we need biomarkers here. The population-based differences are there and all that. And towards the end, I don't want to take too much of time because we're already getting late. One other thing that I want to talk about, and I was very happy that Dr. Rajiv Bell said that we're going to make cell and gene therapy in mission mode in India. And that's the message that came from his talk. The other thing I want to talk about, because we're talking of immunotherapy here, we're talking of immunology here. I've got a lot of friends. I see Sajay coming all the way from Russia. The next International Congress of Immunology, the 19th International Congress of Immunology, is going to be held in August in Vienna. By the way, the youngsters should know that we did the 10th International Congress of Immunology way back in 1998, all due to the efforts of Dr. G.P. You heard him. I've been associated with him. I don't make it 5 years or so. He's 98 years and 4 months. Now I talk in terms of months as well. He's 98 years and 4 months. And he comes on the stage to talk to you. This is a tremendous inspiration to all of us. I see here, maybe, sir, there is 10th generation for you. The academic generation 10th over here. We did this Congress in 1998 at a time when everybody around the world thought that we cannot do it because we are an immunology society with only 200 or 200 odd members actually. And how can India do an international Congress? But you see the dynamism that this chief had. I call him chief because he made me the vice chair of the Congress. And it was such a learning experience. And now with the 19th Congress is going to be held in Viviana, and I would want several of our youngsters to go over there. That's the mecca of immunology. You should all go over there, as many of you as you can. There are going to be special sessions on immunotherapy. I'm also the member of the scientific advisory board of that Congress. So therefore, it is my responsibility to encourage as many Indians as they can go over there. But this is really a wonderful opportunity for you. We are all in really the Viksit Bharat stage. We keep talking about this word. This is like developed India. We are looking towards developed India by 1947. And I think all of these therapies will come. And I'm sure all these youngsters, today's youngsters will be tomorrow's senior scientists, and they will do all very well. Thank you very, very much for inviting me.
Thank you, sir. Let us please give a big round of applause. Thank you for gracing the occasion, sir. We are very privileged to have our next guest of honor, Dr. G.K. Rath, a distinguished oncologist and immunologist. Dr. G.K. Rath is former chief of Dr. B.R. Ambedkar Institute, Rotary Cancer Hospital, served as professor, Department of Radiation Oncology, and as director, National Cancer Institute, AIMS. For his immense achievements, he has been bestowed with various awards, including the Lifetime Achievement Award, the Hindustan Bhushan Award, and Apne Delhi Samaj Ratna. With these very few words, I request Dr. G.K. Rath to please address the gathering.
Thank you. Dignitaries of the day, ladies and gentlemen. When I was an MBBS student in 1970, cancer was not talked about. We had only 2 lectures in the whole 5.5 years on cancer. The common causes of death in 70s was not cancer, but communicable disease in this country was cholera, smallpox, and plague. Today, cancer is number 1. If you, because there are students here, there is an article in Lancet Oncology, 3rd of September 2019. Death from cancer has already crushed cardiac. And this is a study from McMaster's Canada, 5 continent, 25 country study. India particularly, anybody wants to study cancer, India is a fantastic country. India is the only country in the world where you can call United States of India so far as cancer is concerned. The lowest cancer incidence in this country is in a place called Barsi, a village in Maharashtra, where the incidence is 40 per 100,000. The highest incidence is in a place called Aizawl, where it is 280 per 100,000. 7 times difference in the incidence is not found anywhere in the world. This is, we call it a mesothelioma of study cancer. Second thing, I call cancer a fantastic disease to study medicine. The reasons are 3. Cancer is 60% in this country, 60% preventable, 60% curable, 60% early diagnosable. We have a fantastic state called Punjab. You will not find a oral cancer there. Proof is here. I have never seen in my last more than 50 years of career a cancer of the oral cavity from our great state of Punjab. Cause is here. So cancer, to study cancer, this is the best thing. What we have done is from the government side and from AIMS, we have established the largest translational cancer research center in a place called Jhajjar in Haryana, because in Delhi we talk of square millimeters, Delhi, Bombay square millimeters. There we have got 300 acres of land and we have constructed the largest cancer research center. Because the time is short, I'll stop here and thank you for inviting me here. Thank you.
Thank you so much, sir, for your words. It's time to release the abstract book for the 5th International Global Cancer Consortium Conference on... So we'll go ahead with the release of the abstract book for the 5th International Global Cancer Consortium Conference on Advances in Cancer and Cancer Immunotherapy. I request all the dignitaries on the dais to kindly unwrap and release the abstract book of the conference. Please give a huge round of applause. Thank you. Now, we would like to very warmly felicitate our distinguished guests of honors who have spared time from their busy schedule to grace this inaugural session of the conference. I request Honorable Vice Chancellor Ma'am, Dr. W. Selvamoorthy Sir, Dr. Chandradeep Tandon Sir, Dr. B.C. Das Sir, Dr. Vishwas, Dr. Hidesh Prakash Sir, to kindly step forward to do the felicitation. Dr. Vivek Rangnekar is requested to join for felicitation. May I request the dignitaries to please felicitate Professor G.P. Talwar Sir. Ladies and gentlemen, please give a big round of applause. He could take out time to be here today in spite of his busy schedule. Thank you so much for joining us today, sir. May I kindly request the dignitaries to please felicitate Professor N.K. Mehra sir. Ladies and gentlemen, please give a big round of applause to Professor N.K. Mehra. Thank you for coming here today and gracing the occasion, sir. May I please request the dignitaries to please felicitate Professor G.K. Rath, sir. Please give a big round of applause. The clap should not stop. Thank you for joining us here, sir. As we come towards the end of the inaugural session, I request the dignitaries to please felicitate Dr. Vivek Rangnekar. Please give a big round of applause. Please join me in clapping for Dr. Vivek Rangnekar. Thank you so much for being here, sir. As we come towards the end of the inaugural session, I now invite Dr. Manoj Garg, Professor and Assistant Director at AIMSR AUUP and Joint Organizing Secretary GCC 2025, kindly propose a vote of thanks.
Good morning and most welcome, everyone. I would like to express my deepest gratitude to most respected Honorable Founder President Dr. Ashok K. Chauhan ji for his unwavering support, vision, and passion for advancing research, innovation, and nation building. The success of the 5th GCC conference would not have been possible without your invaluable guidance, help, and encouragement. A heartfelt thank to our dynamic Honorable Chancellor, Dr. Atul Chauhan ji, for his exceptional leadership, providing us the right infrastructure, invaluable resources, and continuous engagement that empower us to organize this prestigious event. A special thank And congratulations to our Honorable Vice Chancellor, Madam Dr. Valvinder Shukla ji, for providing clear direction, immense help, support, resources, and encouragement in making the 5th International Conference on Advances in Cancer and Immunotherapy a reality. We are also deeply grateful to our esteemed Chief Guest, Dr. Rajiv Behel, Secretary DHR and Director General, Indian Council for Medical Research, Government of India, for his immense contribution to scientific community, especially his dedicated support for translational research and immunotherapeutics. We are honored by the presence of our esteemed guest of honor, Professor G.P. Talwar, Professor N.P. Mehra, Professor G.K. Rao, whose invaluable contribution to immunology, human cancer, and immunotherapy have greatly enriched our conference. I would like to thank ICMR, DBT, DST, INSA, CSIR, Thermo, and other sponsors who have supported this event to make a successful event. A special thank to Professor B.C. Das, Professor W. Sarvamurthy sir, Professor Chandradeep Tandon sir, for their unparalleled support and through thought-provoking insight, which have significantly enhanced the quality of our discussions. We would like to extend our deepest thanks to Professor Subrajit Biswas, Professor Hirdesh Prakash, Professor Vivek M. Rangekar, Professor Tanveer Nave, Dr. Nath Kiran, Dr. Vineet Kumar, Dr. Prakash Baligar, Dr. Palvi Agrawal, Dr. Sonia Kapoor, Dr. Subrata Pore, Dr. Monica, Dr. Sudeep Bose, and all the faculty of AIB, AIMT, AIP, and all the members of the organizing committee for their dedication, hard work, and unwavering support in making this event a grand success. We also extend our heartfelt thanks to eminent speakers, session chair, participants, rapporteur, and coordinators whose active involvement, dedication, and support played a key role in making this conference a grand success. We are equally grateful to Wing Commander M.K. Sharma, Mr. Sushil ji, Captain Kapil Shukla for their assistance and management of the conference. Finally, we extend our deepest appreciation to Dr. Sudhi ji and his team for ensuring smooth operation in a hybrid mode of 5th GCC International Conference. Once again, I thank each and everyone present here for making this event as a success event. Thank you.
Manoj, we also thank Dr. P.B. Sharma, Dr. Rajendra Prasad, who have also joined us on this occasion, and all those who have joined online, not only from India, from other different parts of the world who have joined us. We thank you and we look forward to your continued interaction with us.
Dr. Murthy,
yes, sir.
One word for all. अभी तो पार्टी शुरू हुई है अभी तो पार्टी शुरू हुई है अब मैं आपको चेस करूंगा मैंने कह दिया कि इंडिया इलाज निकालेगी मेरे बारे में कहा था जो चौहान ने कहा वो करा और जो चौहान कहेगा वो करेगा मैं सुनता हूं लोगों से चौहान ने जो कहा वो करा और चौहान जो कहेगा वो करेगा तो अभी तो पार्टी शुरू हुई है
For those delegates from other parts of the country who have joined us, that what he said was, now only the work has begun. The party has started just now. So we have many things to do. And once he makes a statement, success by compulsion, that is his philosophy. We have to succeed at any cost and we will succeed. And I'm sure once we work together, this vision can be achieved. Thank you so much, Founder President.
I thank everyone present online and offline here. Before closing the session, I request all to please rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा जलधितरङ्गा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
We close this session. We will now break for tea, which is served in the foyer area for the conference participants and students. For the esteemed guests and invited speakers, please join us in I2 Lounge. Our next session will start in 15 minutes. Please join us back here in the same hall.
The next session will start with the keynote speaker. So I request all the conference participants to be there on time. For the conference participants, please go to the I2 for the volunteers are requested to guide them. And all the esteemed guests are requested to please join us out in lounge. Welcome back, all of you. Please settle down. So we are starting our next session, which is the keynote lecture by Dr. Danny Welch. This session will be chaired by Dr. Ashok Venkataraman, who has joined us online, and Dr. Vivek and Rangnekar. So I'll just give a brief introduction to our chairs. Dr. Ashok Venkataraman is Director, Cancer Science Institute of Singapore. Distinguished Professor of Medicine and Director, NUS Center for Cancer Research. He is widely recognized for his meritorious contributions in the field of cancer research, effect of genomic instability on carcinogenesis and cancer therapy, and also discovery of BRCA2 gene. Dr. Vivek Rangnekar is the professor and Alfred Cohen Ando Chair at the College of Medicine, University of Kansas, and also serves as Associate Director at the Market Cancer Center, USA. He's the founding chair of the Global Cancer Consortium, and his research focuses on drug discovery, development, and moving compounds for clinical trials. So I give the session to our session chairs.
Welcome back. It's really a great privilege for me to introduce our keynote speaker, Dr. Danny Welch. Dr. Welch is Professor and Associate Director for Cancer Education at the University of Kansas Cancer Center. This is an NCI-designated comprehensive cancer center. Dr. Welch is also the founding chair of the Department of Cancer Biology, and he has made a number of advances in the area of metastasis. He served as one of the presidents of the Metastasis Society in the United States, in North America, and he has identified a large number of metastasis-associated genes. One of them is called KIS1, that he found when he was at the Penn State University in Hershey. He might be able to tell you more about how he came up with that name. But without further ado, I would like to request Dr. Welch to present the keynote talk. Dr. Welch.
Okay.
Thank you very much, Vivek, for the very kind introduction. And thank you all for the honor of being able to come here and speak. And as soon as my slides show up, I am going to be talking today, I've given the title, The Forgotten Genome. And as I was talking to someone beforehand, it's a genome that I think we've all studied, but few of us have in fact remember, and that is in the mitochondria. So, are these slides? Okay, excellent. So, just for the physicians, if there's any chance that you might get continuing education credits, I have really no conflicts to disclose, but I do have to acknowledge that I've been generously supported by a number of organizations. And if any of you are part of the Tata family or other rich families here in India, I'm the man you'd like to donate to for this research. The most important slide in my presentation is this one. It shows you that this work has taken several people to contribute to. Also, I acknowledge the people on the right-hand side. These are patients who have cancer. They are the inspiration for what we do, and they've also helped direct the research that we do in our cancer center and in our laboratory. And the five people at the very bottom are unfortunately people who were great friends, but who've all succumbed to metastatic disease. And they are the inspiration for the work that primarily Isidore, Katie, and Adam have done in the lab. So the outline for this morning is a bit of symbolism. This has been a windy road to identify what we've done. It's not been a straight line where we've known exactly what we expect. It's been a finding of new things. My talk will talk about quantitative trait loci and what are known as complex diseases, and quantitative trait loci and what those are. I'll then do a brief introduction into mitochondrial DNA and how those they are involved in metastasis by both intrinsic within the cancer cell and extrinsic from the tumor host and the tumor microenvironment. And I'll talk about the potential mechanisms by which that is happening. And ultimately, I'll end with some speculation of how we think this information may change clinical practice. And hopefully, for those of you who are doing laboratory work, maybe change a little bit about how you're thinking about the project. I'm not asking you to change what you do, just change a little bit of your thinking in doing that. So complex diseases like cancer, Alzheimer's disease, diabetes, and epilepsy, these are not one molecule causing one disease. All of these diseases involve cooperation amongst different genes that determine the severity of the disease, sometimes even the development of the disease. Mostly, these complex diseases and the genes involved in them are critical in determining how these cells respond to the environment. And our goal is to try and understand this better, especially in the context of cancer and metastasis. This word metastasis is a cancer conference, but it's important to recognize that it is a complex trait. It is well recognized that more than 50 to 100 different genes are involved in the process of metastasis. So it is by definition a complex trait. Metastasis, the spread of cancer to different sites to establish a secondary locus, is involved or responsible for more than 90% of the morbidity and mortality due to cancer. And it's a highly inefficient multi-step process. And it involves different kinds of genes, promoting genes, those that make the metastasis, inhibitory genes, the suppressors, those that inhibit, and modifier genes, and those are the ones I'll talk to you about today. Since he introduced the first gene my lab cloned, we called it KISS1. KISS was discovered in Hershey, Pennsylvania, the home of the chocolate factory. And we called it initially suppressor sequence, SS1. And a friend said, you must give it a better name so people remember it. So I put KI in front of it so people would remember KISS. The irony is that KISS is the master regulator of puberty. you cannot undergo puberty without a kiss. So puberty begins with kissing. Very important to know. But I won't be talking about that any further. First introduced by Kent Hunter at the National Cancer Institute. And he took the mouse mammary tumor virus driven oncogene, the polymyxin driven mouse mammary tumor virus, a transgenic mouse, not more than 90% within 90 days. He crossed that mouse with 27 other strains of mice. And on the right, you see a bar graph, and it may be a little difficult to see, but if he crosses with the same genetic background as the polyoma middle T mouse, he got a baseline number of metastases in the first generation. But you can see some mice strains promoted metastases and others inhibited metastases. And he used the crossover frequency to measure and identify more than 20 different metastasis modifier loci. And he could do this based upon crossover because you inherit half your DNA from mother and half from father. The key to his experiment and what we looked at is that it was always male transgenic mice crossed with females of those other strains. And that was for purely technical reasons. They can't nurse their young. But since you inherit mitochondria only from your mother, the possibility is that those 27 strains mitochondrial DNA could be driving or modifying the metastasis efficiency. So this was the hypothesis that we wanted to test. So is this even worthwhile? Well, what we need to know, you've already learned, mitochondria are maternally inherited. There are hundreds to thousands of copies in each cell, and each mitochondria contains 2 to 5 copies of mitochondrial DNA, a circular DNA that encodes only 37 genes, and it is thought that mitochondria are ancient bacteria that one phagocytosed into another. And importantly, these mitochondrial polymorphisms can be used to define your ancestry clade or colloquially your race. So these are important points that will play a role as I go further into this talk. Also importantly, mice have similar mitochondrial polymorphisms that define the different strains of mice. So we're using mouse models to study mitochondria. So when we proposed this hypothesis, the grant reviewers wrote this comment and did not fund us initially. The mitochondrial genome is too small. It's only 16,000 bases compared to 3 billion bases in the nuclear genome. Well, I'd like you to take a look at this, and I'll just use these 4 words. We'll just use this one. $25 bills. Same 4 words. But if you have a hyphen between 5 and dollar, the value of $25 bills is $100 US. If you have the hyphen between 20 and $5 bills, the value is $25. The hyphen is very small, but it plays a big difference in the value of those 4 words. So the mitochondria, just because it's small, doesn't mean it's not effective. Okay. The one on the right, I love, let's eat grandma. It's a difference between where the comma is, are you going to eat your grandmother or dine with your grandmother? Okay. Small comma makes a big difference. So was there any relevance to our hypothesis? We did a review of the literature and found that copy number variants and small polymorphisms in mitochondria are associated and correlated with metastasis. Unfortunately, most of the algorithms for next-gen sequencing don't factor out the mitochondrial data, and so these numbers of studies are very small. But importantly, different races have different susceptibilities to different kinds of cancer and different kinds of metastases. In terms of metastasis, Kaori Ishikawa in Japan did an interesting study, a beautifully elegant study, in which she took HeLa cells. These are non-metastatic cancer cells, but they're very prevalent. And she treated those cells for 1 year with ethidium bromide. Mitochondrial DNA is exquisitely sensitive to ethidium bromide, and what happens is the cells lose the mitochondrial DNA. She then replaced that mitochondrial DNA with mitochondrial DNA from a metastatic human breast cancer cell, and the HeLa cells became metastatic, changing only the mitochondrial DNA. So this established the precedent that mitochondria could in fact be regulating metastasis at some level. We wanted to study this in more depth, but by treating cells for a year with a low-grade mutagen, we were afraid that there could be introduction of mutations within the nuclear genome involving literally hundreds of different loci, and we did not wish to have that as a problem. So Scott Ballinger and I proposed a different way of making these kinds of mice so that we could study the mitochondrial DNA. And the essence of the technique is to take fertilized embryos, take a needle and pull out the nucleus, and take the nucleus from another strain of mouse and put it in the enucleated oocyte. And then we did PCR, 50 cycles, so well over overkill, to show that we didn't have any hitchhiker mitochondria that came along with that nucleus. These were homoplastic with pure mitochondria from one strain and pure nucleus from another strain, never exposed to a mutagen. We've made a number of strains. You see them on the right-hand side. For the rest of the talk, I'm going to use a two-letter code. The first letter would be the nuclear genome. The second is the mitochondrial genome. C57 black 6 mice is C, C3H is H, BALB-C is B, and FBB is F. So we replicated the Hunter experiment. And there's a lot of data on this slide, but if you can focus with me, can you see my pointer? No, apparently not. Okay, I'll just, as I say, in the polyomymiddle T mouse, our minx mice as the females, our data were identical to those that the Hunter lab collected in terms of tumor formation and latency, as well as the number and size of metastasis. We extended that to another oncogene, the HER2 or ERB2, and Carol and Vivian in the lab aged mice, minx mice, to their natural death and showed that there were different susceptibilities to metastasis without any oncogene specific drivers. Okay. We also did the experiment where we took male minx mice, crossed them with these mice, and since you don't inherit mitochondria from the male, we were able to demonstrate no change in the metastasis or tumor formation, saying that it's not some other factor. This is unpublished data. It's an experiment still in progress in collaboration with John Taylor and Ben Woolbright. Basically, we're treating mice with a carcinogen that induces bladder cancer. And I just think this is an interesting result. The C3H nuclear genome actually makes more aggressive bladder cancers. But interestingly, C3H mitochondria seem to come very close to eliminating the male-female ratio of bladder cancer. Males get about 3 times more bladder cancer than females. This is 0.07 in mid-experiment p-value, but it's kind of an interesting idea, and this would be consistent with a quantitative trait locus. I'll provide these references to others, but the minx mice have been used by other laboratories, and you can see multiple different diseases that the mitochondria are having a distinct effect on. I'm not going to cover these in more detail, but it lets you know that this is a powerful model to study mitochondrial genetics. So even though our data is superimposed with what Hunter found, things still don't quite add up. 37 genes in the mitochondria, only 13 of which are proteins. All of those proteins are involved in electron transport. So there are no adhesion, motility, or invasion genes, immune response genes present in the mitochondria. But all of those genes are required for metastasis, either up or down. How could this genome impact metastasis? Well, our hypothesis, work with Baudur, Carolyn, and John McGuire, was that the mitochondria, the polymorphisms somehow regulate the genes in the nucleus, those adhesion molecules and the like. Okay, and so we did the first whole mouse genome-wide methylation study and ChIP-seq for histone marks. And this is difficult to see, but I wanted to show you that the data do exist. Fewer than 500 loci out of the 3 billion bases in the mouse nuclear genome have changes in the methylation state or the histone marks that are associated with those loci. So the key word here is selectivity of where those epigenetic changes are taking place in the nucleus. We have a lot more informatics to work through, but this indicates that there is probability that the mitochondria are impacting the epigenetics. But during the course of this, we realized that it's not just the cancer cells that are inheriting the mitochondria, it's also the microenvironment cells. Every stromal cell is impacting. So what we did is we took 4 cell lines that are syngeneic, so they're immune matched with the histocompatibility in our mouse lines. We had 2 melanomas and 2 mammary carcinomas, and we took these cells and we injected them into nuclear matched mice, either wild type or with different mitochondria. And we measured metastases. Again, this is data from a single experiment, but the bottom here gives you the conclusion from probably 30 different experiments done over the course of time. Whenever we have C57 LAC6 mitochondria, metastasis is inhibited by 90%. Whenever we have C3H mitochondria, we see 300 to 500% more metastases. So there's clearly something going on here, and it's not within the tumor cell, it's how the tumor cell is responding to the microenvironment. So I hope you're at least convinced from this bit of data that mitochondrial polymorphisms from these different strains of mice contribute to metastatic efficiency and selectively modify the epigenetic marks and histone marks, but also impact the behavior in response to the microenvironment. So what are the mechanisms responsible? I'm going to summarize a lot of data. I'm going to go through it very quickly from a series of experiments that I call OMG omics. Why do I call it that? Because of the amount of data you collect in each experiment, and more importantly, the bill that comes when you do the experiment. These are literally hundreds of thousands of dollars of experiments. We had 117 plausible hypotheses. So we went through this unbiased kind of analyses, the omics studies, to try and help us narrow it down. And we measured a number of different things. The first one that people think about when you hear the word mitochondria is metabolism, electron transport, and so on. We used Ouroboros, seahorse assays, and showed modest but very minimal effects on oxidative phosphorylation or glycolysis. We did metabolomics for more than 5,000 different metabolites. And I think the key thing you can see here, in larger, you would be able to see it easily, but the metabolites and those other studies are superimposed on top of each other. If there are difference in metabolism, there's nothing individually that correlates with any of the phenotypes that I showed you. They may still be there, but we can't find them yet. So we don't think metabolism is the key mechanism responsible. Mitochondria are also responsible for most of the reactive oxygen species present within cells. And Amanda Brinker took a drug known as mitotempo. This is a manganese superoxide dismutase mimic. It scavenges reactive oxygen species. We could treat the tumor cells. They are unaffected in terms of viability and things like that in vitro. And the mice are very healthy at doses in which the reactive oxygen species are way, way, way down. We injected tumor cells into these mice, and I'm going to show you later on the left is a melanoma. Data on the right is mammary carcinoma. Here we have the melanoma that's injected in the syngeneic cells of the C3H background. When we have the C57 mitochondria, again, I told you that C57 inhibits metastasis by 90%, but that effect is also observed. We scavenge the free reactive oxygen species. And obviously, since it's already low, it doesn't change in the minx mouse. Here we have in the syngeneic mouse, we get a low number of metastases. When you add C3H, you get three times as many metastases. That again is washed away when one looks at the reactive oxygen species being removed. I want to acknowledge here, there's one control missing in this experiment, but it's unethical for us to do the experiment. The obvious control is to induce more reactive oxygen species, but that makes the mice so sick that it's not allowed to be done. So this data is consistent in 4 cell lines, but we cannot do the one control that would make all of Koch's postulates come through. And I want to be honest with you, so don't be mad at me, but we can't do some experiments. The one that matches with this meeting in particular is among the cells in the tumor microenvironment or immune profiles. This was work initiated by TJ Beednell, and he's a postdoc in the laboratory. And I'm going to show you just a small amount of the data that TJ collected in looking at infiltration of macrophages into the metastases or dendritic cells into the metastases. And you can see that there are profound differences in the number of macrophages and dendritic cells that are recruited into a tumor. And importantly, for the macrophages, also for neutrophils, there's changes in the polarization state of those innate immune cells. And to summarize this data, most of the effects, in fact, more than 95% of the effects that we see are in the innate immune population. And that was a bit of a surprise for us. Our working hypothesis was that the polymorphisms in the mitochondria might help explain why some patients are hot or cold. That's not what happened to us, but clearly the polarization states are critical. Here's an experiment I call my shower experiment. One morning I'm taking a shower, and as the water is hitting me, I think mitochondria are thought to be ancient bacteria. And we know in microbiology, bacteria communicate with each other to regulate growth of other bacteria by quorum sensing. So we asked simply, do mitochondria retain the ability to communicate with bacteria? And if they do that, they might control their growth and change the microbiome. So we measured the gut microbiome. Here's a quick summary of those data. Here's the parent FBB. The changes in the mitochondria show clear differences in clustering. And the numbers in the red boxes are the species of bacteria that change. We have very selective alteration of the mitochondrial, or I'm sorry, the microbiota in the gut. So this, yes, there appears to be selective communication, at least correlation. So at this point, I've shown you a lot of data. Where are we going? What are those signals that signal to the nucleus and signal to the microbiome? Okay, so I'm about to speculate, but critically, all of the phenotypes that we're studying are complex. Metastasis, heart disease, immune functions, and so on. But there's selective changes in the epigenetics, immune functions, and microbiome, and the selectivity would not be explained by metabolism. We think it's due to the nucleotide sequences where those polymorphisms are. And since the majority of genes encoded in mitochondria are RNAs, I refer to these as among the 50 shades of RNA. And since 22 of the genes are tRNAs, you know what those are. we ask where the polymorphisms are, and there's one polymorphism that correlates with the phenotypes we're examining. That happens to be in the tRNA for arginine, and it's basically an insertion deletion. And we were shocked by this result initially because mitochondria are known to be shuttles for amino acids to the ribosome for protein translation. But in fact, that's not their only function. It particularly studied early in plants, tRNAs can be cleaved into specific tRNA fragments that have stem loop structures that are a lot like microRNAs. These tRNA fragments are involved in a number of different phenotypes, and the number of these phenotypes continues to grow each and every day, but it involves stemness, immune function, growth, protein stability, a number of different functions. And so we are asking, are there mitochondrial tRNA fragments? They're well known from the nucleus, but they hadn't been demonstrated in mitochondria. Because of time, I'm not really going to do much, but we've made probes for the entire span of the tRNA for arginine. And here is just one northern blot. You cannot study tRNA fragments by PCR. I'll explain why after the session, but it cannot be done yet. Okay, but we've detected at least 6 different tRNA fragments. They differ by the number, amount, and the fragmentation size in different tissues, and we are trying to characterize them, sequence them, and look at them. But why haven't we made faster progress? Well, there's no map that corresponds mitochondria. We can't do site-directed mutagenesis because there are thousands of copies. And even with the best CRISPR, we would end up with cells that are heteroplasmic, mixtures of mitochondrial DNA. And that would create a genome instability, which would complicate any potential interpretation. But we still hope that at some point, we will be able to reintroduce good tRNA fragments and maybe remove bad tRNA fragments. And that's the clinical hope that we have. And part of the problem for doing some of these studies and sequencing is because tRNAs are among the most modified bases in cells and so on. So with that, I will draw to a close. But I think this quote, looking at your faces, may represent what you thought with this lecture. Enrico Fermi said to Robert Oppenheimer that before he heard his lecture, he was confused. He's still confused after the lecture, but at a much higher level. So hopefully your level of confusion is at a higher level. And with that, I say thank you so much, and I'll try and answer questions if I can.
Thank you, Dr. Welch. At this point, I want to bring in our co-chair for
Point
this.
the microphone to your. Point the microphone to you. It's no.
Dr. Venkatraman, I think he's online.
Yes, of course. Thank you very much. Thank you very much, Dr. Welch, for a really fascinating lecture. While waiting for questions from the audience, perhaps I can just kick off with a question. I was quite fascinated listening to your description of the mitochondrial anomalies that you're seeing. What selective advantage do you think that they may confer on cancer cells as they evolve?
That's an excellent question. The short answer, I don't know. I think the key part here is to remember that the polymorphisms we're looking at can be based also in just what we observe between people of different races. So polymorphisms that are from Africa convert energy or food into energy that's more required for sprinting, running, chasing down things in ancient man. But in Sweden or other cold climates, Russia, it's cold. You want to convert some of that food energy into heat. So they're both perfectly normal, but they change the efficiency with which things happen. I believe those are the kinds of changes that take place. And another point, since it's related to the immune function, every immune response requires some kind of oxidative burst. So perhaps those oxidative bursts may be the critical elements here, but we need to know exactly what's going on before we can answer the question.
Thank you. Those are very interesting perspectives.
Thank you very much for your great talk. Forgotten genome, I was confused about this genome, but I'm even more now.
No, at a higher level.
Yeah, so I want to ask you, you said that the mitochondrial DNA works complementarily with the nuclear DNA, and in fact, it modulates that effect. So in terms of tumor, say human solid tumors, does the tumor depend on the mitochondrial content of the cells? Of course, the mitochondrial content will vary from one cell to the other. So if the basic role, as you say, of the mitochondrial DNA is to modulate or maybe regulate the nuclear DNA, in that terms, it would mean that the more the mitochondrial DNA in the cell, more the mitochondrial content in the cell, because it varies from one cell to the other. How does it affect the tumor then growth?
Well, we did not find different levels of mitochondrial DNA in the cells. But what may be happening, and again, we just haven't had the full opportunity to study it. Mitochondria in cells that are motile and so on move to places in the cell to help determine invasion, motility, and so on. This is also involved in neuron function. So the polymorphisms may change the ability to move within cells, and also the fission and the fusion of the mitochondria to change during the course of each cell cycle. And again, these are dynamic things, and they're in a steady state, and we will need to address those.
Can I? Two questions. One is, did you check the mitochondrial import of proteins? Because huge number of proteins actually regulate the functions of the mitochondria. Some of them are involved in metastasis also, like MYC. So did you check the effect of the polymorphisms on mitochondrial import of proteins, which are from the nucleus? And the second question is whether you have checked the supercomplexes. Have their constitution or the complexes have been altered because of this polymorphism?
I'll start with the second one. The supercomplexes were studied by Scott Ballinger, who's a real mitochondriac. That's what he calls himself. And there was no overt difference there. You're the first person who's ever asked me about import of molecules from the nucleus. And that's a really interesting idea that we have not looked at explicitly. But now that you've suggested it, I should. So, and I will claim it as my own idea, just so that you know. Okay.
Yeah, there's a question here at the back, and then we'll go to Dr. Kundu.
Hello, sir. Thank you for your insights, because we would have never guessed that mitochondria also play such a role in cancer development. So my question was that we always focus on the nuclear DNA, but how can we begin to integrate mitochondrial DNA into our own workflows? Like what techniques and tools can we use for that?
So, well, the simplest answer to your question is don't ignore mitochondrial DNA. The techniques are largely the same, but again, next-gen sequencing, all of that is filtered out. So don't filter it out. And then the challenge with the mitochondria, in my opinion, is going to be how to manipulate it because of the things I was showing, multiple copies and the like. I think the technology will eventually catch up to answering those questions. But right now, we are at a point where we can look for correlations relatively easily. Applying that information for my clinical colleagues is going to be a bit more of a challenge. But if we keep our eye on doing that, we will eventually get there. Smart people like you will do it.
Thank you, sir.
Dr. Welch over here. So this mitochondrial metastasis in breast cancer is one of that major issue. So what you have shown that your E0771 as well as melanoma model, what happened, especially triple negative breast cancer, basal-like or luminal A or B type breast cancer, do you see any mitochondrial polymorphism, especially in metastasis-associated macrophage, MAM, as well as some of the stromal component like CAF, because there's a different subtypes of CAFs. Do you have any comment?
That is a great question. Again, these are mouse studies. There are no luminal metastatic models that we can study in mice. And the HER2 models that are available are very few and not metastatic. So we're not able to do that. Once we can identify some corresponding change in the human mitochondria, then I think we can address those questions for mitochondrial differences in subtype. But that's not, the tools are not available to us in the mouse at this point. Thank you.
Is there any role for the organotrophic behavior of these tumors? Do the mitochondria actually play a role in sending these tumor cells to particular tissues?
So the question is about organotropism. In my dreams, we would see that, but the mouse models that we use don't metastasize widely to different places. So again, the tools, as the gentleman here was asking, are not particularly well suited for answering that question at this point.
We have time for just one more quick question there.
So I was just wondering that, you mentioned that other than polymorphism, so what percentage of cells in mitochondria do have tumor mutation, but that actually drives the metastasis in cancer cells?
I don't know that I understand the question.
So like you said, it's the polymorphism, if in talks, because that's an, evolutionary process, right? So in case of metastatic cancers, what percentage of cells do we expect that actually modulate, I would say, mutations, metastasis?
So, well, the difference there are mutations and polymorphisms. Polymorphisms are present in the population, but there can be added mutations due to the genomic instability induced in the cancer cells. We're studying at this point the background genetics and the polymorphisms. We're limited in the number of mice that we've been able to create. In people, I believe there are 13 different clades. There are probably that many in mouse, but we have not made all of them at this point. Again, if you're rich, we could do that, but we don't have the funds to do it. So, sorry.
Thank you. Thank you, Dr.
Thank you.
Thank you. It's very nice beginning with.
Dr. Welch, I'm sure the audience is now convinced that mitochondrial DNA has a role to play. I request Dr. Vivek Rangnekar to please felicitate our speaker with a small memento. I request Dr. Welch to please accept it as our token of gratitude for being here and for being a part of this conference and for speaking.
Jenny, this is a symbol of our Indian culture. Yeah, Ashoka emblem. Yes.
Thank you so much. I now request Dr. Videsh Prakash to please present a small token of gratitude to Dr. Vivek Rangnekar. Thank you, Dr. Vivek, for chairing this session. Ladies and gentlemen, students, participants, please give a big round of applause. With this, we now move to our first technical session, the session on tumor microenvironment and immunity. For this, I request Professor B.C. Das and Dr. Selina Gangora to kindly come on the dais. They'll be chairing the session. Professor B.C. Das, we have all met in the morning itself, is the chairman of Family Institute of Molecular Medicine and Stem Cell Research, Dean of Health and Allied Sciences, AUUP, Chairman URC, and Vice President of Amity Science Technology and Innovation Foundation. He is fellow of all 4 national science and medical academies and made outstanding contributions in the field of cancer research, tumor virology, human genetics, mutation research, and special contribution in developing and promoting cervical cancer vaccines. We welcome Professor Das on the dais. Dr. Selina Gangora is a CNRS Research Director and heads the Drug Resistance and New Cancer Therapies team at the Montpellier Cancer Research Institute, France. After completing her PhD in Cellular and Molecular Biology in Montpellier, Selina Gangora completed a postdoctoral fellowship in the USA at the prestigious National Institute of Health, Laboratories in Bethesda. Her research lab aims to develop new therapeutic strategies to overcome resistance, a very major problem, the resistance to anti-cancer drugs in digestive and urological cancers. We welcome Dr. Selina Gangora on the stage. I request them to now proceed with the session and introduce the speakers.
Well, welcome again to the second or the first session, the scientific sessions after the keynote address. So this first session is named as Tumor Environment, Microenvironment and Immunity. And it is with my co-chair, Dr. Selina Gangora. I welcome you all to this session. And in this session, there are 4 speakers in this session. And the first speaker will be Professor Dr. Ashok. So he will be speaking on the metabolic triggers for cancer evolution. And Dr. Venkataraman is the Director of Cancer Science Institute of Singapore and Distinguished Professor of Medicine, Young Lu in School of Medicine, NUS, and Director of NUS Center for Cancer Research. Professor Venkataraman had held a very prestigious position with the appointments at the University of Cambridge. And a few years back, I have met him there, where he served as the Ursula Jola Professor of Cancer Research and Director of the Medical Research Council Cancer Unit. He is widely recognized for his meritorious contributions in the field of cancer research, effect of genomic stability in carcinogenesis and cancer therapy, and discovery of BRCA2 Thank you, Dr. Ashok Venkataraman. I invite you for your talk.
Thank you very much, Professor Das, for the warm introduction. And I'm very grateful to the organizers, particularly Professor Prakash, for having invited me to speak here. I'm sorry that I cannot be present in person, but I hope you will forgive me. It would have been great to meet the many friends that I can already see in the audience. So if you can give me a second, I will start my presentation and just confirm that you can actually see my screen. Are my slides visible, please?
Yes, sir, it's visible.
Oh, okay, perfect. Let me, great. So as Professor Das had indicated, I moved a few years ago from Cambridge to Singapore. And what I'm going to be sharing with you is work that started in my laboratory in Cambridge and has continued for the past 3 years in my laboratory in Singapore. I apologize, I'm experiencing a technical glitch. I can't change my slides, but I will try. No, I'm afraid that my slide presentation appears to be frozen. So please forgive me until, there we go. Excellent, I'm back online. So let me start by outlining the problem that my lab has studied for the past 20 years or so. It concerns early intervention in cancer. As many of you will be aware, we know that cancer starts in lesions that involve tens to hundreds of thousands of cells. At this point, it's potentially curable either with surgery or early chemo intervention. However, it's also a sad fact that we rarely detect cancer until it involves lesions which have billions of cells, at which points it's advanced and very difficult to treat. So we've known for many years that early intervention in cancer has a far greater impact on clinical outcomes, yet it remains the case that only a small percentage of cancer research worldwide engages with this problem. This is the issue that my laboratory has studied for many years. And the particular problem that we are concerned with is how does cancer evolve from dormant pre-malignant cells? With the advent of genome sequencing, we now know that somatic mutations, which could potentially drive carcinogenesis, accumulate in virtually all of our tissues, even though these tissues remain normal. So these so-called dormant pre-malignant cells bearing such mutations accumulate as we age, dependent on our genetic background, and dependent on our various environmental exposures, such as diet and comorbidities, such as diabetes mellitus, which can all enhance the incidence of cancer. Some of these pre-malignant cells can then evolve into cancer cells. We really don't understand this process, nor do we understand what makes these pre-malignant cells accumulate in the first place. And indeed, these are the two problems that my laboratory has been studying. What is it that accounts for the accumulation of somatic mutations that could promote carcinogenesis in apparently normal tissues? And second, once you establish these mutant clones, what is it that determines which of them is going to compete with wild type cells and with one another and establish malignancies in such tissues? One of the model systems that we've been using for quite a while is that of inherited breast cancer predisposition associated with the breast cancer genes BRCA1 and BRCA2. I've outlined a few points for you in case you're not familiar with this system. As we now know, germline mutations affecting BRCA1 or BRCA2 occur in families with a high prevalence of breast, ovarian, and many other cancers. Many somatic alterations affecting these pathways can also occur and can promote carcinogenesis, again in the breast, ovary, prostate, pancreas, and many other tissues. I've shown in the panel below what we know about one of these genes, the breast cancer gene 2, or BRCA2 for short, which, like BRCA1, was discovered in the mid-1990s in Cambridge by Mike Stratton and others. And in fact, we started to work on it soon after Mike and his colleagues had isolated this gene through familial reverse genetics. You'll see in the picture below that this is a very large gene, and it actually encompasses over 3,500 amino acids in humans, and you will see that it has no structural features that enable us to understand its biological function. There are a few structural features which are of note, and in particular, let me emphasize the presence in the middle of the protein of 8 repeats. These peptide motifs are between 30 to 40 amino acids in length, and they recur 8 times in all mammalian BRCA2s, not only is their sequence conserved, so also is their spacing, speaking to potential importance and function. In the clinical side, if you inherit a germline BRCA2 mutation, you're not just predisposed to breast cancer. In fact, it increases your susceptibility to ovarian, pancreatic, prostatic, esophageal, and many other malignancies. It's a high penetrance gene in that if you inherit a mutant copy of this gene on one allele, you have a very high chance of developing cancer. And most patients with BRCA2 mutant cancers exhibit early onset cancers in that they develop at the age of between 40 to 50 years. As I said, we started working on the gene soon after it had been cloned by Mike and colleagues at the Sanger Institute in Cambridge. We were able to create a mouse model in which there was biallelic truncation of both copies of BRCA2, and we quickly realized that a major role of BRCA2 is in the preservation of genome integrity in dividing cells. And this is easily visible, I think, if you look at the chromosome pictures on the left-hand side. You will see that in BRCA2 deficient cells, a wide variety of aberrations in chromosome structure and chromosome number accumulate in these cells. We and others later went on to show that this arises because BRCA2 has a function in DNA repair by homologous DNA recombination, as well as in the protection of stalled DNA replication forks. And this work, of course, has been done by many labs, not just my own, over the past 15 years or so. We have focused in my laboratory on trying to understand the molecular basis and structural basis for the function of BRCA2 in DNA repair by homologous recombination and in replication fork protection. And it's been very satisfying in recent years to recognize that essentially both of these functions emanate from a single structural mechanism, which is the ability of BRCA2 to guide a protein, an enzyme called RAD51, which is the mammalian equivalent of bacterial REC-A, to appropriate DNA substrates at sites of replication blockage or of double-strand DNA breaks. I'm not going to take you through all of the work that we've published on this point, but suffice it for me to draw your attention in the first instance to the panel on the left-hand side of the screen. You will see that we were able to reconstitute recombination using recombinant RAD51 and recombinant substrates, single-stranded and double-stranded DNA substrates. And very briefly, this reaction does not work under normal ionic conditions in the presence of RAD51 alone. And the reason is that because the RAD51 promiscuously engages double-strand DNA rather than the single-strand substrate, and so the reaction pauses, unable to move forward. If you add the BRC repeats of BRCA2, what they do essentially is to reorder the strand selectivity of RAD51. Now the single-strand complex is stabilized with RAD51 and the double-strand complex is inhibited, enabling the reaction to proceed. And from this observation, we have since, using X-ray crystallography as well as more recently cryo-electron microscopy, been able to characterize the structural mechanism by which the BRCA2 BRC repeats engage RAD51 and guide the strand selectivity of BRCA2. What I'm going to talk about for the next 15 minutes or so is another problem, which is, given these functions of BRCA2 and given the effects of biallelic BRCA2 loss on DNA repair, replication protection, and genome stability, how does BRCA2 inactivation actually cause cancer? As you all know, BRCA2 is a tumor suppressor gene, and I think all of you in the audience will be familiar with the classical model put forward by Al Knudsen in the 1970s, the so-called two-hit theory for tumor suppression based on Al studies on the retinoblastoma gene. Essentially, what the two-hit paradigm hypothesizes is that you can inherit one mutant copy of a tumor suppressor gene and one wild-type copy in a precancerous state. But the second copy, the wild type copy, is inactivated either by genetic rearrangement or by methylation or some such epigenetic phenomenon, allowing cancer cells to inherit two hits, inactivating the tumor suppressor gene and enabling cancer progression. And indeed, we have for many years in the field thought that BRCA2 obeys the two-hit paradigm, in that the second BRCA2 copy is lost in certain tissues and that this inactivation can foster carcinogenesis. Please remember that it's also important because targeted therapies such as platinum compounds used in the clinic or PARP inhibitors only work if the second copy of BRCA2 is inactivated in the cancer cells. That's where the therapeutic index from the surrounding normal cells in the mutation carriers comes from. So I was rather surprised when about 15 years ago, Ferdinando Skoulidis, then an MD PhD student in my Cambridge lab, now leading the thoracic oncology section at the MD Anderson Cancer Center, found in a mouse model for pancreatic cancer that we had developed that BRCA2 can violate the two-hit paradigm. Because these data are already published, let me just highlight some of the important points. What Ferdinando's found in this mouse model of pancreatic cancer driven by mutant KRAS is that even heterozygosity for BRCA2 promotes carcinogenesis, and moreover, that in these tumors, the second copy is not inactivated either by genetic events or by epigenetic mechanisms. We then reached out to Jon and Jorunn at the Icelandic Cancer Registry because many people in Iceland carry a founder mutation, which recapitulates or mimics our mouse truncation. This is the BRCA2 999del5 allele. And what Jon and Jorunn were able to show is that in pancreatic cancers from their cohort, again, many of these pancreatic cancers arising in the mutation carriers did not lose the second allele. And indeed, we were able to show that these cancers are resistant to PARP inhibitors and platinum compounds. So there's clinical significance. How does this actually work? This has been a holy grail, if you will, within my laboratory for the last 15 years or so. And our first breakthrough came about 5 to 7 years ago when Sean Tan, then a PhD student in my laboratory in Cambridge, decided to expose BRCA2 heterozygous cells to many different types of genotoxins. Essentially, he found that BRCA2 heterozygous cells were just like wild-type cells in exposure, in response to almost every genotoxin we could throw at them. But he tried aldehydes, formaldehyde and acetaldehyde in particular, which are well-known genotoxins. And he found that then there was a difference in the ability of the heterozygous cells to sustain replication protection. We were able to show that this involved a new proteostatic mechanism. We were able to show that when BRCA2 deficient cells are exposed to aldehydes, there is activation of a proteolytic cascade, which we think is ubiquitin independent but dependent on subunits of the 20S proteasome, that catalyzes destruction of BRCA2, and when BRCA2 levels fall below the functional threshold, that in turn, we think leads to events that could trigger carcinogenesis. We call this idea induced haploinsufficiency because the BRCA2 heterozygous cells are not haploinsufficient until they are challenged with aldehydes. Induced haploinsufficiency. And we think this could be quite an interesting concept in terms of the way that our environment interacts with genetic predisposition to predispose to cancer, because as you know, aldehydes are very common constituents of cellular metabolism, and we're also exposed to them in our environment through automobile exhaust, cosmetics, as well as alcohol drinking. Obviously, then, we asked whether people who carry mutations in genes that catabolize aldehydes, such as the famous flushing gene, ALDH2, aldehyde dehydrogenase 2. People who bear this mutation are common in East Asia, and they can't tolerate alcohol. If they have even a drink or two, they flush because acetaldehyde accumulates. So we asked whether these people had an increased prevalence of breast cancer in BRCA1, BRCA2 mutation carriers, and our colleagues in Japan, led by Minoru Takata in Kyoto, quickly showed that there was no impact. And that led us to think, is our hypothesis right? Might other aldehydes be involved? And at that time, my penultimate Cambridge PhD student, Miriam Ferrer, was working with Tobias Janowitz at the Cold Spring Harbor Labs, and she came upon an observation that focused our attention on energy metabolism. I'm not going to share Miriam's findings with you, but suffice it to say that she discovered in the Cell Metabolism paper published just a couple of years ago that lipid peroxidation products, which include aldehydes like malondialdehyde and 4-HNE, can indeed induce changes in cellular DNA that might lead, in her case, to apoptosis. So we've revisited our pancreatic cancer model in the mouse, which is RAS-driven pancreatic cancer, and looked at the aldehyde connection. This slide is just to remind you, it's a very complex mouse model which involves no less than 4 different conditional alleles, many of which we obtained from my friends and colleagues like Tyler Jacks in Boston, David Tuvison, now at Cold Spring Harbor Labs, as well as Ton Berns at the Netherlands Cancer Institute. But these mice show the occurrence, or the acceleration, I should say, of pancreatic cancer, the green line in the Kaplan-Meier curves, even with loss of 1 copy of BRCA2, and these cancers do not lose the second copy. Ron DiPigno had shown some years ago that when you activate mutant KRAS, you increase glycolysis. So we turned our attention to glycolysis, and you can see here a description of the pathway, and it would not have escaped your attention that a predominant intermediate in the pathway is a dialdehyde, methyl glyoxal, or MGO. In fact, in the clinic, we use MGO conjugation to hemoglobin, HbA1c, as a marker for diabetes control. So it's an abundant, prevalent marker of diabetes. We can show in pancreatic tumors and pancreatic cells derived from these KRAS mutant mice, indeed the pathway is activated as you would predict from Ron's results. And moreover, that all of these cells accumulate protein conjugates on bimethyl glyoxal, which can be detected with the MGH1 antibody in the Western blots. As all of you know, Ludmil Alexandrov over the last 10 years has described through DNA sequencing, next generation sequencing, many patterns of so-called single base substitution mutagenesis that occur throughout cancer genomes. There are over 80 different classes, and each of these classes is associated with a certain insult or a certain origin, a mechanistic origin of genome instability. In particular, characteristic single base substitution patterns arise in cancers that lack the function of genes like BRCA1 and BRCA2 through defects in homologous recombination. So you can characterize loss of BRCA2 function by detecting these SPS patterns. So we looked in our pancreatic tumors from the mice for these patterns, and you see the striking result that we obtained in the bar graphs on the left-hand side of the screen. Totally unexpectedly, the KPC BRCA2 heterozygous mice exhibit a pattern reminiscent of loss of BRCA2 function, even though, as you can see on the right-hand side, they all retain a functional copy of BRCA2, they express BRCA2 protein, and they remain resistant to PARP inhibitors, showing that they are not haploinsufficient for BRCA2 function. In fact, what surprised us that even about half, 40% of the wild type mice, which have intact BRCA2, were exhibiting this pattern where you have enhanced glycolysis. So how does this work? We turn to in vitro models, and here I'm just showing you some due diligence experiments. Aldehydes are very difficult to work with in cell culture systems because they are very labile and they conjugate very rapidly with proteins, even fetal calf serum in the culture media. So here what we did was to take cells and inactivate genes involved in methyl glyoxyl metabolism. We inactivated the glyoxylase 1, GLO1, and we inactivated ALK-BH7, a mitochondrial enzyme whose inactivation leads to excessive methyl glyoxyl accumulation. And we measured the levels of MGO in these endogenous settings. And you see that you accumulate in these cells somewhere between 100 to 500 picomole per mil of MGO in this sort of natural setting. What we then did in the bottom panel is to titrate the addition of exogenous MGO in our model system to faithfully recapitulate the same intracellular concentrations of 100 to 500 picomoles. Then we did a rather challenging, or should I say heroic experiment. We did whole genome sequencing at great depth in cells carrying BRCA2 and other mutations, and embarked on a pipeline to call SPS mutagenesis from these sequencing experiments. You can see that we used multiple subclones at each step. We subtracted backgrounds, all to ensure that what we were seeing is de novo SPS mutagenesis, ongoing mutagenesis. This experiment visually captures a huge panoply of different results. I draw your attention to the blue histograms, which represent the BRCA2 associated SPS mutagenesis signature. There are three cell types here: BRCA2 wild type, BRCA2 heterozygous, or BRCA2 null. And you can see that SPS signature, even without any challenge, already occurring in cells which have lost both copies of BRCA2, just as you would predict. But look what happens when we expose heterozygous cells to low doses intermittently of methyl glyoxyl over time. And I hope you can see with the arrows that many of these clones begin to acquire the characteristic pattern of SPS mutagenesis associated with BRCA2 inactivation, but they don't lose BRCA2 at the level of DNA, at the level of protein, at the level of RNA, or at the level of function. BRCA2 is only temporarily inactivated, we inferred through aldehyde exposure, but it retains function at the end of the experiment and at different times during the experiment. We have gone on to recapitulate these findings using human breast organoid models, which we have derived from tissues derived for prophylactic mastectomies of mutation carriers, comparing with wild types. And what you can again see, for lack of time, I won't go through all the data, the key take home is intermittent exposure to aldehydes induces SPS mutagenesis without permanently inactivating BRCA2 at the level of DNA or RNA. We can even see these types of patterns occurring in breast cancer tissues, strikingly even from non-BRCA1, BRCA2 breast cancers, particularly we think in patients who may have comorbidities like diabetes or obesity, which are known to predispose to this disease. Charlie Swanton at the Crick Institute has posited that we cannot explain cancer evolution through linear events. Instead, he supposes that from next generation sequencing, there are macroevolutionary events, something like a comet hitting the planet Earth and wiping out all the dinosaurs, which then sparks evolution. So we wondered whether metabolic exposures of the type that we have described might be such macroevolutionary events. Again, for lack of time, I'm not going to take you through all of the data, but suffice it to say, another really heroic experiment done by my colleagues in the lab, we explored whether intermittent exposure, regrowth of clones bearing BRCA2 heterozygosity could re-invoke these patterns of macroevolutionary events during tumor evolution in vitro. And as you can see from this description, they do. And these events are represented by the occurrence shown in the orange circles of the BRCA2 associated SPS mutagenesis signature. So what do our data imply? This work was very recently published in Cell just a few months ago. We think we are describing an alternative approach or an alternative way that you can get two hits in tumor suppressor genes. In other words, a revision, if you will, of Al Knudson's classic two-hit paradigm. We think that the type of metabolic bypass that we're describing here, induced by methylglyoxal, triggered by excessive glycolysis and potentially by metabolic disorders like diabetes or even obesity and poor diet, can temporarily cause the second hit and is sufficient to trigger the genomic instability that is associated with carcinogenesis. And we're now working very hard in the lab to establish a number of in vivo and clinical models to test whether this occurs in patients, both carrying BRCA2 mutations and those who are wild type for these mutations, to see if it has a significance in these systems. I don't think I need to remind you that in Asia, obesity, poor diet, and metabolic disorders like diabetes affect well over 500 million people. We still don't know why they have an excess of cancer, but we believe that our results suggest that they may induce mutagenesis in apparently normal tissues, leading to the accumulation of mutant cells with cancer-driving mutations that can eventually potentiate selection and the evolution of cancer in these tissues. And as I said, we are yet to test this hypothesis in the human setting, but we're working on it. So I'm going to wrap up by saying, great, we know this, but what are we going to do about this? And I'm just going to share with you 2 slides representing the other facet of my laboratory, which is trying to develop new technologies for drug discovery based on structure, biochemistry, and genetics. All of you know that virtually all cellular pathways are regulated not by enzymes alone, but by macromolecular interactions. And you're also aware that macromolecular interactions have remained inaccessible as drug targets to current methods for drug discovery. So in my Cambridge lab and now in Singapore, we have been developing a series of tools to find ways to drug these interactions. And I'll just share with you that some of these tools have now been validated, genetic tools to identify and validate macromolecular interaction targets. The work is published, so you're free to look it up. And this work has been spun out into a Cambridge spin-out, Foremost, which is now collaborating with major players in pharma to bring this to the clinic. And so also we have developed several new methods for structure-guided discovery of drug-like ligands. Again, several of these we expect to reach clinical trials in the next 6 to 12 months through collaborations with industry. So I hope I have been able to give you a whistle-stop tour of the 2 aspects to my laboratory, the 2 questions we focus on: why are some people more susceptible to cancer than others? And what can we, in the end, do to treat, delay, or prevent cancer onset by developing disruptive new technology platforms? I thank you for your attention. The work started in Cambridge. It's been continued in my Singapore lab. This is what I do in my spare time. And here's a picture of our lab enjoying ourselves, and particularly Lee Ren was the protagonist in many of the studies that I just shared with you. Thanks for your attention.
Thank you very much, Dr. Venkataraman. And it's an interesting, very interesting talk. And now this talk is open for discussion. Very quick questions, 2 questions. Yes, please.
It's a great concept and, great work. I just have a small question. Does those SBS, BRCA2 mutants show gain of function property?
So what I'm referring to, that's a very interesting question. We don't know yet, but what I'm referring to, I remind you, are patterns of genome-wide mutation rather than mutations in specific genes. When we do deep sequencing, we see these patterns of mutation which represent base transversions of different kinds occurring throughout the genome, not just in specific genes. So at the moment, we cannot say whether they cause gain of function or loss of function. In theory, they could do both. but those experiments long-term are underway.
Okay, thank you. Next.
Professor Venkaraman, for a wonderful talk.
Thank you.
A question related to the mechanism by which that BRCA can actually contribute to this haploinsufficiency. Did you ever look into the BRCA have any undergoes dominant negative effect? Because
That's a very important question, and I'm sorry that I didn't share the results with you, but yes, we did, and many others have also. So when we look in our haploinsufficient, that is our heterozygous cells, we expose them to many different types of genotoxins, radiation, ultraviolet light, double-strand break-inducing reagents, replication blockers. Other than aldehydes, there is no evidence of functional haploinsufficiency. These are with truncating mutants. We don't know whether point mutants, which result in the creation of a BRCA2 mutant protein, may cause haploinsufficiency or dominant negative effects, but those are relatively uncommon. They only represent a few, 10 to 15% of clinical BRCA2 cases. That we don't know yet, but the truncating mutations, which account for the large majority of BRCA2 carriers, don't seem to be haploinsufficient except when you expose them to aldehydes.
Thank you. Next, please.
Hi, Ashok. This is Sridhar Ganesan.
Oh, hi, Sridhar. Good to see you.
Great talk. This really explains the SBS3, phenotype. When you exposed to aldehyde and saw SBS3, and you did whole genome sequencing, did you also see the rearrangement pattern associated, rearrangement pattern 5, or is this really able to dissociate the SBS pattern from the rearrangement pattern?
That's another great question, Sridhar. The problem you will see is with the number of mutations. So we are doing these experiments in vitro, and what we're doing is to subtract background by deriving multiple clones at every stage of exposure. So we always have to subtract background. And when we subtract background, we find the de novo mutations that occur number in the thousands to tens of thousands across the whole genome, which given the 3 trillion base pairs is not a huge number. We're sure that they happen. But we don't think that we have taken the experiment far enough to look for the insertion deletion mutagenesis signature. These ID signatures are relatively less common, or yet for structural variants. Longer term experiments involving bulk sequencing are underway, but I suspect they will take us at least another 6 to 12 months before we can read out. It's a great question.
Thank you. Kumar.
Yeah.
Kumar.
Ashok, Kumar here.
Hi, Kumar. Good to see you.
Yeah. If I understood correctly, 2-hit hypothesis remains there, except that you are saying second hit can be replaced by, at times, the transient metabolic bypass. That's what you are trying to say.
Exactly right, Kumar.
Is that applicable to other tumor suppressor genes, including BRCA1?
We have not found any evidence of this occurring with BRCA1, but soon after our paper came out in Cell, there were 2 papers, which you may have seen. They show that P53 can also be inactivated by another byproduct of energy metabolism, which is lactate. But the mechanism there, alluding to what Dan Welch shared with us, is via tRNA lactoylation. There was another paper then that came out showing that MR11, another tumor suppressor, can also be inactivated by lactate, and here it's a direct conjugation mechanism. So we and many other labs are busy looking for all the different tumor suppressors and all the different metabolites that might potentially cause such mechanisms to occur. I do believe now these results suggest it's a more widespread phenomenon.
So thank you very much. So we cannot have to felicitate you as you are online. So thank you so much to make
Thank you. It was a real pleasure. Thank you.
Thank you. Thank you so much. And the next talk now would be by Dr. Manos K. Paul. So this is he will be talking on IRF1 shows opposing functions in tumor cell intrinsic and extrinsic mechanism of anti-tumor immunity. Dr. Paul is an associate professor at the Manipal School of Life Sciences, Mahe, Manipal. He worked in the University of California, Los Angeles, USA for nearly 14 years, and he has contributed significantly in stem cell biology, regenerative medicine,
organoid biology and drug discovery and immune oncology in lung cancer. Dr. Paul is recipient of many of the awards, prestigious AAISCR Award, Vijay Lakshmi Award, and then Innovative Cancer Research Award, UCLA Vice Chancellor's Award, and the Editor's Choice Awards for the annuals of biomedical engineering. With these words, I welcome Dr. Paul to deliver his talk.
Hello. Good afternoon, everyone. Thank you for the organizer to give me an opportunity to present my work. And I will be talking about tumor intrinsic and tumor extrinsic factors that can regulate tumor growth. And this is a beautiful image where you can see the tumor and the stroma. The blue is the tumor and the red is the stroma and the immune infiltration shown in this. Not moving. So today I'll be talking about the understanding the tumors and intrinsic and extrinsic roles of IRF1 and anti-tumor immunity. So as you all know that interferon signaling is very important, and there can be two types of interferon signaling: type 1 interferon and type 2 interferon. And this interferon signaling goes via the JAK-STAT pathway, and the STAT then interacts with the ISRE and activates the IRF1 gene. So the ISRE is the interferon stimulated response element, right? So then what we know that this interferon signaling is very important for tumor ecosystem and anti-tumor immunity. And this type 1 and type 2 interferon both are important for critical anti-tumor response. And interferon regulatory factor 1 is a transcription factor that plays a vital role in regulating production of type 1 interferon and type interferon induced genes. And in the literature, there's a dubious role about IRF1. It's a double-edged sword. If the IRF1 is high, IRF1 is known to actually play a role. Here, how this IRF1 plays the dual role in tumor progression. So we thought that whether we can sort it out, the role of IRF1 by doing experiments where we can study the effect of IRF1 both in intrinsic and extrinsic factors. So IRF1 is expressed in multiple cell types like the T cells, NK cells, and the conventional DC1 cells, and it's also critical for expression of PD-L1. So PD-L1, as you all know, can play a key role in cancer immune escape, and so this IRF1 is known to activate PD-L1 expression, which causes immunosuppression. And to better understand this role of IRF1 during an anti-tumor immune response, we did a simple experiment. So what we did is, we can see that we have did a CRISPR knockout of, on this left-hand side, you can see we have done a CRISPR knockout of IRF1, and the data suggests that IRF1 is knocked out in these tumors. So these are IRF1 mutants. We have used the MC38 cell line, which is a mouse colorectal cancer cell line. Why we use mouse colorectal cancer cell line? Because the MC38 cell line has high expression of MHC1, and this can be very highly immunogenic. That's why you use this immunogenic cell line. So what we did in the experiment, as a part of the experiment, you can see here in number C, we have taken this MC38 cell line and we have grown in the dish. And these are IF1. So we have used wild type as IF1 knockout and skin knockout tumor cells. And then we have injected subcutaneously in the host. Host is wild type C57BLC, which is endemic to these cell lines. And we have taken the tumor measurement over time. And what we are seeing here that in the wild type and sting knockout, both the tumor sizes are same, and there is no difference between these. In the B, in the section B, you can see, and you will appreciate that IF1 knockout was a significant decrease in the tumor size. So what we are seeing, and we have used all the clones here to understand the effect of IF1. So it suggests that if IF1 is not there, then the tumor size grows significantly small. So the question is, does tumor intrinsic IF1 expression impair immune cell recruitment to the tumors, or it has different roles? So what we need to understand that, so we have used, so wild type, sorry, I need a pointer, the pointer is a bit trouble. So we have used wild type IF1 and, sorry, give a point. So you can see in number F, what we have done is we have used wild type or IF knockout cell line, and we have used normal mice, wild type mice. So the host is wild type, and we have injected this on the flank. And we then studied the histology and multicolor FACS imaging and immunofluorescence imaging of this infiltrated tumor infiltration we studied. What we found is, you can see in the number G, is that there is a significant increase in the CD45 positive cells in the IF1 knockout. And when we tried to understand what is the effect on T cells, we found that the T cells are also significantly infiltration has happened to the CD3 positive T cells, and CD4 positive is not that significant, but CD8 again, T cells are significantly high in the IF1 knockout cells. Same thing we see in the NK positive cells, NK 1.1 positive, and NK T cells and NK cells. And myeloid cells, we don't see much difference, like the macrophage you can see here, and the dendritic cell, we don't see much of a difference, so it's not significant. So what the question is, increased infiltration of adaptive immune cell is associated with impairment of the IF1 tumor is the question. So what we did is, after that, we did immunofluorescence microscopy, multiplex immunofluorescence microscopy, and here the CD4 cells are shown in green and CD8 cells are shown in red. And you can see that in the white type, there is a tumor margin, as you can see, is marked here, tumor margin. And you can see the immune cell infiltration is very low, especially on the margin and especially in the inside of the tumor. So in IF1, you can see a significant difference as compared to the wild type in regard to tumor immune infiltration. So why this is happening and how it is happening is a very important question. And so as you know, the immune infiltration is very key to tumor lysis or tumor killing. So, and this is the HME of this, the tumor histology is shown here. And you can show that there's a lot of stromal infiltration in the IF1 tumors. And while the normal tumors, wild type tumors are solid, and there is a very clear tumor boundary is there in this case. So to confirm that we are seeing the same thing in other cells, we used two cell lines, what is called B16, F10, and we use YAM2.1. Both are melanoma cell lines. To confirm that it happens in all type of tumors, we use this. So we use this two cell lines. So as you can see here, and so that we got similar data, as you can see, it's a very strong data that IF1 knockout can cause significant tumor reduction, and in both B16, F10 and YAM21 cells. And this suggests that IRF1 has a definite role for tumor proliferation and immune escape. So then we wanted to know whether the growth kinetics of wild-type IRF1, PC38, MC38 tumors in immunodeficient mice. To confirm that the immune system is very important for this tumor cell killing, we then used several cell lines, mice lines. We used NOTSKIT, we used RAG1, we used CD8, and we used RAG2 gamma C mice in which they have NOTSKIT. You know that they have TB innate lymphoid cell deficiency, and RAG1 we have TB cells deficiency. CD8 we have CD8 positive T cell deficiency, and RAG2 gamma C has TB NK cell deficiency. So if we are putting these tumors, this wild type and IRF1 mutated tumors in this NOTSKIT RAG1 deficient, CD8 deficient or wild type mice, what is the size of the tumors we are getting? We studied them. So you can see in this B, in section B of this figure, we can see the RAG1 shows significant difference in the tumor size. The IRF1 tumor does not grow much in the RAG1, and same with CD8 negative mice lines. The IRF1 does not grow. And in wild type, the same data we get, that is significant tumor reduction. And RAG2 gamma C also we see significant reduction. That means we see an effect of the role of NK cells and T cells in the tumor extrinsic role of NK cell and tumor cells in the IRF1 knockout tumors. So the growth of IRF1 MC38 tumors in RAG1 and CD8 mice was intermediate to wild type mice and RAG2 gamma C or not SKIT mice, indicating that both the CD8 T cells and NK cells contribute to the generation of enhanced anti-tumor immunity. So from this, we understood this very clear now. Now, what we did is to understand whether tumor cell intrinsic IRF1 expression impairs immune checkpoint blockade. So what is the role of this in your immune checkpoint blockade? And as we know, we have multiple type of immune checkpoints, out of which the important ones are PD1, PDL1, and CTLA4. So what we did is, in this case, we did an interesting experiment where we used wild type and IRF1 knockout MC38 cell lines, and then we used anti-mouse PD1 or anti-CTLA4. So that we can stop the expression of PD1 and CTLA4 in the tumor. Here, as you can see, and then we studied this on different days, day 8, 11, 14, and 17. What we found that in wild type, as you can see in B, the wild type tumors are same when we use anti-PD1, and wild type CTLA4 also there is no significant difference. What does the data suggest? The data suggests that CTLA4 and PD1 is not important in wild type MC38, but when we do it in the IRF1 knockout MC38 cells, we see a significant effect in case of CTLA4, but not with the PD1. So CTLA4 can be also a very important downstream component of IRF1 knockout IRF1. And here you will appreciate that we have used 2x times of cells, means twice the number of cells to generate these tumors, because IRF1 MC38, the tumors are getting lost. They don't form tumors. It can form palpable tumors, but after 6 to 9 days, we can see palpate the tumors that they are forming, but after that, the tumors are gone. So we have now used 2x times of tumor cells just to see what is happening. And as you can see, the CTLA4, as also known that the CTLA4 can be an important mechanism. So we can see from this data that presence of IRF1 in tumor cells suppresses adaptive immunity to tumors and limit the effectiveness of ICB responses. Now, to better understand that what is the cell types that are associated with this IRF1 knockout phenotype, what we did is we did a RNA-seq data for the tumor and the wild type stoma, and we found that there are almost 12 cell types we found that are different. And then you can see on the A, that wild type and IRF1, And then we compare that with, here B is the bar graph representation of their different expression level, different numbers, percentage of the wild type MC38 cells, and IRF1 knockout MC38 cells. So you can see on the left hand side of the B, we can see the cells which are higher, and as you see, cancer cells are higher. And in the right hand side, we are seeing what are the cell types which are higher in IRF1 knockout cells, knockout tumors. We can see a significant association of NK cells, CD8 NKT cells, and CD8 effector memory cells, and also CD8 naive-like cells, which is similar data we also got from the immunofluorescence earlier. So again, confirming that these are the cells which are important in IRF, which can be modulated by IRF1 when IRF1 is overexpressed in the tumor. And this dot plot can show again the similar thing when IRF1 tumor showed enhanced expression of ISGs in almost all cells of the TME. And one interesting thing is we can see an expression of increased expression of CCL5, PD1, GB5, GBP5, IRF1, IRF8, IRF7. These are overexpressed in these cell lines when we have IRF1. So tumor cell intrinsic IRF1 expression suppresses the overall activation state of multiple immune cell types, including innate and adaptive immune cells in growing tumors. So that is one way how IRF1 suppresses the tumor response, anti-tumor immune response. So to further understand how this is happening, we have done the wild type and IRF1 MC38. We have tried to check whether what is the role of interferon gamma response on this. So interferon gamma we have added for 2 hours and we harness it to identify IRF1 regulated ISGs. So here we can find that IRF1 dependent, there are in the B, you can see that IRF1 dependent, there are certain genes which are highly expressed in this one. And you can see here in the PDL1 is there. One is the PDL1 and one is TRAIL, one is TMEM 140, and there is NOS2 and there's IDO1, which are highly expressed when IRF1 is there, and which is also interferon gamma dependent. And out of the independent one, interferon gamma dependent, we have SARPIN31, FAS, CXL9. And then we try to understand what is that, what does that it binds to PD1 to induce exhaustion of immune cells. So it is important. TRAIL is also a very important factor which has been reported multiple times. And we are showing here that this IRF1 dependent, and TMEM similar way has been shown as a prognostic factor in multiple cancers. And here TMEM40 is also dependent on the IRF1 expression. And CXCL9, CXCL10, CXCL11, these are all chemokines which are important for the T cell and NK cell infiltration.
Dr. Paul, just 3 minutes left.
And so now the question is, now what is happening if we change the host and keep the tumor cell and the host different. So we also use interferon gamma receptor, interferon gamma receptor, interferon type 1 interferon receptor knockout, type 2 interferon receptor knockout we use to understand whether type 1 or type 2 is important. And we can see that interferon IRF1, like interferon 1 is more important compared to interferon 2, in this case of IRF1 responsiveness. And so the deduction we can say is here is tumor cell IRF1 expression opposes interferon 1 signaling that drives adaptive immunity and anti-tumor immunity and not dependent on the type 2 interferon response. So here we, sorry. Yes. So out of these TLRs, there are different TLRs which can play a key role. Different TLRs which can play a key role. Sorry. Yeah, the different toll-like receptors also contribute to this IRF1 response. So what we did is we used MyD88 knockout mice. We used TRIF knockout mice, and we made a double transgenic MyD88 TRIF double transgenic knockout mice, and we injected the wild type and RF1 MC38 in that. What we find that in the MyD88 and TRIF both responds to IF1 and the tumor size are also high. In that what does both TLR adapters MyD88 and TRIF work in connection to suppress IF1 tumor growth. So that suggests that the IF1 expression in the host microenvironment is required to do the clearance of the IF1 tumors. So not only the tumor specific IF1 is important, but the IF1 in the microenvironment is also important. And here the data suggests that IF1 knockout might show effect in CD8 positive T cells and NK cell maturation. That is another one. So in summary, what we can say is that IF1 promotes cytotoxic T cells and NK cell function in the tumor microenvironment. And tumor cell intrinsic expression of IF1 can contribute to T cell exhaustion by regulating the T checkpoints PD-L1. But at the same time, there can be other markers like IDO1, NOS2 trail or TMM140, which is evident from our work. Our study provides additional insight into these opposing roles of IRF1 in tumor and the tumor microenvironment. Thus, that we can now think of targeting IRF1 and how to target IRF1 in the tumor, but without affecting the tumor microenvironment. It will be very interesting. And so this is the basic finding what we have. So this is very relevant because now we are using CAR T cells, and IRF1 shows that IRF1 can regulate the immune infiltration and the T cell function. So in that case, this will be very relevant for CAR T therapy, whether the IRF1 expression can reduce the efficacy of the CAR T therapy. So that is the thing. So we publish this paper in Cell Reports. And now what we are trying to do is develop the multiplex imaging system and the RNA sequencing for these stromal cells so that we can understand the role in a better way. And thank you to all my mentors. And this is my mentors with whom I have worked. So this is Professor Stephen Dubinet from UCLA, with whom I have worked. I have worked with Professor John Mina and Dr. William Spear, Anthony Ribas. And this work also is part of Dr. Anthony Ribas is part of that. So thank you so much. I'll be happy to take questions. Thank you.
Thank you. Thank you very much, Dr. Manashpal. So now the question is open for discussion. Just quick 2 questions, exactly 2 questions, if there is anybody.
Hi, Dr. Manas. So, you know that interferon gamma is, in general, interferon signaling is very much essential for cancer immunosurveillance. So in your model, it appears that the NK cells and NKT cells are, involved. So is this the NK and T cells, they're tumor intrinsic or they're recruited from the peripheral blood?
Sorry, sir. Can you repeat it one
The
more
NK and T
yes,
cells,
yes.
are, whether the IRF1 is somehow enhancing the tumor intrinsic expansion activation of NKT cell. The peripheral blood.
So it is mostly what we have found is mostly recruitment from recruitment. So that is the only part we have done.
And in that case, how do you think those immune cells are recruited? Is there any, chemokines or something which you think is critical?
Yes, as I was showing that there are multiple chemokines which are different. And those chemokines are secreted and they are also regulated by RF1. So those chemokines actually is attracting the NK cells and T cells. So that is how this immune infiltration is affected. Once the immune infiltration is affected, then the tumor cytotoxicity is limited.
Because this...
No extension. Sorry. Don't go ahead. All the discussion.
We can discuss.
And the tea time or the lunch time. So thank you. Is there any other questions? Any pressing question? No, thank you very much. So thank you for the excellent talk. So, thank you. The next, I hand over to the
request the session chairs to kindly felicitate Dr. Paul for his talk.
Okay. Yes. The next 2 talks, please be in time, but otherwise you will be getting delayed in the lunch and the also for forthcoming decisions. So thank you very much.
Thank you.
I request Dr. B.C. Das sir and Dr. Selina, please step forward. Ladies and gentlemen, please give a big round of applause. I request the session chairs to please continue the session.
Okay. Okay. So now we will welcome Dr. Gopal Kundu. Yes, he's here. So Dr. Gopal Kundu is a Director of Research and Development at KIIT deemed to the university and holds academic position in both biotechnology and medicine in KIMS. He conducted postdoctoral research in cardiovascular diseases, inflammatory diseases, and reproductive biology and renowned institutions in the USA, including the Cleveland Clinic Foundation and NIH. And he held research position in National Center for Cell Science, Pune. He is a fellow of the National Academy of Science and the Indian Academy of Sciences, and is renowned for his work on tumor biology, cancer stem cells, angiogenesis, and cancer therapeutic. So the title of his talk is Therapeutic Targeting of Osteopontin and Associated Genes in Breast and Other Cancer. So please, Dr. Kundu.
Thank you. Good afternoon. I thanks organizer inviting me to attend this consortium. And because of lunchtime, so I'll try to brief it and try to finish within 18 to 20 minutes. So as title said, mostly I'll be talking about that some of that understanding the tumor microenvironment along with tumor immunomicroenvironment. And there will be three components. I will take 5 minutes each, and first 3-4 minutes little bit about introduction. Before I start, earlier I was part of, especially those came from outside India, I was in one of the National Research Institute located in Pune next to Mumbai, funded by Department of Biotechnology. Last 5 years I moved to one of the private university located eastern part of India. Started 28 years back with $100 equivalent to 5,000 rupees. Today that institute annual budget 25,000 crores with 40,000 students, 5,000 faculties, and 20,000 non-teaching staff. And the founder of that university, Professor Dr. Uchchata Samant. So coming to now that SDG, Sustainable Development Goals, framed by United Nations, all of you know 17 SDGs, where that healthcare, including cancer, plays very important role. And our Honorable Prime Minister also said that Viksit Bharat 2047, there is a strategic goals. And if you see these strategic goals, healthcare management and including management of cancer plays a very important role in terms of drug development, therapeutics, diagnostic, etc. In terms of cancer treatment, regular treatment, all of you know very much, but two added therapy other than neoadjuvant therapy, that one is the targeted therapy and another one that immune therapy coming majorly. And so therefore understanding tumor microenvironment, TME, is very, very important. As Professor Welch also talked very nicely, followed by other speaker, that not only tumor cells, many other stromal cells playing very important role, including immune cells, as well as other stromal cells like fibroblast. Just few months back, we published a paper in molecular cancer, and we have extensively demonstrated that how to modulate the tumor microenvironment and especially to understand the mechanism of immunotherapy-based drug resistance in breast cancer. So there, if you see that this paper is very critically explained and extensively, like there's a huge crosstalk. As you can see, the different cell types in tumor immune microenvironment, and not only that tumor cell, there are many kind of immune cells and many genes and proteins playing important role, including mast cells, neutrophils, endothelial cells, then your different type of TAM, pro-TAM and anti-TAM, as well as that other kind of cells, fibroblasts, etc., playing important role. And so TAM polarity basically indicates the prevalence of immune suppressive and tumor promoting factor within TIME. And immune tolerance within TIME also plays important role. As you can see that morning I was just asking that question, one of the questions. Now there are almost 8 different subtypes of CAF or TAF, cancer-associated fibroblast. So which one playing important role? Which subset playing important role in immune tolerance? So this is also a huge question, and many of the things can be solved only by single cell RNA-seq, not by bulk RNA-seq. Similarly, the tumor microenvironment mediated immune tolerance in breast cancer, including the protein or gene which we are working on, called osteopontin or SPP1, along with some chemokine-like protein, CXCL, they also plays important role in regulating this. So crosstalk, not only that within that stromal cells, but there is a huge crosstalk between CAF and TAM in the tumor immune microenvironment. And as you can see, many transcription factors, many pro-angiogenic molecules and genes, they are basically coordinating this. And the right side, as you can see, the protein which we work, and we have initiated some of the study, that how that osteopontin or SPP1 also plays important role in the tumor immune microenvironment. This is a busy slide you cannot read, but it is all demonstrated in the recent molecular cancer, which came that few months back. And the same review, we have also collectively written that various latest clinical trial that is going on in the multiple therapy in different subtypes of breast cancer, where you can see that here not only that targeting that cancer cells, but here you can targeting dendritic cells, targeting that CAR T cells, as well as different kind of macrophages. And these many of the trial, either they are doing it that HER2 positive or HR positive breast cancer, or many of the trial going on in TNBC, triple negative breast cancer, or metastatic breast cancer. So with their respective NCT number. So coming to breast cancer, as all of you know that there are 2 different kinds. One is a ductal, another is a lobular, and subtypes also, but country like India along with the other country, basal-like or TNBC or triple negative is more aggressive, and developing that kind of cancer is a much earlier stage as compared to luminal A and B, starting with a small little lump, then that developing primary site and then targeting to the lymph node, then metastasizing to lung, liver, brain, and bone. So one of that collaborative work we have initiated few years back and completed in collaboration with Tata Memorial Hospital and IBMG and few other institutes. The idea of that to develop that hormone resistance and hormone sensitive breast cancer patient-derived xenograft PDX model, and once you develop the PDX model from the patients, those are luminal positive breast cancer patients. Some of them, they develop resistance and some of them, they are sensitive. So basically the idea, once you develop the model, and from there by establishing primary culture and then moving towards the whole genome and exome sequencing as well as transcriptome sequencing, as well as proteomics analysis to identify the target and find out how you sensitize the resistance in this type of breast cancer. So that our team developed this PDX model first time in India,
through this program funded by Department of Biotechnology called DNCI program, Virtual National Cancer Institute program. So where we have collected the patient tissue from Tata Memorial Hospital, Mumbai, and these are the patient code number, and then we develop this tumor in this specialized mice, and the one of the patients who came to the clinic at the age of 51, and then with a little lump, and then doctor decided to give it that initial treatment of cyclophosphamide and 5-fluorouracil and adriamycin. Then patient was surviving for a couple of years. Then again, and this right side you can see this is the immunohistochemistry of that patient showing that ER and PR positive along with HN staining. Then patient again developed that liver metastasis. And this is that showing that ER PR positive in the liver mets patient. So then the doctor again changed to tamoxifen, paclitaxel, zoledronic acid, etc. along with that palliative RT. And then patient was good for a couple of years, and then again developed the lung metastasis, same patients in the year 2016-17. Then again, patient undergone the different kind of therapy, including gemcitabine, followed by letrozole, zoledronic acid, along with palliative RT, and finally that patient expired year 2022. So this patient tissue we have collected. As you can see, we established the primary culture, and also we established the patient-derived xenograft. And these PDX we have characterized their status, especially that ER/PR alpha, bimentin, Ki67, pan-cytokeratin, NCAT, etc. And we move from generation 1 to generation 2. And then this is generation 2. So they are basically maintaining the same expression profile what we have seen the patient versus generation 1. So we went on up to generation 4. And what we have done, the patient versus that different generation, we have done that differential gene expression pattern, and we find that there are many pathways, including the MAP kinase pathways and some of the other pathways. They are expressing, and their level is high when we have done this differential expression pattern. And now we are moving further, establish this primary culture, and develop this PDX up to generation 4. And this model now we are testing that by developing the sensitive model also, and how to reverse the resistance in this model along with the primary culture. Now, along with that, we are also involved in many other projects, like one of the projects collaborating with All India Institute of Medical Science in Delhi, where studying that improve efficacy of gene expression based PAM50 classifier along with epigenetic marker along with microRNA in to improve the prognostication of the breast cancer patients. Similarly, we are also working on India. We have an issue with stage 2 breast cancer survival rate. They are 66%, whereas the global stage 2 breast cancer survival about 88%. So through the spoke and hub mode, through that the Ministry of Health and collaborating with our regional cancer center, Acharya Harihar Cancer Center, we are also studying that status of these 5 signatures of these breast cancer patients, and based on that, how we can improve that overall quality of life of these women who are developing stage 2 breast cancer from 66% towards 88%. Now the second part, I just like to talk few minutes, 4-5 minutes, that the protein which we work called osteopontin, it binds with the integrins, and this protein as well as its receptor, different kind of integrins, either they express in tumor cells or immune cells, and they express very the breast cancer patient or some other cancer or cell line, you will see they are sitting in the top of the list. And then this protein has a unique RGD motif, GRGDS, as well as SBB-YGLR motif. So they interact with selective integrins and regulate cell-cell matrix interaction, angiogenesis, metastasis, etc. And we have dissected that multiple pathways and then shown that this is really important. for development of tumor growth, metastasis, etc. So what the question we ask that if this protein, being a chemokine-like protein, whether it's differentiate fibroblast to cancer-associated fibroblast. So there we have used that human normal fibroblast exposed with this chemokine-like protein and found that it is differentiating into cancer-associated fibroblast by analyzing the expression of alpha SMA, PDGF receptor beta, FSP, FAP at the protein level by confocal, Western, as well as qRT-PCR. So one of the transcription factor, twist1, is a key regulator in cancer-associated fibroblast. So we have knocked down osteopontin and comparing with the parental osteopontin in triple-negative breast cancer cells, when exposed with the normal fibroblast, we find that osteopontin knockdown cells, when exposed with the fibroblast, there is a less expression of cancer-associated fibroblast-specific genes and playing important role in transdifferentiation of fibroblasts into myofibroblasts, as well as that expression of twist and SDF1 also going up. Then we developed that preclinical animal model, both in the carcinogen-induced model in osteopontin knockout mice, along with parallelly that osteopontin knockdown MDA231 co-implanted with that fibroblast, or the parental TNBC MDA231 with fibroblast. And so we find that when we knock down osteopontin, that there is a growth of the tumor going down, and tumor volume and tumor weight. We analyze those. Because of shortage of time, I am not discussing that. But in the patient's tissue, we checked the different grades of breast cancer patient tissue, that expression of osteopontin and alpha SMA going up in the higher grades, and especially grade 3 breast cancer patients, if you see that they are showing alpha SMA and twist1 positive, and this alpha SMA twist1 positive cap, they are also co-localizing that osteopontin expression and playing very important role in the growth of progression of the tumor at the primary site, along with metastasis. So this is the proposed model. Basically, it regulates this transcription factor through some of the upstream pathway, and they control some of the microRNA like MIT21, and then deregulates and P10, and followed by controls that AKT activation. So therefore, osteopontin is one of the hotspot, and we also came with some of that PCR-based blood test for detection of breast cancer recurrence using specific variant of this osteopontin gene in collaboration with professor from University of Cincinnati, USA. Now that last 2-3 minutes, I'll just stop. We started the third component of the project where we are identifying the core transcriptional regulatory circuitry of SOX2 and OX4 activity by breast cancer stem cell. So here, basically the idea is that SOX and OX positive, that is called SOT6, positive breast cancer stem cell, how important they are in development of lung metastasis, and what are the drivers gene which are involved in regulation of this lung metastasis.
Dr. So you have 2 minutes more.
Yes. So we got this LN24175 from Professor John Messard from Memorial Sloan Kettering Cancer Center, US, and we have done that this differential expression between MDMD231 versus LN24175. Find there are many genes upregulating and downregulating, and so we made the construct with the SOT6, and basically the last slide I am showing after characterization, we sorted these MDA231 cells with a SOT6 positive, then we developed that library using 10x genomic platform, and then we sequence this snRNA and SN ATAC library on Illumina platform, and we got the multiple clusters. So we are analyzing these clusters, and then finally trying to understand that what are the drivers gene which are involved, and we are also developing the metastasis model. This project, this is unpublished, going on. So I have multiple international collaborators, many students graduated, they are mostly in US, and currently I have about 15 students, including 10 PhD students, and source of funding, Jesse Ghosh Fellowship, DST, Indo-German, DBT, BIRAC, ACRB, ICMR, etc. Some of the lab team members, other team members, and the current team members at my current laboratory at KIT University. Thank you very much.
So thank you very much, Dr. Kundu. So is there any question? Yes, go ahead.
Yeah. So since there's a relationship between obesity and breast cancer,
right.
Also adipocytes are known to secrete osteopontin. Do you see any relationship between the circulating osteopontin and the growth of your PDXs?
Yeah, this is a very good question. So as you rightly said, that women, those who are in obese, and they are more chance of developing breast cancer, and through this metabolism and all these things. So this is the project we have initiated in collaboration with our clinicians from our cancer center. And we are also going to develop that preclinical animal model with and without obesity by injecting that patient tissue from those selected patients, some of them obese versus non-obese. And once we develop that model, and then we'll be characterizing that. So right now we don't have answer.
Thank you very much. So just one other question. Yeah. Go ahead.
Gopal, you said that you have said that you have developed a kit for the breast cancer, right? Okay, and that's one of
basically that when patients undergoing neoadjuvant therapy or surgery or chemo or radiation, many cases there is a recurrence of this.
No, that's fine. My question is that that kit is based on some variant of the osteopontin.
So because of shortage of time, I could not discuss. Osteopontin has a multiple splice.
Right.
So we have selectively designed the primer.
And that's very specific. That's very specific for the breast cancer.
Correct.
And osteopontin being a molecule in the normal individual also, that doesn't detect that particular osteopontin.
Right. So osteopontin C is very much highly expressed in breast cancer. More specifically, TNBC.
Now it's overexpressed or it's also have an expression in the normal cells?
No, osteopontin C mostly expressed in that tumor. And when they are having a recurrence, we are collecting the patient's blood, and based on this RT-PCR, qRT-PCR, we are detecting their transcript level, and we are comparing with B and A. B does not express in the cancer tissue, is mostly expressed in the normal scenario, normal epithelial cells. And A, depending on the nature and type, it expresses different other cancer along with cancerous tissue and some non-cancerous.
Fine. Thank you.
Thank you.
Thank you.
Session chairs to kindly felicitate Dr. Gopal Sikundu. Ladies and gentlemen, please give a big round of applause. Thank you, Professor Kundu, for being here and presenting sharing your research.
Okay, thank you very much. So now it will be the last speaker of the session. And so we welcome Dr. Girdhari Lal from the National Center of Cell Science. So Dr. Lal is a senior scientist in the National Center for Cell Science, Pune. He received his PhD from the Indian Institute of Science, Bangalore, and joined NCCS Pune as a scientist in 2010. Dr. Lal received the prestigious Ramalingam Fellowship, Innovative Young Biotechnologist Award, and Tata Innovation Fellowship from the DBT. He also received the prestigious Swarna Jayanti Fellowship from DST, and is also an associate fellow at the Indian National Science Academy, New Delhi. His laboratory investigates chemokine receptor signaling and neuroimmune communication in inflammation and autoimmunity. So the title of his talk is Neuroimmune Communication of Serotonin Receptors in Anti-Tumor Immunity. So please, Dr. Lal.
So in the meantime, I have a quick announcement. The poster session is going on in parallel. If there is any poster presenter, the student presenter whose poster is scheduled to be presented today, if he or she is sitting in the hall, please you are requested to reach to your poster.
Thank you, Chair, for introducing me, and also let me thank Dr. Desh Prakash for inviting me to share some of the information that I'm doing in the lab. And my lab work on neuroimmune communication, trying to understand how neuroimmune communication modulates the immune system, especially in cancer and also autoimmunity. What I'm going to do today is this type of slides you saw that in tumor is not the one cell, what we see in the petri dish, it's combination of the cells and combination of lot of cells in the body of different origin as well, and how they talk to each other in the tumor microenvironment and then contribute in the progression of the tumor, that's challenging. So that means heterogeneity and the cellular composition dictates what's going to be the cancer growth, and that also dictates how your immunotherapy is going to guide you. If I quickly take you in terms of, let's say, biological system which maintains homeostasis, there are three important networks or systems. For example, immune system or nervous system or endocrine system, all of them have to work in synchronized way. Let's say, for example, if I develop a immunotherapy for cancer and the best one, which mounts very strong immune response, probably that also going to induce more endocrine system disabled or disbalanced the nervous system, and that's what we call it as toxicity in the drug. That means if I have to achieve the homeostasis, you need to make balance between those three organs in a way that you control the disease or control the tumor growth so as not to kill the patient as well. Now, on the same logic, you see that when you think that some of the drugs is going to work, some even placebo works on some patient. Now, question is placebo works on some patient, we know that, but the question is how, what are the mediators? That means the patient is thinking something, developing some neurotransmitters in the body, which might be triggering some component or immune systems, which might be operating, and that's how probably therapy works much better way in those patients. That's the logic was the initiation of the project. And then obviously the one of the students joined and then asked him, okay, let's try out something good neurotransmitter, which makes people happy and see that how it works. So the student started experiment. And then he said serotonin is one of the happy hormone, and let's increase the serotonin level in the animal model and then see what happened. So he increased the serotonin level by injecting either serotonin or the drug which increases serotonin level. So as the tumor also grows much bigger. So then it's frustration. And then it came back, oh, that instead of regression, you have more tumor growth. Then I said, repeat the experiment, we'll see. And they repeated answer remains same. Then I said, drop the project, we are thinking wrong. All right, then we went back to chalkboard and then say that if you look at the neurons carefully or the cells which produces this neurotransmitter, they also has got the receptors which are inflammatory molecules or molecule response for the inflammation. Now, if the neurons has molecules for these inflammatory molecules and the immune cells has the molecule which neurotransmitters which is expressed by them, how they are talking to each other. I gave the example of serotonin which failed, but then we went back and looked at that why serotonin increasing is failing. Then you find that there are 15 different types of receptor expressed across the different cell type. Are we asking the right question to begin with, that which receptor require where and what they do? All right, so I'm not going to explain all this. What I wanted to point out that there are cells in the peripheral system in our body, like immunopharmacology cells, which produce a lot of serotonin, and that's in fact 90% of your serotonin peripheral cells. The system comes from these cells, which is endocrine cells. Now, the next question we were still wondering about that why we failed in serotonin. Then one day we were just looking at, okay, let's look at all this information of this 15 receptor and colon cancer. And what we find was a little more surprising. When we segregate the patient based on the serotonin receptor high versus low and ask the question, who survives better to express any one of these receptors among all these 15 receptors? And when zoom on to one of these receptors called STR2B, the surprise thing came, this patient who are expressing low expressor, they survive much better than the patient who has the expression of STR2B in high level, they actually survive less. Then question is, are these all these patients are responding, going to respond it if I trigger only this receptor rather than a pan-serotonin receptor and then see what happens. I just noted that we have analyzed all of them. None of them said difference. Obviously, go back to patient, take the tissue and look for the STR2B expression, and you will find that there are a lot of STR2B expression in patient with a different rate and different location, either in the tumor or in the region. And then you went back again in the patient to see that how does this work? Can we learn something from what is known? And when you look at that, the patient which you see on left and right, there are a lot of differential expression gene happen just by looking at if the one of these receptor is up in patient versus in the lower, and the survival rate which I already discussed with you. Now question is, how does this receptor is talking to immune cell? I'm not going to see the data who all the immune cells express these molecules just because the chairperson is going to kick me out very soon. So what I want to point out here is that if you look at these graph, the color coding, the heat map, there are a lot of important genes which actually immune molecule, mediated molecule, their expression pattern changes moment the serotonin receptor, one of the receptor expression pattern change among the patient. And also a lot of effector molecules and biological pathway also alters based on the expression of these neurotransmitter signaling and other molecules, which is very important, immunologically very important. Always you can keep on doing this experiment and see all the parameters what is required for cancer, EMP, angiogenesis, or the signaling pathways. They all actually sense differently the moment this receptor expression pattern changes. And also the immune profiling, if you look at infiltration, what kind of immune infiltration profile happen when the low and high, why you see the output in the low expressing patient surviving better. The red channel, what you see in the bottom STR2B is much more. So as for the NK cell, so CD8 T cell, NK cell infiltration is much more dominating when there is a low expression of STR2B. And if you look at those patients which is high CTL activity among them, you find them, they actually show a complete differential T cell response. Now, all this in human. Then we thought, okay, let's do some experiment in mouse to prove what we are doing, because we can't do the experiment in human. So simple experiment, again convince him to do it, not this time increasing serotonin, just agonize or antagonize this receptor. These receptors are available pharmacologically, neurobiologically, people are using it. So what he did, he used agonist for this receptor or antagonist. Look at the green line. The moment you agonize only this receptor, tumor just keep going up. And antagonize this, tumor has a hard time to grow. Now, I showed you in the tumor, in the human patient, there are a lot of immunologically important molecules. Then we were interested, okay, why only this, why not other? Let's try out some of those other serotonin receptor, and you have a list of those. The moment you try to interfere with others, they do not have impact on tumor growth. Whereas the moment you antagonize STR2B, which is green line there, you see either one or two or multiple receptor antagonists be tried, it has hard time to grow. All right, fine. Now, next question is, how does this work? Because what data I showed you is the colon cancer. Does it work in metastasis? Does it work in other cancer, melanoma or others? We tried and it works. For example, what I'm showing is the breast cancer thing. Here we are looking at not only tumor growth in the breast cancer, it reduces, but also looking at does it inhibit the metastasis of the tumor? The answer is yes, it does inhibit the metastasis, and also the cellular infiltrations are altered. Now, the next question was, does immune cell is playing any role here? So the simple experiment was done. You take NRG mice, which do not have T cell, CD8 T cell or NK cell, and inject the tumor and also antagonize the receptor in those mice and see if this effect carry on. If the mice does not have functional immune cell, the activity of STR2B is dropped. It does not work. And also, if you try actually agonizing or antagonizing the differently, just by transferring the cells, actually you control the disease, which is shown there. The tumor cells, if the cells has seen the tumor cell, the antagonist,
the immune cells from there, it's self-control, you don't need agonist itself. That means it modulates immune cell in such a way that it controls gives the anti-tumor effect. Now, biology, what you see in petri dish, the one cell is different than what you see in the whole complex organism. So obviously technology has to change. And then that's where we used multicolor flow cytometry, where we can look at all these different immune cells and the expression of those molecules. With 28 we are trying now more to see that what are goes on. And that's what done by Surjit and Rashmi. What I'm showing you to just focus on dendritic cells and look at what happened to dendritic cells with different markers. Likewise, we have looked at other, I'm not going to show all those data, just want to point out, looking at just one cell type versus looking at a whole cell type in one go gives you totally different perspective of the disease. For example, if you look at dendritic cells, there are a variety of clusters formed and having the different phenotype just by altering one of these antagonists. Now, question is, who works where and what is the role they play? I'm not going to discuss that part here, the lack of time, but we know some information where and how they work. Let's focus on the T cell, which is more important as a topic today. Now, the question is, who are the T cell playing important role? The first question was, is it T cell? Because I showed you human as well as mouse that CD8 T cell, NK cell was up. So take away CD8 T cell by depleting, giving the anti-CD8 T cell antibody. The green line, what you see, all the protective effect of STR2B antagonist is gone. That means it is actually contributing in the antagonizing this receptor. Now, if you take, that's one of the experiments where you deplete it. Now, what about if I reconstitute the CD8 T cells from a mice which is exposed to STR2B and the same tumor? And if you do that, the red line, what you see, that the just T cell itself able to protect the tumor growth. Although there are other cells involved, that the protection is not efficient, as you see in the previous slides. Now, if this is the case, is there any responsibility of antigenicity? Because tumor is heterogeneous, there are some contribution here. We don't know the antigen. So we thought that if you have two different tumors, let's say I have a breast tumor going in one flank, melanoma tumor in another flank, and then ask the question: if I inject the tumor cells, which the T cells are immune cell which exposed to only one of these, and see if it can protect both of them. Answer is, it cannot protect the other subtype. That means there is something antigenicity coming through the interaction of the receptor antagonist and also the immune system. Now, question is, how, so then you can go ahead and ask question that does it really antigen specific? You can use OY specific, or there are other transgenic knockout mice to prove that yes, it is actually antigen specific. So let's ignore that data and come to the final conclusion. Why we want to do this? We already have immunotherapy, we have a chemotherapy. What is new? We are going to combine it. Like I mentioned, the best immunotherapy also induces toxicity on neuronal axis as well as endocrine axis. So can we cut down the dose of immunotherapy in such a way that it does not induce toxicity? In fact, it does not even work. And then you combine these neuromodulators in low level that it does not work in themselves, and what we put together, does it work? That's the question was asked. So the dose what is used here, either immunotherapy or STR2B, independently they don't work. But if you combine them, you see the violet light in the bottom. They are irrespective of the dose what you are using, the checkpoint inhibitor you are using. They actually functionally work. Now you can ask the same question in chemotherapy. Can we bring down the toxicity? I'm done. That's my last slide. Thank you. If you look at the chemotherapy, either 5-fluorouracil, oxyplatin, or the other drugs, you find that the moment you combine them, you can reduce your dose so low that they don't work, but then you combine them, they all work. That means the parameter what you are checking actually modulating in a way that all these three systems should, and combining the immunomodulator as well as neurotransmitters, it boosts in a way that gives better immunotherapy, the function of better immunotherapy. What I showed to you so far, that there is a cell, there is a tumor, there is immune cells, different types of immune cells, they talk to each other, and when there is an expression or alteration of this neuromodulator, the function of these cells alter in such a way that it actually pushes you to give you better anti-tumor immunity. And I'll close here acknowledging the people behind this, our clinical collaborators and different hospitals, DY Patil, as well as FMC, and the present lab member. What I showed to you, mostly major work done by these two guys. They finished their thesis also. They just actually waiting for the defense and also the funding agency and the core facility what we run used in the National Center for Cell Science. Thank you very much. I'll be happy to take question if time permits.
Okay, thank you very much, Dr. Alan. So just one question, if there is any. Yes, go ahead. There is.
Yeah, hello, sir, and excellent presentation, sir. So I wanted to know, like, just for like when the tumors is actually growing, like like the nerve interaction is also there. So I mean, the receptors are present in both the immune cells and the cancer cells together, and having a local effect when the tumors are progressing, or it is having a distant effect, like as the neurotransmitter can proceed through the bloodstream.
Excellent question, and we have tested. The first question was because we could not show here the time that does serotonin level increases with tumor progression? That's one question. Does receptor expression changes with tumor progression?
Yes.
Does machinery which synthesize serotonin or the receptor doublet rate, does it change? Answer is yes. As the tumor progresses, the receptor goes on. From let's say stage 1, stage 2 to stage 3, you will find more of this receptor, and you can do in animal model we tested, and also in the different grade of the cancer in human patient. So it does actually goes up. So that's how probably it provides you the antagonist provides the liver factors.
Okay. Thank you.
Thank you very much.
So thank you very much, all the 4 speakers. We thank very much, and all the good talk was presented. And now we come to the scientific sessions before the lunch. Now we break for the lunch, and before that, I think
before that I request the session chairs to please felicitate Dr. Bidhari Lal. Please accept our token of gratitude for being here and presenting in the presentation.
This is just an announcement for everybody that everybody can have their lunch within half an hour and reassemble at 3, because all the online speakers are waiting at their respective place. Please, in half an hour. Yeah.
I also request Dr. Hidesh Prakash to please felicitate the session chairs, Dr. Celine Gangora and Professor B.C. Das, sir. Please give a big round of applause. Please join me in thanking the session chairs for conducting the session. Thank you very much, Dr. Celine Gangora. Celine. I also request Dr. Hidesh Prakash to felicitate Professor B.C. Das, sir. Kindly accept this as our token of gratitude. As announced, now we are breaking for the lunch break. As our sessions are already delayed, I request everyone for a short lunch break, and we will resume the session in half an hour in the same venue. Thank you.
I request everyone to settle down quickly. We are about to start.
All of you, please settle down.
Yeah. Can you just focus here? Here. Hello. Yeah. Hey, John.
Hi.
Hi,
Hi,
it's
everybody.
me. How are you?
Very good, thank you.
Yeah. So, welcome to this session, and I would connect you to the next session speaker, who is Sergey, again my friend from Berlin. So, over to you, Sergey, to start. Yeah, please.
Hi, John. This is Sergey. So I will introduce you. Also, I want to make a note to speakers that we should be staying on time. Time, unfortunately, is very, very strict. On the previous session, we had to book some people with yellow cards, So hopefully not this time. So the next speaker is, the session is called Emerging Cancer Immunotherapy. Next speaker is John Silke from VHI, Melbourne. I just briefly read his resume. He had a law degree from King's College, biochemistry degree from Churchill College, PhD from Zurich with Walter Schaffner, did postdoc with David Waugh at VHI, and right now he is working on, he is famous in the cell death field. This is where I met him. And his lab at La Trobe University continues, and now at VHI continues to explore the function of proteins, which are called inhibitors of apoptosis in transcriptional and programmed cell death pathway, how they regulate extrinsic apoptosis and necroptosis in both cancer and inflammation. So John has a nice sense of humor, and this is reflected in the title of his talk, Watch Your Mouse, Advances in Detection and Treatment of Oral Cancer. John, please.
Thank you, Sergey. So in the interest of time, I'll get straight into it. Disclosures, while I'm going to talk about results from the OptaScan, we don't receive any funding from them. So this is not going to be an immunotherapy talk, I'm sorry, but still very pertinent to curing cancer, treating cancer efficaciously. So we're in the lab principally interested in head and neck cancers. That pretty easy to understand where they originate from, but we're specifically interested in oral squamous cell carcinomas, OSCC. And for a long time, it's been considered to be an environmental carcinoma. If you smoke too much, or in Southeast Asia, betel nut use, alcohol use, exposure to HPV, and of course, smoking and drinking. So it's often been associated with older men who don't live very healthy lives. However, across the world, and in Australia too, and this is an Australian study here, there's been this very surprising and not understood change in the demographics. So traditionally, although it's been viewed as a disease of older males, there's an alarming increase amongst younger people. And I hope you can see my pointer here. So specifically in under 45 years, and what you can see here is the incidence of smoking and drinking sort of, the health messages get through. This is kind of staying steady, the incidence of OSCC in this aging group. But it's this younger group, and particularly females in this bottom line here, where is starting to rise quite dramatically in quite young people, under 20s, have been diagnosed with oral cancer, and for still not understood reasons. So my title reference treatments in 2023 to 20, and just before, there was considerable excitement about the use of SMAC mimetics. These are drugs that antagonize IAPs, which you just heard from Sergei has been a particular interest in my lab. And what you can see here is when these SMAC mimetics were combined with chemoradiotherapy in this phase 2 trial, there were some really stunning results. You can see here that it didn't even reach the 50% progression-free survival when the patients were treated with SMAC mimetics over 5+ years. So, and this is on the bottom line, you can see just the placebo and chemoradiotherapy. Unfortunately, this then led to a very large phase 3 trial. There was a large multi-center phase 2 trial, but unfortunately, this phase 3 trial just was published in 2024, June 2024, where Merck, the company running it, announced the discontinuation of the phase 3. And this was on the basis that the trial would be unlikely to meet its primary objective of prolonging event-free survival. So we, in my lab, find it hard to believe that this result in a phase 2 clinical trial, multi-centered, wasn't actually detecting a real signal. And what we believe is that what's necessary is to understand better the population that are at risk and that can benefit from this combined treatment. And that's one of the things that we're doing. And one thing that's really worthwhile pointing out here is that very few of these patients were actually oral squamous cell carcinoma patients. So this was the best hope for treatment for a new drug. That was the best hope in the last 30 years. It's not good as many people had hoped. It wasn't as good as the hype. But the fact is that the prognosis for stage papillomavirus negative oropharyngeal cancers is very dire. You can see stage 4 here, that the overall survival plummets very rapidly. But if you can detect oral cancers early and remove them surgically and some chemotherapy a little, then the survival increases dramatically. And there's really a very simple message here, is that late diagnosis leads to a very average survival rate, and early diagnosis leads to a much improved survival rate. And it also dramatically affects patients and the impact that therapy has on them. If people have half their face removed during a late diagnosis surgery, whereas an early diagnosis surgery could be really minimal and have minimal impact on speech and eating and social and psychological parameters. But the problem is that early detection is not trivial, it's not quick, and it's definitely not pain-free. So the traditional pathway is that you get a surgical biopsy for a lesion that the clinician is unsure what it might be. Then that's followed with histology, scoring, and diagnosis. And that really, even in an excellent health system, can take weeks or months. And don't just believe me. So you can hear from a patient in 2023 how it takes a long time and there's a lack of positiveness about what, whether he's even had an oral cancer. So we want to change that. And we are really interested in this OptiScan, which is a confocal scanned single fiber endo microscope. And that is a mouthful, and the pun is intended. But what it allows us to do, and particularly Lorraine O'Reilly, who leads this research, Dr. Lorraine O'Reilly, is to get single cell resolution in a painless, real-time way. And you can see the parameters here of the microscope, the technical parameters. And you can see how tiny this probe is to enable this. And, I'm going to show you what this OptiScan can do. But having a microscope on its own and be able to, in a single cell resolution, go around the mouth is not necessarily going to aid the clinician in diagnosing cancer at an early stage. And so we're particularly excited by this dye that was published by the group in Memorial Sloan Kettering, which is basically the anti-cancer drug Alacrity fixed to a fluorophore. And what that does is that in normal cells where PARP is not upregulated, there's a very low signal to very low to no signal. But when it is upregulated, and as we know that frequently happens in cancer, then we get a strong nuclear signal. We also use the cell dye acroflavin, again another safe dye, that gives us some additional context. But we're really hoping and relying a lot on the ability of the PARP inhibitor FL to specifically mark cancer cells. And the Sloan Kettering group had shown in patient samples that in oropharyngeal and esophageal epithelial cancers that the PARP FL was able to stain fresh tissue. And you can see that in the fluorescent images down there at the bottom. So, to cut to the main idea here is that could we develop a virtual biopsy to facilitate early detection? And this would be particularly useful for high-risk patients who might need to be screened frequently and followed up frequently. And I just want to again stress how useful this confocal microscope is. I've got a picture here of the little case that we carry it around in. You've seen the size of the probe, and I've got my rucksack and a teacup there to show the size. And what this means is that for a machine that is very transportable, and particularly in Australia, could allow equitable health outcomes where we could screen people at their point of residence for older people who actually have the increased risk. So something very portable, easy to use. So the key questions then that need to be addressed are safety. Is this going to be safe? Ease of use, but particularly the sensitivity and specificity. Could it detect the difference between benign and malignant lesions? And accuracy. How many times does it get it right or false positives and false negatives? So from the ease of use perspective, we've already demonstrated this with our collaborators, Tammy Yap. This is, you can do this virtual biopsy. This is a picture of Tammy with a patient here with scanning with the exact machine that we use later in our experiments. It's chair side, no anesthesia is required. It's painless, there's no surgery. It's instant and visual, and you can follow the lesion. You can do a quantitative analysis. You can see here with PARP-FL staining of the oral squamous cell carcinoma that you've got this positive nuclear stain, but in the healthy tissue alongside no stain. So definitely proven easy to use in patients. The problem is, though, to demonstrate the accuracy and specificity. So this study that was published in Frontiers in Oncology, you can see that the numbers of low grade, high grade, and frank carcinomas is really very small. And again, I want to stress that what clinicians going to be really interested in is this low grade dysplasia, whether this is showing any malignant tendencies, so that they could remove it before it becomes a problem. So how are we going to address this? Well, we're going to use mouse models. And we're very lucky that there is a really gold standard mouse model where they have the carcinogen 4-NQO in the drinking water. And this has been exceptionally well characterized, both phenotypically at the cellular level, histologically, and also genetically. And what I've shown in this slide is really a genetic analysis showing that the same genes that are mutated in oral squamous cell carcinoma in patients, this is a Nature paper on the TCGA study, FAT1, TB3, caspase-8, NOTCH1, as the same genes are mutated in the mouse model. Together with our oral clinician, Antonio Celentano, we've used this model to show that exactly that same clinical development that you expect from an oral lesion, from that initial stage of inflammation to this mild dysplasia, more severe dysplasia, the carcinoma, and then the invasive carcinoma. These are really exactly what Antonio would see with his patients. And we see exactly the same thing in the mice. So it's a good model for the human disease. So the protocol is superbly simple. You can see here that basically and it's actually more difficult in mice because, of course, you do have to anesthetize mice, whereas you heard with patients that's not necessary. But we anesthetize them, apply the dye, wash, and you can see with a little cotton bud there, and then image with the confocal microscope Doppler scan. And again, you can see the relative size of that. For mouse's mouth, it's quite big, but for a human mouth, that would be next to nothing. And then we look at the left cheek, the dorsal, the top of the tongue, the right cheek, and the underneath side of the tongue. And we're staining with PAR-PFL, and then we wash that off, and then we stain with acroflavin, and then we do the H&E. So what you can see here is that these have the dorsal part of the tongue has these papillae. We recognize them on our own tongue, those kind of little bumpy bits, and they've got some autofluorescence. On the underside of the tongue, with PAR-PFL, we've got just this general shadowy stain, and with acroflavin too. And then in the cheeks, with PAR-PFL, we've got no stain, but with acroflavin, which is going to stain all nuclei, we've got this very ordered pattern of nuclei. So, how specific is it? We want to know whether this technique is going to detect ulcerations and benign lesions. And what we can see is with an acroflavin stain or the PAR-PFL stain, we see that, yes, with the acroflavin, we see some differences and no real staining with the PAR-PFL. And that really corresponds to the H&E. And the same with these keratosis, there's leukoplakia. We can see these small lesions, but really not staining in any significant way with the PAR-PFL. And the acroflavin gives an indication of the structure, the order of the cells. But does it pick up actual squamous papillomas and carcinomas, these berry-like carcinomas? Well, the answer is yes. And again, you can see here with either the acroflavine stain or the PAR-PFL stain, we really start to see clear boundaries with the PAR-PFL. And again, I would suggest these are the ones that the lesions that are particularly interesting to the clinician. When a clinician sees a frank thing coming off the tongue like that, they're far more likely to be frank carcinomas. But to be able to detect something that, as you can see, is extremely small, that a clinician could not determine whether it was potentially malignant, but to be able to say, yes, that is malignant through the use of the stain would be invaluable. We'll need to hurry up. So some specificity is really indicated here. I think what's really exciting to us is how small the tumor could be that we can detect. And you can see here this beautiful image where this tumor is less than 1 millimeter in size, but we can really pick out that this tumor and the boundaries around it and know that it's really malignant. We can correlate that and have correlated that with pathology. And again, you can see that these minute lesions can be quickly identified with the PAR-PFL, and that is backed up with the pathology. So the sensitivity is really quite stunning. We can, I've only got 4 or 5 slides, and I will go through them rapidly. What we can do here is we can also, amazing part of this imaging technique is, of course, we don't have to sacrifice the mice. We can image them as many times as we like. And so at week 16, Lorraine and her colleagues can see that we've got a very small lesion that looks like it might go bad. But then you can track that over week 17, week 18, week 9, and then we can take the histology and show, well, yes, it actually did develop into a frank carcinoma. And again, this PAR-PFL staining is really quite diagnostic. And of course, it is a confocal microscope, so we can get a 3D image of the tumors. And this is just going to show you very quickly the sort of 3D nature. And that's, again, going to be particularly interesting to the clinician to know how deep the carcinoma is. What, again, is fantastic about this method is that we really, as already indicated, can follow the development of carcinoma, but really this now allows us to test new therapies like SMAC-mimetics and see whether they are actually impacting on the tumor without sacrificing the animals. So this is going to be a much more useful experimental tool and not just a clinical diagnostic tool. So naturally, having lots of images, we want to use AI, and that we've done that together with Rishi and Lachlan. And this is, again, the advantage of the mouse model, that we can generate thousands of images, which would be so much more difficult in patients. And then we use a deep learning algorithm and get it to predict no dysplasia, low grade or high grade. And we've already published a study using acroflavine and fluorescein as dyes, and this suggests that it could be quite successfully used, and that these CNNs could provide accurate and rapid real-time diagnostic triage. And now we are actually trying to complete the study using PAR-PFL, which we believe is going to be more impressive. So the message of my talk really is we think that you can watch your mouth, and that OptiScan imaging combined with fluorescent dyes is quick, cheap, simple to detect probably malignant lesions. And specifically, PAR-PFL is very powerful, but when combined with acroflavine, which gives a structure, this provides an extra level of information that will be useful to the clinician. Of course, we still need to analyze a few hundred more tumors and really get that AI image diagnostic going, but the signs are very, very good to make a real impact for oral cancer patients. And so it just remains to thank you for your attention. Sorry, I went a minute over time, and to thank the people that contributed to the story, and particularly who I mentioned as I was going through, but particularly our consumer advocates. You heard from Alex early on, and also our funding, and it's a lifeline with that, which we couldn't do this research. So thank you very much for your attention.
Okay, John, thank you very much for very interesting talk and also for staying on time. So we have time for several questions. If I may start with a very simple question. How much this portable machine costs now at market price?
At the market price is about $200,000. So it would be feasible for some Australian dentists, but we rather envisage that it will be at some regional health center, and then could be sort of, as I said, it's portable and easy to carry around. So certainly within the budget of an average medium-sized health center, I think.
Questions, please.
So by any chance in the mice studies, have you done any fine needle aspiration and gone for a genomic correlation?
We have not yet done that, but that's certainly something that we are combining this with SMAC mimetic therapies, because we believe that there will be a signature for SMAC mimetic response. And so, yeah, exactly. So that, and then we will combine that with the sort of response to the therapy. I think that the genetics of the 4NQO model are really well established, and we couldn't add very much there. But you're right, maybe there would be some tumors that are not being detected with PARP-EFL, and they might have a different genetic signature. But I have to say, we've not really noticed any of those, and we've done quite a significant number by now.
More questions?
Yes, please. Thank you, Dr. John Silke, for this wonderful session which you gave. My concern is this is the first AI-based diagnostic tool which is being discussed for cancer detection in this conference so far. And I really appreciate it. And I do understand that you must have got it patented in US, or you must have filed for a patent in US. Have you ever tried to patent in India and get the technology available in India for its use?
We haven't, and I'm not sure that we've even applied for a patent in the US. I mean, we're not especially driven by these sort of commercial incentives. And there may be some complications around that anyway. So we're really about showing that it could be done, and certainly trying to extend it into patients, but we're not rushing to the patent office, I can tell you now. And I guess this counts as some disclosure, so I've already messed up my chances there.
I would request you to go for one.
Okay.
Thank you very much for your question.
One last question.
Well, yeah, Sergey. Oh, sorry, John. This is not a question. This is a kind of greeting to you. Good to see you here online. I wish you could come offline. Sometime, you know, we will invite you as an invited speaker for establishing the collaboration. CIP1 and 2 knockout mice. Yeah,
and come with this machine, please.
Yeah, sure.
Yeah, I can carry it in my suitcase, that's for sure. Yes, and I'm ashamed that I could not be there this time. It was an unfortunate time, but I'm fingers crossed to the next time. Thank you very much.
So I was told that we have one victim already of the last session. Yes. So somebody who was supposed to speak, he was available 1 hour earlier, but now he's not available. So we have less speakers, which is good news. And so my pleasure is to introduce. Huh? I know. Yeah. To introduce next speaker, who is Lucas Flats. Yes. And
excuse me. I have a short announcement and then we can continue. So here is a short announcement that all the registered participant, guest, invited speaker will join us for gala dinner at Golf Course from 8 p.m. onwards. Thank you.
okay, so the next speaker is Lucas Flats from Tübingen. So Lucas is clinician, professor of dermatology. He studied in University of Bern, completed his postdoctoral training with Rolf Zinkernagel and Hans Hengartner in Zurich, then worked at NIH with Gary Nabel. And he is now, as I said, he is the head of derma-oncology section at University of Tübingen. So he's working, as his title suggests, on mechanisms of immune checkpoint blockade. And the title is Mechanism of Immune Checkpoint Blockade Triggered Autoimmune Responses. Please, Lucas. "20 minutes, if possible."
Thank you so much for the kind introduction and for having me here. So I'm like a T cell. If you ever tell me move to the stage now, I act. So I try to give my best. And I also would like to let you know that I'm a kind of a clinician scientist. You see me on the left-hand side working in a BSL-4 lab with Lassa virus in Hamburg. And I actually learned virology, immunology taught by viruses. And by training, I'm a dermatologist heading a dermato-oncology unit. So I would like to dive into you what we can learn from toxicities, from side effects, and why they are good. And to understand that first, we need to go back when there was the advent of checkpoint inhibitors. And what you can see here is the 10 years overall survival data from melanoma patients who were stage 4. So before we had checkpoint inhibitors or targeted therapy, these patients passed away within 12 months. And look at this data. If they have PD-1 mono or anti-PD-1, anti-CTLA-4, they have 50% of the patients survive 10 years. This is incredible. And this comes to a price because checkpoint inhibitors, all of us have these checkpoints because we need them. When we get a viral infection, we need to shut off the immune response. And this is what checkpoints do. If you block them, you may have toxicity all over your body, and this may be life-threatening. For example, if you have a myocarditis, immune-related. And together with my team, I'm tackling the question, what antigens are recognized in the tumor by tumor-infiltrating lymphocytes? And you could even extend that. I'm also interested in, we know that TLS are important, or what are antibodies seeing in the tumor? And I think this is a question we are not addressing enough in detail. But I would like to convince you why this is very important if we want to develop next generation treatments for cancer. And to better understand that, we maybe want to first think about what kind of antigens could be seen in the tumor. On the one hand side, and the community is strongly believing in that, are tumor-specific antigens. And if we have HPV, for example, E6, E7 antigen, that can be seen, but also neoantigens can be seen, KRAS mutation or a melanoma BRAF mutation. However, I personally am a strong believer And basically, I learn from my patients. I observe in my patients. And I would like to convince you that tumor-associated antigens, lineage antigens, these are the antigens we should go for. Example for lineage antigens is also HER2, for example, which is a shared antigen. Or the CD19 for B-cell leukemias or B-cell lymphomas. And if we think about the well-known and well-studied tumor-associated antigen or lineage antigen, we can think about melanocyte differentiation antigens, because this is one of the most studied T-cell antigens in human cancer. And just in all of us, as we sit here, our melanocytes have these proteins here in action, tyrosinase, TRP2, MART1, GP100, and all these names. And they are there to produce the melanin. And if they're targeted by our immune system, then you will have vitiligo. I know melanoma is not so frequent in India, but vitiligo definitely is as frequent as it is in our countries. And so what is going on in these patients is that the T cells attack the melanocytes. And what you see on the right-hand side, if you have a melanoma patient, and this melanoma patient shows vitiligo, then this is very good, because that means these T cells, they're not only recognizing the melanoma, they're also recognizing the normal melanocytes, and in the melanoma, they kill the tumor cells. And this is basically the most important toxicity for melanoma patients. It's of course not dangerous. However, it's associated with a very good overall survival. Of note, if you give the same treatment, the same anti-PD-1, so nivolumab or pembrolizumab to a lung cancer patient, this patient will not show up with the vitiligo. Now, I would like to conclude this first small part that melanocytes and melanoma cells can produce the same differentiation antigens, and therefore that may result in vitiligo and in anti-tumor response. But could we now take this further? Because I know in India it's, for example, oral squamous cell carcinoma, or also what is also frequent is what you see here on the slide. It's the non-small cell lung cancer. So could we now also use this observation to decipher new antigens which we don't know so far? And we recently published a paper where we introduced a technique called DITAS, Discovery of Tumor-Associated Self-Antigens. And we basically take the tumor to tissue similarity to find out what kind of antigens may be present. So you can check the RNA expression of healthy tissue, which is the closest relative to the cancer. So in lung cancer, that would be lung tissue. And then you can predict what kind of antigens may be specific lineage antigens or differentiation antigens in these cells. Then we take overlapping peptide pools, do T cell stimulations, and check in our patients who are undergoing treatment with checkpoint blockade to see if they have these kind of cells, these kinds of immune cells recognizing these antigens present. And now I will just show you how we discovered the new group of keratinocyte differentiation antigens in non-small cell lung cancer patients, but also in cutaneous squamous cell patients. And I'm pretty sure that also in the oral squamous cell carcinoma, you would probably find as a target antigen keratin differentiation antigens. And what did bring me to that is the observation that if you treat the non-small cell lung cancer patient with checkpoint blockade, they do not show up with vitiligo, but they show up with kinds of similar diseases to psoriasis, so psoriasiform, or maculopapular rash, or lichenoid eruptions, or bullous pemphigoid eruptions. Some of them, like bullous pemphigoid, can also be a paraneoplastic syndrome. And here we then established a prospective patient cohort in order to study this. And you can see here several CT scans from 6 different patients. And what all of them have in common, they have either lung cancer or metastasis. You see at the bottom right, liver metastasis, and all of them responded well, and all of them had skin toxicity. On top left, it's psoriasiform. Below that, it's a nummular eczema-like, etc. So how can we now find out what's going on in these patients? So the first simple thing, what you can do is you just take biopsies. On the right-hand side, you can see the lung cancer stained with immunohistochemistry for CD3. And you can see indeed that the tumor and the peritumoral stroma is full of T cells. If you now check on the left-hand side, the skin, where you see this skin lesion, there you can see a very similar picture. It's full of T cell infiltrate. Very similar T cells, they're there. And what we did next is we hypothesized with the DITAS approach I told you, what kind of antigens may be shared between the skin and the lung cancer. And we called it keratinocyte differentiation antigens. And as the name implicates, you can see several keratins in there. And we then did T cell stimulations. So we took from these patients the blood, had the overlapping peptide pools, stimulated the T cells, and sorted the interferon gamma secreting and TNF alpha secreting CD8 T cells. So they recognize these antigens. And then we did a beta chain sequencing of the T cell receptor. And then we also did a beta chain sequencing of all the T cell receptors present in the skin and all the T cell receptors present in the lung cancer. And if they are overlapping, they're showing up in the middle. So you can always see on the y-axis it's skin, so clonotypes only in the skin. On the x-axis it's clonotype in the lung tumor, and in the middle these are there both. And what you can see on the left-hand side with the patient, there is keratin 6 specific T cells or desmocolin 3 specific T cells here or here. The CD8 T cells, they are present not only in the lung cancer, but also in the skin, causing toxicity. If we go here to a second patient, we can see this MUSPIN specific CD8 T cell clone is present in the lung cancer and in the skin. Here, for example, we have a CD4 positive interferon gamma positive, so a Th1 T cell response, which also is invading the tumor. However, you can also find some T cell specificities like the desmocolin 3 or the LL37 or the keratin 14 here on that side, which were only present in the skin, likely causing skin toxicity, but not causing tumor regression. What is also very interesting to see in our cohort is that patients who showed up with this kind of skin toxicity, and this is the blue line here, these patients had a significantly better overall survival than the patients who did not show any skin toxicity. Moreover, if we stimulated 36 different non-small cell lung cancer patients with the peptide pools for all these different keratinocyte differentiation antigens, we saw that many patients had such self-reactive T cells present in their blood. What I also want to say, I think antibodies are often overlooked in cancer. The reason for that is that we are only looking in stage 4 melanoma or stage or non-operable other tumors. That means they already have a very high tumor burden. However, we think that overlooked and may be important. So we found in another publication we showed a couple of years ago together with a resident, I did that in the dermatology, and we found that anti-BP180 antibodies are also associated with skin immune-related adverse events and survival. And I would like to spend a bit more time or want to go a bit more into detail, because this may be particularly of interest for you here also in India, is what characterizes squamous cell carcinoma. Because unlike melanoma, this is a rather huge group of tumors which share several similarities. So a squamous cell carcinoma is a type of cancer that originates in the squamous cells. And keratin is a key structural protein produced by squamous cells. And forms of squamous cell carcinoma include lung squamous cell carcinoma, cutaneous squamous cell carcinoma, oral squamous cell carcinoma, esophageal. I could continue this list with other organs. So the first question to answer the question if there are keratinocyte differentiation antigens present in these kind of tumors is let's have a look into the tumors and see, and they are full of T cells. You see this immunohistochemistry of 3 different squamous cell carcinomas. What we did then is we took the tumors, we did immunoprecipitation with an antibody that binds to the MHC class 1 that was together with Hans-Georg Ramenz's team. And you can see, indeed, if we do the pull down followed by a mass spec, we see that unlike in the far left, you see a melanoma as a negative control. So in a melanoma, there's basically no keratins if you do this pull down assay. However, in the squamous cell carcinoma of the skin, you can find basically all of these different keratins which we investigate. So for this tumor, we came up with the following list, which you can see here from keratin 1 to keratin 5, keratin 6, etc. And I just want to explain you briefly why we put in these different keratins. For example, some like keratin 17 at the very bottom, they are induced by inflammation, described as autoantigenic psoriasis. Some like keratin 6 are expressed in hyperproliferative keratinocytes, and some like keratin 14 are expressed in basal keratinocytes. We then synthesized again these overlapping peptide pools. As a positive control, you see we use CEF, so CMV, EBV, and flu. So each of us should have a response at least against one of these viral antigens. And then we found the following. So in the CEF pool, at the top here, positive control. So basically all patients had a CEF-specific, so a virus-specific response. But also many patients, you see that here, where the pointer is, had a keratin-specific response. And very strikingly, these cutaneous squamous cell carcinoma patients, if they had a keratin-specific response, most of them had a response against keratin 14. If you still remember, the lung cancer patients, they had a more dominant keratin 6 response, whereas the cutaneous squamous cell carcinoma patients have a keratin 14 specific response. In oral squamous cell carcinoma, another keratin may play a role. We then moved on with the keratin 14, so that's basically the MART1 or the GP100 of cutaneous squamous cell carcinoma. In this case, it's a keratinocyte differentiation antigen, but not a melanocyte differentiation antigen. So when we now did a T cell stimulation with keratin 14 reactive CD8 T cells, and then single cell RNA sequencing using the 10x genomics system, we could see that many, or basically almost all of them are granzyme B positive, or several of them are interferon gamma positive. So they are indeed cytotoxic T cells. And we sequenced also in this setting the alpha and beta chain, the entire alpha and beta chain of the T cell receptor, in order to engineer these T cells to see if indeed these T cells can also kill tumor cells. Before we did that, we also clonotyped our cutaneous squamous cell carcinomas and could demonstrate that the TILs within these tumors are also specific for the keratin 14 antigen. Of note, basically, virtually all of our patients who showed the keratin 14 response were HLA B0702 positive, pinpointing that this is a restricted epitope to keratin 14. We are currently characterizing the exact epitope in simulation assays and also in crystallography of MHC1 presented epitope. However, what is more important for us, also as clinicians, is that if we engineer these keratin 14 specific TCRs, i.e. we knock out the endogenous T cell receptor and put in at the very same position this keratin 14 specific T cell receptor, we can see that they induce apoptotic tumor cells and also dead tumor cells. Here you have positive control, and on the left-hand side, you have the respective negative control. Moreover, what I want to say is that this approach not only helps to decipher new cancer antigens, it also helps us to find out what autoantigens we have in autoimmune diseases. A relatively frequent T-cell, prototypically T-cell mediated inflammatory skin diseases like planus. And we then could see, typically you see this dense lichenoid infiltrate, which is exactly attacking the basal membrane, the basal keratinocytes just above the basal membrane. And if you do the immunohistochemistry, you see it's full of T cells. And what we could see also that in this, without the tumor, in this autoimmune disease in patients, we find this keratin 14 specific T cells. And I would like to conclude, therefore, antigens of T-cell mediated inflammatory skin diseases. On the one hand side, if you have as target cell the melanocytes, the antigen is MARC1, GP100, or tyrosinase. So differentiation antigens, melanocyte differentiation antigens, they cause vitiligo and they cause regression of squamous cell carcinoma of the skin. On the right-hand side, if you have the target, the keratinocytes in the skin, then keratin 14 or in lung cancer keratin 6 are the antigens, and they may result in keratin 14 in lichen planus and in keratin 6 with the psoriasis-like appearance. So therefore, if we come back to this model, I suggest not only to study tumor-specific antigens, but also tumor-associated antigens. And as concluding remark, self-antigens can have potent anti-tumor properties, but can also mediate immune-related adverse events during checkpoint blockade. Melanoma differentiation antigens mediate anti-tumor response as well as vitiligo in melanoma patients. Keratinocyte differentiation antigens mediate anti-tumor responses as well as autoimmune skin toxicity in non-small cell lung cancer and cutaneous squamous cell carcinoma patients. Last but not least, self-reactive T cells and antibodies. I could speak for another half an hour about antibodies, but I wanted to focus here on the T cells. Both play a role in the development of immune checkpoint inhibitor mediated toxicity, but also in anti-tumor response. But why is that important? I mean, of course, it's always good to understand the pathophysiology behind. But moreover, I think we are at the point where we have now new weapons like engineered T cells or like CAR T cells, where we need to come up with new antigens in order to use them properly. Because in many solid tumors, we don't know yet what are good antigens to be targeted. So I would like to suggest that from learning from these toxicities, we can come to new cancer targets for engineered T cells, for cancer vaccines, for antibody-based treatments, also antibody-drug conjugates, and also for soluble T-cell receptors with an anti-CD3, also called T-cell engagers. In the end, I would like to emphasize that this is my team which is behind, and also several people who collaborated with us. So a big thank you to all of them. And also to my entire clinical research team, who also helps with getting all the samples, running clinical trials. And thank you for your attention. I'm happy to answer any questions.
Okay, Lucas, thank you very much for an interesting talk. We have time for 2 short questions.
So great talk. Basically, what you have presented
It's not working.
that it's actually a good idea to see the toxic side effects. What I was wondering was that is there a window of opportunity where you don't see the side effects, but you actually target the tumor?
Yes, I think for some, yes, I think that's a very good question. I think the question is how strong is the off-tumor effect? I would not say off-target because it's the same target, but I think as an example, I have also previously discussed it today. HER2 is also a lineage antigen. HER2 specific antibodies we can use in breast cancer. And we need to find these kind of antigens where the toxicity is acceptable, but the anti-tumor effect is much higher than the toxicity. I think, yes, this is possible.
If I may ask a second question, so this technique which you described or used, the GITAS, what is the advantage of techniques which were used previously, such as SEREX? Would SEREX also identify the same antigens?
That's a very good question, because last year at our lab reunion, I met Ugur Shahin, and I told him, Ugur, I'm a big fan of your SEREX technique. Why didn't move that forward? And he just told me he founded also the company before he had BioNTech Ganymede, and he told me just half a year before that, an antibody was approved for that. However, I also asked him why were there not more targets identified. I think it's a very noisy approach, the SEREX approach. And I also think that the SEREX approach was used in the wrong population. You need to compare the right samples with each other. And what I'm doing right now, I can only do that because I take advantage of patients who respond to checkpoint blockade. And this treatment was not available. I think also SEREX could be repeated again with samples, well-curated samples from these patients. Very good point, and I like SEREX.
Very interesting, very interesting. Thank you very much. Thank you. So, Lucas, before you go, apparently there will be something.
I would like Dr. Sagi to facilitate Dr. Platz.
Yeah, you'll get a prize. Okay, now I have good news for you. The missing speaker is back.
Philip. Yeah.
So we have a talk now by Professor Philip Beckhoff from Leibniz Center for Interventional Immunotherapy in Germany. So Dr. Beckhoff graduated from University of Heidelberg and then raised through the ladder to various positions, also at Medical Center of Heidelberg. Then he worked at the KFZ under leadership of Professor Schirmacher. And then since 2015, he is professor and chair of interventional immunology at the University of Regensburg, and then scientific director of this center. And 2 years ago, he became scientific director of the Leibniz Institute of Immunotherapy. Dr. Beckhoff, please, the floor is yours.
Yeah, thank you very much for the kind invitation and the nice introduction, and apologies. Actually, I thought my schedule is European time, so that's why I was late today. I hope now it works, that I can share my screen.
Hey, Philip. Hello. HP.
Yeah. Hi.
Hi. Can you see me?
Yes, I see you. Hi, HP.
All well?
Yes.
Go ahead. Yeah. See you.
So, can you see the screen now?
Yes.
Okay, good. So I'm talking about therapeutic strategies to overcome immune resistance in pancreatic cancer. And this is about breaking immune escape of particular tumor intrinsic immune resistance mechanisms. So I would like to start with the point that we are studying tumor specific cytotoxic T cell responses in a variety of cancer types in patients. And one important point is really to have a look at the interaction between such cytotoxic T cells and the tumor cells. And we have developed a reporter system that shows us the secretion of effector cytokines, such as TNF, for example. And you see here a co-culture of cytotoxic tumor-specific T cells with autologous tumor cells. And you can see now those that become red are just secreting TNF to the outside. And you can see that there is a good activation of these T cells. So they are accumulating and can really recognize the tumor antigen on the tumor cells. The question is now, what happens to these tumor cells? Are they killed? And we have another reporter essay where we study the induction of apoptosis in the tumor cells which become green. And you see this now on the upper left, and here you see the activated tumor cells. They screen the activated T cells, they screen the tumor cells, and here in the middle now there's a tumor cell attacked by several T cells, and the effect is the division. I hope you just saw it. So the tumor cells are definitely not being killed, but they divide. So they are somehow activated instead of being killed. So what's happening there? So we analyze calcium signalings in the tumor cells, and you can see that each time a cytotoxic T cell attacks a tumor cell, there's a calcium signal within the tumor cell, and this of course has an impact on gene expression and signaling. You can see also this interaction here from the T cell side. So there is really an activation of the T cells, and there are pulses of calcium throughout this interaction. So we are interested in identifying those genes in the cancer cells that make the cancer cells resistant against the cytotoxic attack. And how do we do this? We established a high throughput screen for human cytotoxic T cell tumor cell interactions. So the screen is based on a multi-well format where each gene is knocked down by siRNA libraries. And so we can do this with many thousands of genes in parallel. The tumor cells are luciferase transduced so that we can image their death, and then we expose them to cytotoxic tumor-specific T cells or keep them in a control to see whether the gene has a viability effect on its own. So what we normally get is then such a sign. So the control siRNA has no impact on luciferase activity, but if you knock down a gene that mediates resistance against the cytotoxic attack by the T cells, then the signal goes down, and this is then a gene that has an immune resistance function. So we did this with 6 different tumor entities and very, very many screens, and we identified overall more than 230 immune resistance genes that have not been described so far. Here you see an example for pancreatic cancer, and you see here that there are many, many genes. Each dot is an individual gene that have a much stronger immune resistance gene function than, for example, PD-L1. And we have validated these immune resistance genes. And now the question is, what are they doing and what is their impact? And here you see a couple that I would raise today: SIG3, YWHAH, CEACAM6, ACAP1. So first of all, we went into sequencing data sets, transcriptome analysis from many, many patients. So here you see the TCGA database analysis on the left, and you see different types of tumors. From colon cancer over PDAC, many, many ones that are collected there with many patients, and each row is a patient, each line is a patient. And you see that there are very distinct landscapes of immune resistance genes that are used by the different tumor entities. So they are overexpressed here, and they are exclusively overexpressed. And you can see that their colon cancer uses a different set of immune resistance genes than, for example, pancreatic cancer, melanoma, or others. And this we found quite interesting, and we compared this now to a similar data set. It's the GTEx data set that analyzes healthy human tissues. And here you see for PDAC the comparison, and also here you see that there are distinct expression patterns of immune resistance genes in the normal tissue. So that shows that each tissue has a different set of immune resistance genes that help to overcome autoimmune disorders. Now, if you compare healthy pancreas and PDAC, you see that there's a load more and a particularly very distinct set of immune resistance genes in pancreatic cancer compared to healthy pancreas. And that shows that there might be a therapeutic window also to target these. So what we then did is to go into single cell analysis to see what in the pancreatic tumor stroma it really expresses these immune resistance genes and whether these are mainly tumor cells. So we analyzed, we combined a lot of single cell data sets that are published and came up to a merged analysis of more than 78,000 different single cells in pancreatic cancer. And among them are, of course, all the stroma cells, CAF, stellate, macrophages, B cells, and so on, endothelial cells, and of course the malignant ductal cells, which were proven by chromosomal aberrations to be really individually malignant cells. And then you can have a look on the differential expression of immune resistance genes, and you immediately see that the malignant ductal cells have a strong overexpression of many of these immune resistance genes compared to stroma cells that are not malignant. Although you can also see that at least some of the immune resistance genes are also expressed in normal ductal cells, acinar cells, and some stroma cells, such as endothelial cells, also express a few of these immune resistance genes. But in essence, there's a load overexpression of these genes in the malignant cancer cells. And now the question is, how are these malignant ductal cells composed? Is that a homogeneous population? We know that, for example, in pancreatic cancer, there's a strong intratumor heterogeneity of different tumor cell types. And so we were interested whether these differ in the usage of the immune resistance genes. And so we went into a subcluster analysis of these single cells. You see this here on the upper left. So indeed, there are different clusters. And if we have a look at their different biologies, we see that they differ in regard to, for example, proliferation. So cluster 7 is a proliferative one. In regard to cell adhesion and migration, which is a feature of cluster 0, or in regard to tumorigenesis and protein production and translation, which is a feature of cluster 1, or stress response and oxidative metabolism, which is a feature of cluster 11. So we had a look now in these clusters for the differential expression of immune resistance genes, and you see this here in the middle. And indeed, there are very clear different patterns of such genes overexpressed and differentially expressed in these clusters. So each cluster has a different immune resistance phenotype. And that is, of course, quite interesting. And we went one step up and had a look at potential transcription factor landscapes that might drive exactly these genes. And then you see indeed that there are differentially expressed transcription factor landscapes for each of these subsets, which drive these immune resistance genes. And this suggests that there is a kind of an external stimulus that drives the transcription factor activation, which might have to do with the tumor stroma. And we are currently analyzing the spatial composition of these different clusters within one cancer and one PDAC to see whether there is a spatial heterogeneity. And we indeed see that there's a mosaic-like pattern of these different clusters within pancreatic cancer. So obviously, immune resistance is, although it is all, let's say, given by each of the tumor cells, it is not always given by the same genes. And we have to keep this in mind when we want to treat pancreatic cancer with immunotherapies. So now let's have a look on a few of these genes. We wanted to study for each of these clusters a gene that is differentially regulated. SIG3 is an interesting one because it was evenly expressed in PDACs. It is overexpressed in PDAC, but evenly expressed in all the clusters. But the others were differentially expressed. YWHAH was found in cluster 7, ACAP1 in cluster 1, CCAM6 in cluster 0. So we had a look what they are doing and how they work. And SIG3 is the first one I wanted to shortly show. It's a serine threonine kinase. We have made a gene signature that shows the activation of this kinase in the pancreatic cancer tissue and applied that to the TCGA database. And you can very nicely see that the activation of SIG3 in pancreatic cancer goes along with a very, very poor outcome, which is the normal outcome. 85% of the pancreatic cancers show this feature, while low activation of SIG3 is going along with a very, very good prognosis. So this is striking, and we could also show that the high SIG3 expression is based on T cell activation. So cytotoxic T cell activity drives SIG3 expression. So what is it doing? So first of all, we found that if you expose pancreatic cancers to TNF, which is normally deadly to many tumor cells, pancreatic cancer cells profit from it, so they even increase, expand. But if you knock down SIG3, there is a complete abrogation of the resistance, and these tumor cells die. So what is behind that? The first thing that we studied is NF-kappa B activity, because NF-kappa B activity is one of the major drivers of tumorigenicity in pancreatic cancer. And now we have done a reporter assay system where we transduce pancreatic cancer cells with the NF-kappa B reporter, and you see that if you add cytotoxic T cells to these pancreatic cancer cells, there's a strong induction of NF-kappa B. It's very homogeneous, very strong. So T cells, cytotoxic T cells don't kill the tumors, but they induce NF-kappa B. And if you knock down SIG3 in the tumor cells, there's no NF-kappa B at all. So SIG3 mediates the induction of NF-kappa B after the cytotoxic attack. And this is entirely mediated through TNF receptor signaling, as if we block this, we can then also completely abrogate the NF-kappa B induction. So we can conclude that T cells induce NF-kappa B instead of killing, and that this is going through SIG3 and through TNF. So what is now SIG3 doing apart from the induction of NF-kappa B? So we had a look on anti-apoptotic genes, and we found that SIG3 drives the expression of NF-kappa B mediated anti-apoptotic genes, and there are a lot of them, and a few of them are shown here. And they are only upregulated upon T cell exposure when SIG3 is present, and they are not induced when SIG3 is absent. And this has a strong impact, actually, on the survival capacity of and anti-apoptotic resistance of pancreatic cancer cells. So this is here the mode of action, which is a bit more complicated, so I don't go into this due to time constraints. But TNF receptor 1 triggering by the cytotoxic T cell now can induce the caspase activation, so the apoptosis normally, but it also triggers the activation of SIG3. And SIG3 then phosphorylates HDAC4, and HDAC4 goes into the nucleus and can acetylate NF-kappa B. And this is the anti-apoptotic pathway. And SIG3 shuffles HDAC4 out of the nucleus and makes sure that the acetylation, that means the inactivation of NF-kappa B, cannot happen. So it protects basically the tumor cell from HDAC4 mediated NF-kappa B inhibition. So this is the mode of action. And now we wondered whether we can generate an inhibitor against this. So we spun out a company, Iomics Therapeutics in Munich, and they have come up with an inhibitor for SIG3. And if you apply this inhibitor to tumor models in the mouse, you can see that there is a strong reduction of tumor outgrowth, which is much more potent than a PD-1 treatment. And this also goes along with a strong reduction of NF-kappa B activity in vivo in the tumors. We brought this into phase 1 clinical trial, and this is a basket trial at the moment, but it has passed phase 1 already. And here you see that we can induce complete and long-lasting remissions of late-stage metastasized cancers with this drug. Another one that I wanted to show, this is now a gene that is expressed in malignant cluster 0. This is CCAM6. CCAM6 is a gene that is overexpressed in many pancreatic cancer, the strongest overexpressed immune resistance gene that we found there. And if it's expressed, it completely shuts down the activation of tumor-specific T cells. So you see here positive control in an ELISpot assay with survivin-specific T cells. And you see here the response to tumor cells that express survivin. If you block CEACAM6, then you have a complete restoration of the T cell activation. So there's a complete shutdown of this activity through CEACAM6. So we found out that CEACAM6 in the tumor cell recruits the CEACAM1 on the T cell side, and CEACAM1 has an item motive and brings the SHP1 phosphatase to the T cell receptor, and this can then dephosphorylate the T cell receptor, for example, sub-70, and shuts down T cell activation. So we generated, together with Bayer Healthcare, a blocking antibody against this interaction in order to maintain T cell activation in the context of a tumor interaction. So this antibody can indeed restore the reactivity against tumor cells that express CEACAM6. So that is a very strong effect, for example, in interferon gamma secretion, and it can restore a complete lysis of tumor cells by these T cells. So it went into clinical phase 1 trial, and there it turned out that based on some let's say leftover FC based activity, the antibody can activate also monocytes and neutrophils in the periphery, and this caused some side effects. So what we have now done, we have shuffled this and changed it into a single chain small fragment CEACAM6 antibody. We could show that it also blocks the interaction, so this is completely silent now. So this can block the interaction to CEACAM1. It restores the cytokine production as much as the full antibody, and we tested it in function killing. Here you see here the addition of CEACAM6 antibody to co-culture with T cells. It increases the cytokine secretion strongly, and in vivo it also can then lead to a abrogation and elimination of established tumors in a mouse model compared to just the application of T cells. And here we used a CAR T cell system where we added the CEACAM6 antibody. So this works quite well, and we are now preparing this for clinical application. So the last two genes that I wanted to show, they resemble differentially upregulated genes in malignant cluster 1 and 11, and in malignant cluster 7, it's ACAP1, a kinase anchoring protein 1, and YWHAH. So if you block them, you see that in these subsets, cluster subsets, you have a strong increase of cytotoxic function compared to SIG3, so it's has a very strong effect. They protect against the exposure to death receptors such as TRAIL and FAS. And so they are genes that have an impact on the apoptotic cascade that is induced by death receptor ligation through the cytotoxic T cells. And how does that work? Here you see the mode of action. GPCRs are triggered on tumor cells when a cytotoxic T cell approaches the tumor cell. There are metabolites by the T cell that activate the GPCRs, and that leads to an activation of the adenylate cyclase and the CM production. And ACAP1 is activated now through the CM induction, and ACAP1 then can activate the phosphokinase A to phosphorylate BAD, and this then has a pro-apoptotic BAD protein sequestered into the cytosol so that the mitochondria are protected from the mitochondrial apoptosis. So this is how it works, and in this regard, ACAP1 has a very, very fundamental role to protect against the central apoptosis pathway. And just one step later, YWHAH comes in the game, and it keeps the BAD, the sequestered BAD protein out of a potential reusage at the mitochondrial membrane, and therefore also has a major impact on the apoptotic cascade. So these two genes are in the same line and have a very strong impact on the survival. And here you see just an overview of the different pathways that we found. It's a bit confusing, but basically what you can see is that there are multiple different approaches of a tumor cell to overcome cytotoxicity of a T cell and to protect the cell from survival on the one hand side, so by maintaining pro-apoptotic genes, but also to drive tumorigenicity by activating pro-tumorigenic gene transcription and even increase of the aggressiveness of the tumors. And with this, I'm done and would like to acknowledge people in my group and of course collaborators of the past years. And thank you very much for your attention.
Okay, Philip, thank you very much for a very interesting talk. We have time for a couple of questions. If I may start with one. So you mentioned your screen have shown you TNF receptor 1. And you indicated that TNF is actually ligand for this receptor. Can you exclude that it actually soluble lymphotoxin alpha? Because we published many years ago that some tumor cell lines are using lymphotoxin as a growth factor. So this would exactly fit in your initial hypothesis.
Yes.
Potential molecules which may be cytotoxic under certain conditions when cells are in appropriate context actually receive signal for growth and not for cell death.
Yeah, exactly. So what we are actually to find out which death receptors mediate the effect or make it visible, we first test the expression levels of the death receptors on the tumor cells. And as you know, these are differentially expressed in many cancers, and this has of course an impact on which gene is particularly relevant. And here you see an example. You see here basically the cell survival, that means the luciferase activity. If we add the tilts, you see that there is a decrease, right? And when you knock down the gene, but now you can also use the supernatant, TNF, trail, fast ligand, and here you see lymphotoxin alpha, light, interferon gamma, right? So we test all of them, and in this case, ACAP1 also mediates protection against lymphotoxin alpha quite strongly, as you see this. If you knock it down, then lymphotoxin alpha can kill very efficiently, while YWHAH is less relevant here, although it's the same cell line. Yeah, so it has to do with the signaling moieties and with the expression of the gene, but lymphotoxin alpha is indeed a relevant inducer of killing when these resistance genes are shut down.
Thank you. Questions? No more questions, Philip. Thank you very much.
Yeah, thank you very much.
Thank you. So on this note, I got a suggestion to close the session. Because
Can I
the
talk?
first speaker will speak tomorrow.
Sergey.
Is that correct?
No. Sergey, can you give me 1 minute to allow me to talk to Philip? Philip, it's me.
Yeah, hi.
How are you?
I'm fine, thank you.
So now question is, whether this targeting TNF receptor 1 will compensate the TNF signaling to the TNF receptor 2, or does it giving advantage to the cancer cell? Maybe the gemcitabine resistance PDAC1 or something.
So basically, what you explain is exactly what we see. The tumor cells don't express TNF receptor 2, right? But the myeloid cells express it, and the pathway that we found is basically the pathway that is mediated through TNF receptor 2, right? The NF-kappa B pathway. But tumor cells don't express TNF receptor 1, but by expressing SIG3, they shuffle the TNF receptor 1 signal into the TNF receptor 2 pathway. That's basically indeed what happens. So it's a canonical TNF receptor 2 pathway, which is somehow substituted through SIG3.
Thank you. Yeah.
Last question over there, please.
Hello, sir. I had a question that you have selected some gene based on some clusters you were talking about. So the clusters you selected were based on the ranking of the lowest score which you were showing. Or there was
No.
So what were
So the clusters were based on unbiased UMAP clustering of the malignant cells within the pancreatic cancers. So these are based on differential gene expressions, and the genes that we then selected for further analysis were the ones that were ranked according to the LES score.
Yeah. So initially with the single cell data, you went with the UMAP to get the cluster of this cell.
Yeah.
And with them you went with the lowest method to get the ranked cluster. So
exactly.
So the highest the rank which you selected, there was any cutoff for the best clusters?
So the cutoff was for the immune resistance genes. These were the 230 genes that had a stronger immune resistance phenotype than PDL1. That was the cutoff. Anything that was validated and stronger in the immune resistance phenotype than PDL1 went into the analysis, and these are the 230 immune resistance genes. And you saw that not all of them are expressed at all in pancreatic cancer. So the differential gene expression is basically the one that shows these genes that are upregulated in pancreatic cancer, and then you saw how they are distributed to the different clusters.
Right. Thank you so much.
Thank you. Philip, thank you again. And
thank you.
On this note, again, I just want to repeat that Dr. Kumar Prabhash will speak tomorrow. At least this is what HP told me. Hopefully it's consensual, and so with this, we may close the session. What is now? Tea break or what? We continue, okay. So somebody should come up then.
Yeah, since we are running the 1.5 hour or 1.25 hour late, so the next it's for the speaker for the next sessions that they may curtail their talk within 15 minutes. That would be really, help us in managing time. And IT is also placed outside, so that will go in parallel. And and this is also because we have to start the dinner, gala dinner today in time. Otherwise, we'll miss the bus. Yeah. So these are the few minor announcement, and rest you can continue, please.
I would request Dr. Prakash to felicitate Dr. Sergey. Sergey sir, can we have you on the stage, please?
Let's proceed to session 3 on drug resistance and cancer therapy. We have our session chairs, Dr. Kumar Prabhas and Dr. Lucas Flats. Please give a huge round of applause for our session chairs. Dr. Kumar Prabhas is a renowned medical oncologist with over 20 years of experience, currently serving as the head of medical oncology department at Tata Memorial Hospital, Mumbai. Dr. Prakash has worked on over 80 projects and is recognized as one of the India's leading medical oncologists contributing significantly to oncology research and clinical practice. We all welcome you, sir. Dr. Lucas Platz is a clinician scientist and professor of dermatology, heading the dermato-oncology section at the University of Tübingen, Germany. Dr. Platz researches immune-related adverse events and has pioneered the task for tumor antigen discovery. I will now hand over the mic to our session chairs to introduce our speakers for the day.
We just get the program, please. Because we had so many changes, we need to make sure that we are introducing the right people. So we will continue with Sakhar Sengupta. Dr. Sakhar Sengupta will talk about the remodeling of the epigenome linked to chemosensitivity and adjunct therapy in colon cancer. And just a short biography. Dr. Sakhar Sengupta is presently working as the director of the National Institute of Biomedical Genomics, Kalyana, West Bengal. He was elected as National Academy of Science Fellow in 2015. In 2017, he has been elected as a Fellow of Indian National Science Academy and Indian Academy of Sciences. Dr. Sengupta was awarded with J.C. Bose Fellowship in 2018 and has been elected as Vice President of the Indian. His research interest areas are genome integrity, tumor suppressors, and oncogenes, DNA damage response, ubiquitination and phosphorylation-dependent signaling mechanism, global regulation of gene expression, mitochondrial replication, role of mitochondria in cancer. The stage is yours. We are looking forward to your presentation. So a big applause for Dr. Sengupta.
I think Hirdesh, any high tea for chairpersons?
So I will change. We'll do one by one. Listen complete on time. Okay. 20 minutes and we've been asked to 15. Thank you so much, team. I can do that. Yes. No. Till now. Now means which sugar is sugar. Yes, what it is. This is the principle. Let's say, okay. The chair is there. For me, this is. I was in over the bridge. When I was like, based on the bridge, and it is like,
checked.
May I?
I'm doing of the crops and explanation. But I'm not both. I think there is a lot of what's going on in year or so, we were very sensitive to go away from we do not think properly. But it's difficult because of delays and the documents and I think it's more important that you clinician than those understands. But in worst case, in the end, you're not a good scientist and you're not a good clinician. Yeah, it can happen. Do you also check clinical trade and also in I'm Bangalore. 20 years. This is without on the side here. Option there. We have the option. Thank you so much. If that word, so again, take a low dose immunotherapy trial. 20 milligram nivolumab. Only 20 milligrams. Every 2 weeks. Every 3 weeks with the chemotherapy. Every 3 weeks. Yes, but we know there is not much titration. Usually the usual dose is 240 milligrams every 2 weeks and 480 every 4 weeks. We really need them in non-small cell lung cancer. I need to look it up. I need to look. It was a good event. So we are taking it from but you were supposed to give the talk today, yes, no? Yes. Because I was looking forward to on the talk when you are not ready. They ask if you can get this to me. It's one. They don't say. Because you're not an IT. Cells are different places. Say it again. Economically, squamous cells are different in different places. Oral cavity, head and neck. Yeah, they express different differentiation activity, different keratins. I think, yeah. And this is what the T cells are saying. Yeah, I don't know. We need to look into that. It's just that I want to. But you understood that it was striking. This is the first time someone ever differentiating the different cell the way interesting. But we know they're separate, they are separate places. They behave differently. No, that's yeah,
Dr. Sagar, we can go ahead with the next lecture in case there's an issue with the technology, so we can. Yeah. So next is Dr. Hari Kumar B. He is from Rajiv Gandhi Center for Biotechnology. May I request Dr. Hari Kumar B. To come on the dais, please. And his topic is sensitizing of colorectal cancer to checkpoint inhibitor through sphingolipids signaling. Dr. Hari Kumar.
Thank you, Dr. Kumar, and I would like to thank Dr. Tudesh Prakash and his team for the kind invitation. So I will be, since we are cut short the time, as Sudesh said, 15 minutes, I will try to stick on with that. So my lab is primarily working on sphingolipid signaling, and before I start the talk, I'll just give you a brief introduction, like what we are actually working on. So we actually work on sphingolipids, as many of you know that is one of the key lipid molecule. And so in this, we are looking at two of the aspects. One is on the ceramide pathway, and the second one is on the sphingosine pathway, where this the top today going to primarily on acetoceramidase, which is the only enzyme which is known to convert ceramide to sphingosine. It produces a bioactive molecule called sphingosine 1-phosphate, which has several biological functions. Similarly, ceramide also getting converted to ceramide 1-phosphate. So this particular, the one I've shown in the red box, is our major area of interest. And today I'm going to focus on one of the key enzymes, acetoceramidase, which is only known to convert ceramides to sphingosine. And there is also exists a ceramide sphingosine axis, which basically favors, as you all know, that ceramide is always favoring apoptosis, and the sphingosine and 1-phosphate is actually favoring the cell surveillance. So there is exists a rheostat between ceramide and sphingosine as well. So moving further, so we have some information already available that it has known to be a tumor promoter or have an oncogenic role, especially in certain type of cancers where it actually promotes PI3K signaling. Also leads to the higher activation of acetoceramidase, lead to loss of PTEN, and few reports suggest that it also the overexpression of acetoceramidase leads to resistance to certain drug molecules, and especially there's a group in UK, they have extensively studied the role of acetoceramidase in annexing radiotherapy using mouse and human samples, and they've really shown the involvement of acetoceramidase in radiation, resistance to radiation. So today primarily I'm going to talk about the work of my student Yadu, who recently graduated and he's postdoc in US, and mostly his work I'm going to present today. So what we did was initially when we were looking at this contraction role of acetoceramidase, what we did was we were actually looking at some of the clinical samples where we collected colorectal cancer samples, and we did an immunohistochemical analysis of the normal and the different stage tumors. We can see the stage 4, the number is very limited, but what we could see that there is a clear correlation between the stage of the disease and acceleratory expression. This gives us some of the initial clue that acceleratories might be involved is overexpressed. So then again, we look at the TCGA data set and the GPA data set and found that apparently the acceleratory expression is higher in tumor samples compared to the normal samples. Give us the first clue that ASH1 is upregulated in human colorectal cancer. So then what we did was, my lab is, we extensively work on various mouse models of colorectal cancer. And we do colitis models, then colorectal cancer models, then colitis associated colorectal cancers using different preclinical system. So what we did was we actually, from our archive, we choose all this FFP tissue and of colorectal samples, and which is either colitis or the colorectal cancers induced by an associated model or the ARDSS model, which is actually an inflammation-driven cancer model, and try to see what happens in the FFP tissue. And similar to what we observed with the human CRC cases, we could see an upregulation of ASH1, similar at the protein level as well as at the gene expression. This prompted to conclude that whether it's a human colorectal cancer cases or it's a mouse colitis or whether it's a mouse colorectal cancer, there is an upregulation of ASH1. So looking at then the idea is to see what exactly the role of ASH1, even though it is upregulated, whether it is going to have any effect. So that we actually did two approaches. So mostly I'm going to talk about two cell lines. The cell line based works are mostly focused on SCT116, which is a human cell line, and a CD26, which is a mouse cell line. And we also have a specific inhibitor, which actually synthesized at the Medical University of South Carolina, United States, the LCL, and that is only non-acetylamidase inhibitor currently available when we started the work. So now they have a modified version available. We are ready to test that one. So the first experiment what we did was we actually did a tumor model, both in immunocompromised mouse as well as an immunocompetent mouse. So the reason was the immunocompetent because CD26 what we use, it was actually a BALC derived mouse model. So that's the reason we used BALC model. And then the immunocompromised mouse models. So, and we were using the knockdown cells as well as the inhibitor. So in one group we use the inhibitor and the third group we use the knockdown cells. So what we noticed that in immunocompromised mice, whether you are using the pharmacological inhibitor or you are knocking down the cells, there's absolutely no effect on the tumor formation, and more or less there is a tumor is formed in all the group, but no effect with the acetylamidase silencing, either pharmacologically or genetically. But to our surprise, in immunocompetent mouse, what we noticed that whether it is pharmacological or genetic or the knockdown, there is a silencing or there is a reduction in the tumor. This indicates, and this just show the immunohistochemical analysis of the PCNA and cyclin D1 that there is a reduction, indicating that the ASH1 knockdown or the silencing is actually inhibited tumor growth in immunocompetent mice, but not in immunocompromised mouse, giving us some clue that there might be an involvement of immune system. So we did one quick immunophenotyping, and what we noticed, the most importantly, what we noticed that there is an upregulation of CD11B and most importantly, the CD8 T cell into the tumor, indicating that there is this ASH1 is actually silencing the ASH1 is actually influencing the tumor microenvironment and leading to more infiltration of CD8 T cells. So further, what we did was we just did a characterization of the particular drug because so we noticed it's a classical way of doing the pharmacological assays. We noticed that it is actually inhibiting the cell growth in a bunch of cell lines, and it also inhibits the LDS secretion and also induces apoptosis. So so we know about all the different types of cell death. We have about 8 to 9 different types of cell death, and one of the cell death which is important is the immunological cell death, which is basically a kind of cell death which can actually induce an immune response. And there are certain markers like to see whether a particular is actually inducing immunological cell death, just like that the calreticulin translocation into the surface or the secretion of HNGP1 or AKP release. So, and especially anti-cancer drugs which are capable of inducing LCD is a really inactive area of research. And in that line, we actually tested the efficacy of LCL in whether it is going to induce any immunological cell death. And what we noticed that yes, it is actually inducing immunological cell death, as we seen from increased calcium expression on the surface and SMPG release or ATP release. And this was one of the reviewer questions when we are actually doing that whether it actually regulates MSC regulation. So we did one flow cytometry analysis, and what we also noticed that both MSC1 and MSC2 actually getting upregulated at the surface level, whether you are looking at pharmacological knockdown or whether you are going for a genetic silencing, indicating that ASH1 downregulation resulted in immunological cell death and release of damp in CRC cell lines. Then we did a metabolomic analysis and to see what exactly this drug is or what's the role of ASH1. And what we noticed that the most important pathway which is getting affected was glutathione. So we did in the tumor samples the expression of some of the markers like the GSH and the GPS, both in the cell line as well as in the mouse tumor tissue. And what we noticed that yes, it is when you are knocking down, it's actually reducing the expression of GSH and GPS, and also there is a higher upregulation of ROS production. So ROS is also nowadays considered as a marker for ICD, but it has to be correlated with the other markers of ICD. So at least we could conclude that the drug is actually, or the ASH1 silencing is actually inhibiting the immunological cell death. So reducing the immunological cell death. So we also did a mitochondrial stress analysis, and we due to lack of time and not going into detail, but what we also noticed that yes, silencing acetoramidase also induces mitochondrial stress. So the CRC is always considered as a cold tumor because of less infiltration of the T cells, and there's a more presence of the T regulatory population. So our idea was to see whether, since we have seen that this LCL, the compound what we are using, the ASH1 inhibitor, induces immunological cell death, and trying to see whether if you are trying it with a checkpoint inhibitor, what is the effect, whether it's going to have a better effect or the effect will be like each compound has its own effect. So that's what we did was we used again the CD26 model, and we use LCL and an anti-PD1 alone, and then there is a combination of both LCL and anti-PD1. And what we could see that there is a decrease in the combination, and we could see that the proliferation markers are very less in the both LCL as well as in the combination group. And more importantly, the T cell infiltration. So we look at the CD8 T cells. As expected, there was a higher upregulation of T cells, especially in the combination. And then we look at the expression of IFN gamma and granzyme B within the CD8 T cells. So what we notice that within the CD8 positive T cells, the IFN gamma positive and granzyme B positive cells are actually increasing, which actually shows that there is more T cell infiltration in the combination group compared to the individual group alone, indicating that the silencing ASH1 is actually improving the CD8 T cell recruitment. Then we also look at the inhibitory markers, the MDSCs and the T regulatory cells. But we noticed that both MDSCs as well as the T regulatory populations were also decreasing in the tumor samples. So we also look at the CD8 FOXP3 ratio. So there's a thought that it could be an indicator for better survival and a predictive marker for checkpoint therapy. And what we noticed that yes, LCL is actually increasing the ratio, and it leads to immune suppression with an improved CD8 FOXP3 ratio. Then we also look at the macrophage infiltration, and what we noticed that there is more infiltration of M2 macrophages in the population, and we also look at we did an immune deconvolution, the TCA dataset, where what we noticed that. So we took actually a TCGA dataset where and we divided into two halves. The group, the CRC patient showing higher level of ASH1 and a lower level of ASH1. So what we noticed that the patients with the higher level of ASH1, there is a more M2 macrophages and a T regulatory population, but there is a less M1 macrophages. So then we did an RNA-seq analysis, and what we noticed that there is a upregulation of especially the type 1 and type 2 interferon response within the tumor milieu, enhancing the immune response. And to conclude that ASH1 is overexpressed in colorectal cancer, and silencing result into induction of ICD, decreasing glutathione system, increasing mitochondrial stress, and ROS. And ASH1, either as a monotherapy or in combination, is actually resulted in better regulation of tumor, activation of eminent macrophages, lead to enhanced infiltration of cytotoxic T cells, suppression of MDSC, and induction of type 1 and type 2 resistance, which was recently published in the Journal of Advanced Research. Thank you for listening, and this was mostly funded by DBT and ACR, which is now available. Thank you.
There is already one question from the audience, please.
Yeah,
I only have two short questions.
This is a very nice work. Just want to ask you, means as you worked on SH1, that ceramides, so have you overexpressed NSMAs or ASMAs, means sphingomyelinase, or overexpressed or knocked down sphingosine?
Reported that sphingosine kinase 1 and 2 is already reported.
Okay.
The reason why we are looking at that, like why, because that this is upstream of that, and what actually driving the product from more sphinges. Because sometimes what we notice that the level of especially the sphingosine kinase 1 is more involved in colorectal cancer.
Yeah.
Not KG.
Yeah.
But that is not actually telling us why there's a more upregulation of sphingosine. So that's the reason we look at whether ASH1 has a role. So what we notice is that there is more ASH1 is coming, and because of that, ceramide is getting converted to sphingosine.
Okay.
Because this is the only enzyme which can convert to sphingosine.
So whether the similar type of effect you can see for that overexpressing acidic sphingomyelinase or neutral sphingomyelinase, because then means as you were mentioning that in the cell there is higher level of ceramide, means you are making that the cell more ceramide specific. If we see ceramide and S1P, and then if you overexpress that NSMAs or ASMAs, hope we can see the similar type of work. So that will give us a more robust way of presenting that yes, ceramide pool is making this helping that immune checkpoint and all others. Thank you.
If there is no other comments and questions, then we can go ahead with the next presentation. And I think so now Dr. Sagar Sen Gupta is ready. May I request to any other announcement you have?
So before we proceed, I would request our session chairs to felicitate Dr. Hari.
So next talk is by Dr. Medical Genomics India, and he'll be talking on remodeling of epigenome linked to chemosensitivity and adjunct therapy in colon cancer. Dr. Sagar Sen Gupta.
Thank you, and
request all speakers to stick to 15 minutes, as told by organizers.
Yeah, so I will try to keep myself within the 15 minutes, definitely. So without going much ado, let me just talk about the recent work which we have done in our lab about trying to understand whether small molecules can revert chemoresistance. Hello. Hello. Fine. So
This is the broad areas of research which we are doing. We try to understand ask basic biology queries, and from there we always try to get certain translational outputs, and we have certain plans for the future using those translational outputs. So I would like to introduce one of the family of helicases, which we have worked very extensively on, and one of the members we will be talking more extensively today is the BLM helicase. And this family of helicase is conserved across evolution, and mutations in BLM helicase causes an autosomal recessive disorder called Bloom syndrome. Why is Bloom syndrome interesting to us? Because when it is, though it is autosomal recessive disorder, it predisposes every Bloom syndrome patient to all types of cancers, starting from lymphoma to sarcoma, so the entire spectrum of cancer seen. So it has some good model to understand the mechanistic biologies of different types of cancer. BLM, of course, has many other functions. It is involved in genome surveillance, it is involved in DNA damage sensing, and repair and recombination, and it has very defined clinical phenotypes. So one of the long-term projects which it's trying to understand how BLM helicase actually interacts with its native substrate. As you can understand, it is a helicase. It is a DNA helicase, so it will interact with chromatin. So that was the main thing which we wanted to ask at that time. So I am not going to go much into the fact about the active and repressed chromatin because of the shortage of time. But I would like to bring to the attention of a group of proteins which are called chromatin remodelers. The chromatin remodelers are a big group of proteins which consists of multiple subunits with a central ATPase domain, which actually remodels the chromatin and makes the chromatin either active or inactive. It is an interconversion which continuously takes place in each of our cells. And there are a lot of different types of proteins. Because of shortage of time, I'm not going there. There is also something called chromatin remodeling assays, where you try to understand whether the chromatin is active or inactive. Basically, you have nucleosome arrays, and in which you actually put in restriction enzymes and see whether the nucleosome is actually sitting on top of the restriction enzyme or not, which will tell you whether the chromatin remodeling is happening or not. So with this primer, let me go into the data. We saw a long time back, maybe around 14 years back, 2009 to be precise, where we saw the BLM helicase actually stimulates the ATPase and chromatin remodeling activities of a chromatin remodeler called RAD54. And we were intrigued by it. We reported that, and we were asking, why does Bloom helicase stimulate the ATPase and chromatin remodeling activity of RAD54? That was the basic question at that time we asked. And does it have any connection to the role of BLM in its defined role as a DNA repair and recombination proteins? So with this thought process, we did a series of internal amino acid deletions, N-terminal deletions, C-terminal deletions. Remember, BLM is a huge protein, 1417 amino acid. And we found out a 32 amino acid stretch, an internal 32 amino acid stretch from 181 to 212, which was sufficient for BLM to interact with RAD54. As you can see it here on the left-hand corner, that when the 32 amino acid deleted, there is no interaction. And that 32 amino acid was good enough to cause the chromatin remodeling activity also for BLM. And when we actually use a deletion mutant of that delta, we do not see the remodeling activity. So we went ahead, now we made a synthetic peptide which we commercially made, and we wanted to see whether this synthetic peptide was good enough to cause the chromatin remodeling, enhancement of the chromatin remodeling activity of RAD54. Sure enough, this 32 amino acid was able to do it, while a scrambled peptide was not able to do it. So how does chromatin remodeling happens? Of course, it is an energy-dependent process. It has the RAD54, the chromatin remodeler, has to bind the ATP and also cause the hydrolysis of the ATP. And so when we use in trans the Bloom peptide, the red bar, you can see that the Bloom peptide helps in the chromatin remodeling activity much more than the green bar, which is the scrambled peptide. And if you can see the hydrolysis of the ATP also, it is helped out by the Bloom peptide. So basically, these 32 amino acids are good enough to cause the stimulation of the ATP binding and hydrolysis. So having done that, the next question which we asked ourselves, is how does Bloom stimulate the ATPase and chromatin remodeling activity of RAD54? So we went ahead to a tried and tested technique, which is called tryptophan fluorescence assay, which is also a measure of how much the conformation can change when the tryptophan, actually the tryptophan fluorescence is changed when there is a perturbation. So we did the tryptophan fluorescence assay for RAD54, and over a gradient of peptide, the Bloom peptide or the scramble peptide, we saw that when we put in the Bloom peptide, there is a change in the tryptophan fluorescence, indicating that there is a conformation change, but such a conformation change was not seen for scramble peptide, indicating that the Bloom peptide actually causes a conformation change. So what happens in vivo? So next thing which we did was to make a TAMRA tag. TAMRA is a fluorescent dye, a TAMRA tagged cell permeable peptide. The peptide went in. And when we screened for the different proteins, which Ashok has once actually mentioned in the morning about RAD51, which is recombination, along with its twin, of course, RAD54, we see that there is more amount of activity of this RAD51 and RAD54. What does it mean actually? It means that RAD51, RAD54 are more active, and that's why they are helping in the process of DNA repair. That is, in these cells where the Bloom peptide is being put, the cells are undergoing better repair. Remember, these are cancer cells. So what happens to these cells which are undergoing better repair, where there is more repair taking place? So we did the FACS assay. We found out that these cells which are undergoing better repair are undergoing better proliferation. And because of the better proliferation, they are going into the next stage of the cell cycle much faster compared to the scramble peptide. And that is also because CDKIs, the cyclin-dependent kinase inhibitors, the levels of these proteins, the P21 and P27, are much lower in cells which have been treated with the Bloom peptide, allowing the cells to proliferate. So having potentially worked out the mechanism, how this Bloom peptide actually works, we try to understand, we try to ask the next set of questions. The next first question which we asked is, will the proliferative effect of Bloom peptide promote tumor resistance to chemotherapeutic drug? Because proliferation is one of the main reasons of chemoresistance. So we in the lab work mostly on colon cancer, and the two of the frontline drugs which we used, of course, we have tested the other drugs also, as you can see in the bottom, I have written immunotocran, oxaliplatin, we have tested all of them, but we tested in much more detail about the CDTP and CPT. I would like to focus on the red lines and blue lines. As you can see, the Bloom peptide, the blue line actually increased the resistance to camptothecin and cisplatin much more than the scramble peptide. We also saw it in many different other cell lines of colon cancer and also used the different types of drugs. So having done that, we asked ourselves, how does the Bloom enhance the chemotherapeutic resistance to camptothecins and cisplatin? So at that time, we were actually working, trying to actually replace a single nucleotide change. I'm not done anything. Okay. A single nucleotide change, which actually causes the truncation of Bloom in the cancer, in the patient samples. We were trying to actually rescue the Bloom in the patient samples. I will not go into that, and we did successfully rescue it, as you can see it here. From the patient samples which do not have Bloom, we actually rescued that. And we went ahead to do a chipset on these rescued lines. And we saw that the Bloom is present all over the genome. And more importantly, when we zoomed in, we saw the Bloom present on the promoters of the 9 of the 11 efflux pump genes which are involved in throwing away the small molecules which actually cause chemoresistance. So Bloom is recruited to the promoters of these genes, which is also called the MDR genes. We focused on one of the MDR genes, which is called MRP2, but also we have done in parallel in some of the assays, the other MDR genes also. We also created for our sake, because we are looking at resistance. So we created resistance lines, for example, for HCT, for HT29. And we saw that in both these scenarios, the Bloom and RAD54 are present on the promoters of the MRP2, ABCC2, much more in the resistant line compared to the compared to the sensitive line. So having shown that, we again went ahead to do a chromatin remodeling assay, which I mentioned in the beginning. We made another array and we put in now on the MRP2 promoter array, we put in either the bloom or we put in the bloom, and we saw that when we put in the bloom, we saw that there is a chromatin remodeling happening very well. So this bloom now is able to enhance the RAD54 mediated chromatin remodeling on one of the MDR genes, or which is called MRP2. But when we looked at the other MDR genes also, their transcription was also increased. So now that we have found out a mechanism, we wanted to disrupt this interaction to make, now that we know how this chemoresistance is happening, can we disrupt it and decrease chemoresistance and increase sensitivity?
Can we wrap up? Can we wrap in?
Yeah, wrapping up. So we used a Prestic chemical library, 15 minutes, that was the time, right? I'm finishing it up. 15 minutes, so we used a Prestic chemical library and we used luciferase-based protein complementation assay. We found 3 hits which were able to disrupt the Bloom-RAD54 interaction, both in vitro and in vivo. And we also saw that this is because this small molecule actually binds to the RAD54 at its active pocket in nanomolar range, and there were 3 hits. C17 was better than C7 and C3. So we also did the chromatin remodeling assays, ATP hydrolysis assay, ATP binding assays, and all these activities were reversed when these 3 molecules were put in. So can RAD54 disruptors reverse chemoresistance in vivo? First, we saw in cells that they are able to do it. Then we went ahead to the HCT-based xenograft model. When we went there, we saw that there is a decrease. When we are challenging it with the resistant line, we are putting in the 3 molecules. Individually, we saw that the tumor hardly grows. We saw the MRP2 levels actually decrease. It is no longer enhanced because there is no chromatin remodeling. We did it on another colon cancer line, HT29. We did it on a line where there is no 32 amino acid that has been deleted. In that case, there was no such decrease, as you can see it here. And finally, we did it on a CT26 syngenic model where we saw a decrease. So this is the bottom line. I will not go into the model again, and we published it last year. And what next? We are trying to set up with one of the tertiary hospitals a clinical trial, and maybe sometime later, if it's successful, we'll come back. If it is not successful, this will be another example of something working in the lab and not working in the clinics. Thank you.
Thank you so much. Questions from the audience? Yeah, we have 2 questions. And please ask very clear questions to the point due to time restraints.
Yeah. So nice talk. So the chromatin remodelers have a very conserved SNF2 domain or the ATPase domain. So my question is, what defines Bloom peptides specificity to RAD54 and not other remodelers?
Very good question. We were led on by RAD54, but we are doing it on other chromatin remodelers, which are much more well known, especially for the SWI/SNF family.
Yeah, SWI/SNF would be the important.
Then there was a last question.
Hi, nice talk. So since you're working on chromatin remodeling, so have you started on the HDAC inhibitors? Because, or you are only focusing on small molecule based on the structure,
No,
binding
we have
and
not
all?
focused on HDAC inhibitors. Our aim was, even if we had focused on it, it would have been very difficult to do any experiments in human samples. So we wanted to go for a cheap version of by which, because for example, this C17 is taking 800 rupees per month to set up the trial.
So thank you very much. Please stay on stage. We give you a present also. Thank you so much for your presentation.
Thank you, sir.
Please give a huge round of applause for the felicitation of our speaker.
Yeah, Dr. Singhal, congratulations. Then we're already coming to the next. Again, 15 minutes. It's Dr. Ramanandam Manavati from the School of Life Sciences, University of Hyderabad. Please, the stage is yours. Thank you for showing us your data.
Good evening. To start with, I would like to thank the organizer, Prakash, Sudesh Prakash. And today, so I'm going to talk about one of the adapter proteins, hematopoietic pigment impacting protein, HPAP, a driver of phenotypic plasticity, tumor progression, and drug resistance. So this is the picture that I took it a few years ago. The student Sharad left the lab. So he's a graduate student, graduated 2 years ago. And I'm going to talk about the PhD thesis of his work, partly. So we know that cancer is an undaunted enigma. And there are two important questions remain unanswered in the field is that why do majority of the chemotherapeutic drugs fails to cure cancer patients? And second question is that why do a significant percentage of cancer patients develop tumor relapse, tumor recurrence, and metastasis? And the simplest answer to these two questions is that cancer being a heterogeneous disease. And it exhibits both intratumor heterogeneity and as well as the intertumor heterogeneity, spatial heterogeneity, and temporal heterogeneity. So there are different kinds of heterogeneities is found. And it was, Hepner, a few years ago, half a century years ago, mentioned that I'm not worried about the intertumor heterogeneity, which is anyway is common, but I'm worried about the intratumor heterogeneity that is commonly found in the patients. So the heterogeneity can be actually heritable and as well as the non-heritable, and so heritable by the mutations can happen, or non-heritable contributors are phenotypic plasticity and stem cells. So we all know that the Hanahan and Weinberg defined the cancer principles into 6 hallmarks initially, and then later on 4 more hallmarks have been added, and very recently 4 additional hallmarks have been added. So one of these 4 hallmarks is unlocking the phenotypic plasticity. So it is not something that is very maybe new to the cancer biology, but it is not very new to the biology field. So what is phenotypic plasticity? So it is an ability of an organism to change or adapt to the new conditions. There are spectacular examples which have already been known to define the phenotypic plasticity. So a few examples here is the monkey flower plants that is in the left side panel produces the large open flowers in response to long day lengths, small closed flowers are produced. And the second, another example is that a single clone of water flea, that is the Daphnia, can produce either a normal morph or in the presence of predators, a helmeted morph is produced. And the third typical example here is that depending upon the nutrition they receive, the larvae, the leafcutter ants can develop into either a large major workers or a small minor workers. So this typically exemplifies how the phenotypic plasticity can actually influence the animal depending upon the conditions, the stress that they face. This is another example where that Hokkaido salamander will exhibit both prey-induced plasticity and vice versa, the predator-induced plasticity. And they went on to identify the number of genes, the defense genes that actually contribute to this phenotypic plasticity. And not only it is restricted to the animals and plants, but also is observed in the microbes as well. That's, for example, here I'm showing this slide. The E. coli, when it is exposed to the zinc oxide nanoparticles, the rod-shaped bacterium will turn into the spherical shape. So, suggesting that it is actually kind of a universal phenomenon across the various kingdoms of the life. It is observed. So now we are realizing that in the cancers also exhibits a similar kind of phenomenon. And so the fundamental philosophy of the life is that whether it is an animal, plants, or microbes, or a cancer cell, survival through adaptation is common. Okay, so whether it is microbe or plant or animal, so with respect to the phenotypic plasticity, it is also true for cancer cells. So how does plasticities can actually arise, and how can potentially contribute this to the tumor heterogeneity? So that is the fundamental question to be addressed. So we know that a tumor is a complex ecosystem and composed of several biotic factors, including cancer cells and other associated cells. And you can also find abiotic factors. So because there is a internal competition arise among these cancer cells, and the competition is for basically nutrients, it could be for the space and also the oxygen. So one of the prevailing environment in the tumor is the hypoxia. So hypoxia and the hypoxic stress, there is a transcription factor called hippon alpha, which will be stabilized, whereas in the normoxic stress, this transcription factor gets proteolized and will be degraded. So now I'm going to talk about one of the genes that we have been extensively working on that, and which is also be a target of hippon alpha and induced in response to hypoxia. So the gene was discovered in 2000 by Humphrey's lab in Canada, and it was discovered as a protein that is interacting with the PPX interacting protein. And then later we found that it is as a estrogen receptor interacting protein in 2006. And then if you look at the journey that until now there are several labs around the world have actually contributed extensively to this protein, and so this is this particular gene is located on chromosome number 1q21.3, which is amplified in the lung cancers, and it has a very interesting domains like child domains and tubulin binding domains and so on and so forth. And if you look, you can look at the functions that it actually explores in different tissues, and in the dissections of the HPAP functions involves across different kinds of tissues and then different cellular functions and cell proliferation, ranging from cell proliferation, migration, and so on and so forth. So recently, a Chinese group actually showed that it has a role in the osteoporosis as well. So we started working at how hypoxic response regulates the HPAP gene expression, and which in turn contributes to the cell survival. So this data, the experimental data shows that it is a hypoxia responsive gene, and it is dependent on the hippon alpha, and hippon alpha will directly go and bind to its promoter and two different locations, HRE1 and HRE3 elements. And so what? So if the gene is getting induced, how does it is going to contribute to the cell survival? So several hallmarks of the cancer have been tested now in the laboratory by performing the gene silencing experiments, like spheroid formation assays have been conducted, and we have also looked at the apoptosis. See, silencing of the HPAP gene actually compromised its survival ability and promoted the apoptosis. And not only that, HPAP silencing also compromised the invasion and stemness of in the breast cancer cells. And then we also looked into the whether HPAP is required for the breast cancer metastasis, because it is actually controlling the cell invasion and migrations. So we performed experimental metastasis assay in an orthotopic mouse model, and where you can clearly see that the loss of expression of HPAP significantly decreases the metastasis, breast cancer metastasis into the lungs. And what is the mechanism behind this? So we actually looked at the secretome, the proteins which are secreted out from the breast cancer cells upon HPV silencing, and it turned out to be that some of the secretory proteins like MMP9, TIM3, and TIM2s are actually expression have been significantly compromised. And so we realized that how this HPAP could be controlling the MMP9 expressions with our H2 hybrid analysis showed a protein called SRP14, which is involved in the protein translations on the endoplasmic reticulum. And when we knock down SRP14, HPAP mediated MMP9 synthesis had been compromised. So suggesting that MMP9 synthesis mediated by HPAP was actually dependent on the SRP14. And in the normoxic stress, then we looked into the normoxic stress whether HPAP could contribute to the cell growth or not, cancer cell growth or not. So to cut the story short, that we found that HPAP stabilizes the HIF-1 alpha in turn under normoxic stress and can significantly contribute to the tumor progressions, suggesting that under normoxia, HPAP stabilizes HIF-1 alpha and induces the tumor growth, and so which will conferring the Warburg effect. And so we also looked into the whether the hybrid state, EMT hybrid state can be observed in response to the dynamics in the HPAP expression levels when you switch from the normoxia to hypoxia. So we found that from 21% oxygen to the 1% oxygen when we switch the culture conditions, you clearly see that there is a dynamics in the dynamic changes in the HPAP expression levels, and which is actually correlating with the HIF-1 alpha and as well as the other EMT markers. So then we measured the degree of plasticity upon HPAP silencing by quantifying the proliferative index and as well as the invasive index and migration index. So the data clearly demonstrated that the degree of the plasticity upon HPAP silencing was actually very low when the cells were actually in the hypoxic stress upon loss of HPAP. So to support this data, our mathematical modeling also kind of corroborated these findings, showing that when you increase the HPAP levels, the HIF-1 alpha levels will be upregulated and vice versa. So suggesting that there is a kind of feedback loop between the HPAP and HIF-1 alpha enables this kind of plasticity.
Request to wrap.
Just one more minute. And so our clinical analysis of the expression of HPAP and SRP14 and with also correlated HIF-1 alpha expressions in the TNBC samples. So together we are going to propose a model that so there is a reciprocal feedback regulation occurs between HPAP and HIF-1 alpha, which controls the phenotypic plasticity of breast cancer cells in response to microenvironment switch from hypoxia to normoxia. So this work was published in Cancer Letters, and in the energetic stress conditions also, and acute in response to the acute energy stress, HPAP is also being induced, and which ensures the cell survival by operating via glutamine anaplerosis. But when the cells are subjected to chronic stress conditions, so cells will die. So this is a kind of reversible plasticity was also observed in the cancer cells. And this is the others work, like HPAP expression conferring the tamoxifen resistance in the breast cancer cells. And we also observed HPAP resistance in response to the cisplatin in the ovarian cancer cells. And our recent data also shows that it can also confer the resistance to the vaccine. So with this, so how the tumor heterogeneity can arise? So for example, here what I'm talking about, when the plasticity is imposed on a population 1, when the natural selection takes place, which along with the genetic assimilations, probably if the phenotype is fixed in a particular environment over a period of time, that phenotype will be conferred onto the cancer cells. So this is proposed by the genetic Waddington's genetic assimilation mechanisms. So with this, I would like to thank you for your attention. And so I'd like to acknowledge the DBT, DST, and ICMR and other funding agencies for this. So thank you very, very much for your attention. Any questions?
Thank you so much. One short question. We need to move on. One short question. Yes, please. Microphone, please. Microphone. The lady will come. Wait a sec.
Is HPIP conserved during evolution?
It is conserved in the vertebrates, but you don't see that in the non-vertebrates.
Okay. So thank you so much again. A big applause, and please stay at the stage. You will have a present.
Please give a round of applause for our speaker.
So our next speaker is Professor Kumar Somasundaram from Bangalore. The title is PTAR Inc. RNA is an inhibitor of P53 mechanism and biological consequences. Thank you so much. The stage is yours.
Okay, good afternoon. Let me thank Professor Das and Prakash for inviting me to this conference. So I'm going to talk to you about link RNA. We call it as a PTAR, which we show it as an inhibitor of tumor suppressor protein P53. So basically, I will tell you how we identified this link RNA, the mechanism how it inhibits P53, and the biological consequences. So what you see here is actually a tetramer of P53. It's a dimer of a dimer bound to the DNA. And let's see how P53 gets regulated normally. So in the normal cells, P53 levels, when it gets accumulated, it forms a tetramer and binds DNA and activates target genes. Depending upon conditions, it will activate certain genes which will bring about cell cycle arrest as well as programmed cell death. So hence, in the normal cells, P53 levels are always kept very low. Only when there is a stress like DNA damage, P53 gets accumulated, that brings about cell cycle arrest or apoptosis, depending upon this particular situation. But in the cancer cells, P53 gets mutated. The mutation makes the P53 protein levels to accumulate automatically all the time. And the mutated P53 also forms a tetramer, but it cannot bind to the DNA and hence it cannot activate the targets. And the reason being, most of the mutations are occurring in the DNA binding domain. This is what happens in the cancer. P53 gets inactivated because mutations occur most of the time in the DNA binding domain. It just cannot activate transcription. Now, let's go back to the normal cells where P53 is wild type. It's not okay for normal cells to have P53 active all the time. So P53 has to be, the DNA damage response by P53 has to be brought back to the normal. So that is done by yet another target of P53, NPM2, which is a E3 ligase, which gets activated also in addition to the other targets, which eventually degrades the P53 through ubiquitination, and thereby the DNA damage response by P53 is brought to the normal. Cells become normal. So here in this talk, I'm going to talk to you about the identification of a link RNA called PTAR, which binds the 228 RNA, which is a protein coding RNA, thereby increases the 228 levels, thereby inhibits the P53. I'm going to tell you the story behind it. This was done by, this work was carried out by Samarthik. PTAR stands for P53 inactivating 228 associated RNA. Okay, how did we found PTAR? PTAR, we carried out a study and published a few years ago, large-scale screening of regulated link RNAs. From that link RNA, it's highly upregulated in glioblastoma as well as the glioblastoma stem cells. We also found out that it is expressed highly only in glioblastoma, not in other cancers, and it's localized in the nuclei through multiple techniques. And we also show that when you silence, it inhibits the growth of cells, inhibits cells in, arrest cells in G1 phase, induces apoptosis, sensitize cells to chemotherapy. But in the normal cells, the levels are low. If you further decrease the PTAR level, does not have any impact on the normal cells. Now, the point is we need to identify the target, because as you know, link RNAs do not code for protein. How this PTAR works? So basically, we took two approaches. One is to identify bound RNAs by using chromatin RNA immunoprecipitation. Another one is to do
silencing followed by RNA-seq to find out differentially regulated genes. Essentially, combining these two techniques we identified, out of a bunch of 15 selected RNA-bound targets, we chose TRIM28 as a potential target because the gene ontology analysis of the differentially regulated genes showed the idea that Peter could probably inhibit p53. And since TRIM28 has been shown to be inhibitor of p53, we chose to work on TRIM28 as a potential target of Peter in inhibiting p53. And you can see that TRIM28 protein actually binds to MDM2. TRIM28 has an E3 ligase activity. It also binds to DS and because by virtue of its ability to bind to MDM2, it's taken to the vicinity of p53 and it promotes p53 degradation. This has been clearly established before. Okay, and what we now show here, TRIM28. We actually confirm that TRIM28 transcripted protein levels are very high in GBM, and there is a nice positive correlation between TRIM28 and Peter, suggesting Peter is likely to regulate a TRIM28 RNA, thereby TRIM28 protein levels. Further, we also confirm, I'm not going to show the data for lack of time. Peter TRIM28 interaction be confirmed by independent PCR as well as in situ colocalization. And Peter silencing actually reduced the transcript and protein levels. We found out mechanism to be through actinomycin experiments. TRIM28 transcript half-life is going down, suggesting that Peter binds to TRIM28 and promotes its stability and thereby the expression. And where exactly the interaction occurs. So it's a multi-exonic RNA, both of them. So for that, we basically used some online tools which identified the 80 base per region in the last exon of TRIM28 and the first exon of Peter to be the location where the interaction occurs. We used made some clones. First exon was made to express, overexpress, and you can see the sense first exon is able to bring down TRIM28 RNA, but not the antisense RNA or the sense RNA having the 80 base pair deletion. Similarly, if you use actually a 3' UTR loop construct, one can see the luciferase activity from this particular construct can be decreased by the silencing of Peter, which can be reversed by overexpression of Peter. In addition, one can also simple overexpression of first exon can increase activity, but not when you have the 80 base pair region deleted in the first exon. In addition, if you use a TRIM28 3' UTR loop, which is having 80 base pair deletion, such that Peter cannot bind. Now, Peter overexpression is not able to increase that significantly the activity from this reporter. So basically, to suggest that Peter exon first exon is interacting with 3' UTR of TRIM28 mRNA. Now, what is the impact on p53? If TRIM28 has been shown to be inhibitor of p53 already, results so far show Peter binding to TRIM28 RNA increases stability of TRIM28 RNA and protein. So, what is the impact on p53? One would expect that this activity will inhibit p53. Okay, so how do we confirm that? So, what we did is we took a cell line where Peter levels are very high, TRIM28 levels are also high. We silence Peter, one can clearly see the p53 activity is going up without changing the p53 RNA. p53 protein level goes up, p28 protein level also goes up. Similarly, and that can be shown, the data is shown here. I will just skip this. And if you actually overexpress Peter, exactly the opposite happens. Basically, the p53 RNA doesn't change, p53 protein level comes down, and the activity also comes down, the p28 level comes down. This can be further confirmed by overexpressing TRIM28 in Peter silence condition, as well as silencing TRIM28 in Peter overexpressed condition. The phenotype can be exactly reversed to confirm that the whole thing is happening through TRIM28. Basically, Peter inhibits p53 through its interaction with TRIM28. And we also confirm through cycloexcipient experiment, Peter half-life in Peter silence condition is increasing, Peter getting ubiquitinated in Peter overexpressed condition, suggesting that Peter regulates p53 through its interaction with TRIM28. Next, we have so far shown the p53 which is present in the normal cells. The absence of stress is inhibited by Peter when it is overexpressed. What happens when p53 gets activated? p53 levels goes high like crazy. Is that DNA damage induced p53 can also be inhibited by Peter? Our results show that yes, Peter can actually inhibit DNA damage induced p53. Number one. Number two, when next we ask if that is the case, can Peter be also be another molecule like MDM2 thus forming a negative feedback loop? We found out it is not. Peter is not a direct target of p53. On the other hand, we found out DNA damage can directly activate Peter without any involvement of p53. Basically, to conclude, Peter inhibited DNA damage induced p53, and Peter is also a DNA damage inducible link RNA, but in a p53 independent manner. Now, the last few slides. So, what is the impact on this finding on tumor growth, chemoresistance, and clinical relevance? Because what we are showing is Peter, by regulating TRIM28, is regulating the p53 levels. p53 being a tumor suppressor should have some impact on the tumor growth, tumor resistance, and clinical relevance. See, if you have high levels of Peter in the tumor, it will bind to TRIM28 RNA, increase the TRIM28 protein, which will lead to p53 degradation, which means the tumor should grow faster, right? So possibly it should promote, high levels of Peter should promote glioma tumor growth, and it should impart tumor resistance to the tumor, and it will lead to poor prognosis in the patients. So let's see whether all these statements are true. So in the animal model, you can see here, if you silence Peter, on day 7, the tumor size are more or less similar, but day 25, at the end of the experiment, you can see the tumor is completely gone. You can see the quantitation here, silencing Peter inhibits the tumor growth, and you can see the survival is exactly opposite. In silence conditions, survival of the mouse is increased. You can see the big tumor in the control conditions, but not in the silence condition. And of course, the TRIM28 levels goes down in silence condition, Peter silence conditions. On the other hand, if you actually overexpress Peter, it increases the tumor size. Okay, and increase in the tumor size depends on the presence of TRIM28. If you silence TRIM28 and then overexpress Peter, it doesn't increase the tumor growth as much as it does in the control cells. Similarly, overexpression, increased tumor growth also imparts tumor resistance. Tumor element is able to inhibit the growth efficiently here in the control vector, the stable cells, but not so much in Peter overexpressed condition, concluding that Peter overexpression also promotes tumor growth as well as the tumor resistance. Let's come to the last part, clinical relevance. So far I show wild type p53 is inhibited by Peter. That's very clear. If the cells contain wild type p53, it will inhibit if you overexpress Peter. But in the mutated condition, it doesn't seem to have any impact at all. So what's the meaning of this? So if you take the TCGA patients, glioblastoma patients, you can see if you those containing wild type p53 and mutant p53. If our model is correct, high Peter will have an impact on the tumor growth, that is increasing the tumor growth by inhibiting p53. If only the tumor contains wild type p53, that should show a clinical relevance in terms of the prognosis. So you can see here, only in the patients which are having wild type p53, high levels of Peter shows the poor prognosis, but not in full cohort as well as the mutant cohort. So basically, to conclude from this slide, high Peter predicts poor prognosis only in the wild type p53 containing tumor. The model, last 3 slides have been done very fast. I'm saving time for you, Chair. So if you see the model here, a simple model, biological model is, so in the cells, Peter linked RNA binds to TRIM28 RNA, which stabilizes TRIM28 RNA. The high levels, in addition to TRIM28 RNA being made by transcription, whatever is made, the level is increasing further because of increased stability given by the binding by the Peter. That will lead to increased TRIM28. So the TRIM28, along with its association with MDM2, is brought to the p53, promotes its degradation. So MDM2 and TRIM28 together ubiquitinate p53 and effectively degrade p53. That's the biological model. Now let's go to the cancer system. How does this model is applied? In the normal cells, I told you there is some amount of Peter in glioblastoma cancer system where the level of Peter is high. Okay. So what is the significance of that? The Peter will probably bind to some of the pool of part of the subpopulation of TRIM28, and those part of TRIM28 RNA gets stabilized, so the level of TRIM28 increases. That will keep the p53 degraded, keep the check on p53 levels and in the normal growing, proliferating cancer cells. Okay, because p53 level has to be kept low to keep the cells growing. So this is under normal conditions when the cells are growing. And when there is a irradiation in the form of treatment, we all know the irradiation will increase p53 because DNA damage increases p53, which is supposed to induce programmed cell death and kill the tumor cells. But what we show here, in addition to that, DNA damage also activates the Peter levels. We know that Peter is actually an inhibitor of p53 through its association with the TRIM28 RNA. Perhaps high levels of Peter, much more than what is seen before irradiation, will bind to all the entire pool of TRIM28 RNA and make more amount of TRIM28 that will inhibit the DNA damage induced to p53 very high levels, thereby promoting degradation that will lead to chemoresistance. Now, final slide. So this is actually bringing an incoherent feed forward loop, meaning one signal, DNA damage, activates two molecules, p53 on one side to inhibit growth. On the other side, it also induces Peter, which is an inhibitor of p53, thus creating an incoherent p-forward loop. And the last slide. So far I show Peter inhibits wild type p53. But the problem you all know, people have been saying all the time, p53 is mutated in cancer, which means the finding Peter inhibits wild type p53 probably has no relevance when it is mutated, right? But then it is not so. If you look at the cancer TCGA data, it is not mutated in all the cancer, not all of it. For example, pan cancer data shows only 42% of the tumors p53 get mutated. And ovarian cancer, 94% of the tumors have mutated p53, whereas in kidney cancer is only 2.2. What does it mean? In those tumors where p53 is not mutated, other mechanisms of p53 inactivation occurs. Okay, so we show here higher levels of Peter is yet another mechanism of p53 inactivation. In those tumors, p53 is not mutated. The last slide, here you can see the two major tumor suppressor pathway people are shown to be inactivated in most of the cancer. The glioblastoma is no exception. You can see here p53 pathway is mutated in inactivated in about 86% overall, while RB pathway is inactivated in 79%. Let's concentrate on p53 pathway. While 86% of the tumors in glioblastoma has been shown to get p53 gets inactivated by some way or other, but you can see p53 itself is mutated in only 28% of the tumors. The remaining 86 minus 28% is done by either amplification of inhibitor MDM2 or MDM4 or deletion in a large extent, about 61% of TDK2B, which is a 14 kDa protein which binds to p53 prevents MDM2 binding, and we show from this work that Peter by its high level interaction with TIM28, increasing the 28 and TIM28 through its association with MDM2 forms yet another mode of p53 inactivation, thereby adding to the large volume of p53 biology where there is new method of p53 inactivation in tumors where p53 is not mutated. So finally, I thank my postdoc Samarchit Dana who did this work. The other students who contributed are Bhavana, SSP and Mainat, and my collaborators and funding from various agencies. Thank you very much.
One short question. Yes, please.
Kumar, excellent talk as usual. So my question, other than GBM, this Peter, what you have shown. So there is another type of brain cancer called oligodendroglioma. That is a very rare type of brain cancer, and especially is for children. Do you see that the same function of the Peter, what you see in association with p53?
It's applicable in all kinds of glioma. It's also a kind of glioma.
Right.
So it is applicable, but not in other cases.
Okay. Thank you.
Yes, one last question.
It doesn't bind to p53. It binds to TIM28 RNA. So it stabilizes TIM28 RNA. More TIM28 protein is made because of that. TIM28 is the one which is a E3 ligase, binds to not directly to p53, but it binds to MDM2. Through that complex, it goes to the p53 and promotes degradation. It doesn't bind to p53. Even TIM28 doesn't bind to p53 directly.
Okay. Thanks for correcting.
Thank you.
Thank you. Thank you. Next talk is by Dr. Amit Dutt from South Campus, University of Delhi, and he'll be talking about genetic insights into lung cancer resistance to targeted therapy. So, Amit, floor is yours.
Very good afternoon, everyone. Yes. So, thank you to Professor Hidayat Prakash for having me over here and all the organizing committee. I see that we are running late and it is late during the day as well. So I have shortened my presentation to fit in and to the delight of the should be fine, of the chairpersons. For that, so kind of like for sure. Be as brief as it can be. I'm just going to give you kind of like an overview. So this is going to be this is I'm coming from the Department of Genetics, University of Delhi South Campus here in Delhi. However, the work that I'm going to be talking about today, thank you. However, the work that I'm going to be talking about today, a brief one, is primarily has been carried out in my lab at ACTA, Tata Memorial Center, Mumbai. So all the work has been carried out here in collaboration with our chairperson, Dr. Kumar Prabhash. So along with Dr. Kumar Prabhash, we have been working on lung cancer since about a decade now. And what we have been doing is that we began with defining the baseline alterations in lung cancer in Indian patients. And we have made a significant contribution in that direction, whether it is the baseline frequency or mutations in EGFR or KRAS and many other therapeutically relevant alterations. What we find in summary is that those genes which are found to be therapeutically relevant and significantly altered in across the globe and different populations remains to be the same here in the Indian population as well, albeit at a different and altered frequency. What are the underlying reasons for these altered frequency is that we do not completely understand as of today. There could be an ethnicity, there could be etiology, there could be several aspects associated with it. Nevertheless, very recently, a short story that has kind of like come in the lab is while looking along with Dr. Kumar Prabhash and other clinical friends of ours at the Molecular Tumor Board at the Tata Memorial Center, what we found is this. This is a molecular tumor report of a patient, of a lung cancer patient, and this has been taken essentially from the internet. It's a Foundation Medicine report. So what it is kind of essentially doing is that what you find over here is an oncogenic alteration in KRAS, which makes most of the clinicians smile to an extent because they are therapeutic relevant drugs which can be matched to this specific mutations and that can be given to the patient. But what essentially kind of like happens is that it's not possible to kind of take into account in more often than not into the co-occurring alterations that are, and in this case, it happens to be two tumor suppressor gene. So what would essentially happen in a typical molecular tumor board? Looking at this mutation, should the means allow, we would go for a KRAS specific directed therapy. However, these two alterations, which is right there in front of our eye, we would have to ignore for the reason we cannot do much about it. And we also do not understand what it is kind of doing over there and what the significant effect it's going to have in the prognosis or in the outcome to the patient. So it's just left aside. So a graduate student in the lab, Supriya Hayal, what she did is that she goes back to a real world data set that is called as the AACR data set. And she looked into specifically into those patients which were mutated at EGFR. And then along with that, she delineated those patients which were also having the tumor suppressor co-occurring alterations. So what you see over here is that here is the patient who are mutated only in EGFR, and here are the patients who are altered who are mutated in EGFR plus tumor suppressor genes. And what you see is that the overall survival is significantly altered. Even the progression-free survival is significantly altered, and it appears to be that hazard ratio is totally in favor of that. So definitely these co-occurring tumor suppressor genes are doing something more, and then we So along with Dr. Kumar Prabhash at the Tata Memorial Center, we designed an experiment. What did we do? We took a rare set of sample set. Now, this is the kind of like sample set which would not be so easily accessible to majority of the basic researchers, for the reason that what we did is that we followed up this patient who received the treatment, and then when there was a progression of the disease and the patient comes back to the clinic, and then you collect that patient sample again. So here is a baseline sample, and then you also collect a rebiopsy from the same sample. Now that makes that a very rare sample set, because we also had certain other contingencies to it. For example, they were all T790M negative, but that's besides the point. So now the three samples from the same patients were taken, and what did we do? We took a genomics approach. We said, okay, let's go ahead and perform an whole exome sequencing and see if we can find something new. What we were interested in? We were interested in looking for novel therapeutic alterations, and that might be, initially, that's what was our interest was in these patients. And the hypothesis that was initially is that if the co-occurring tumor suppressor genes, if they have to do anything in specific with these mutated, along with the mutated EGFR, what is shown over here? Here are the sensitive cohort, and here are the paid resistant cohort. What did we find when we looked into the tumor suppressor gene? Something very interesting. That was an interesting hypothesis generation. We found that the allele fraction of the mutations in the tumor suppressor gene, when the patient came back, was significantly higher. So what does that mean? We didn't know exactly what it meant. So when we, this is exactly the same, the heat map representation in a more simplified form. These are the different mutations that what we found. They were retained at the baseline and retained when the patients came back. There has to be some pressure. Why a mutation which is happening in such a stochastic manner would be retained over a series of months? When we looked into, we found, as what the heat map showed, that there was an enrichment of a class of gene that we call as the tumor suppressor gene. Now, this made Dr. Kumar Prabhash and myself pretty much excited about it. And what did we do next? Let's go systematically and see if we can add some more value to it. So here, the patients that what we had, a rare set of samples, they were divided in three different subtypes. Here are the folks who relapsed early. They came back within 8 months in the disease, and then here are the ones who are relapsing after intermediate relapse, and here are the ones that were late relapse. When we looked into the allele fraction of specific genes, for example, these were mutant EGFR, and they were also receiving the EGFR-directed therapy. So not so surprising, when they were receiving EGFR-directed therapy, this is the baseline and early relapse, and you would see that there was an increase in the allele fraction of EGFR mutations because these were coming back early. They were not responding to the treatment as much. Similarly, this was a little bit lower in the intermediate relapse when the patient had a late relapse. That means they were kind of partially responding to the treatment to a significant period of time. You see that the allele fraction in the EGFR was down. This was true not only for the mutant EGFR, this was true for P53, and so was it true for even the tumor suppressor genes that were co-occurring, that the allele fraction of these alterations were getting enriched when you were collecting them at the baseline and when you were collecting them after the relapse. So again, we sat onto the table. Now this time, let us bring technology onto it. And let's see if we can change our technology and if we can use a completely different cohort of set and validate this, and if that might be suggestive, anything more of that. So what do we do? Along with the whole group, we decide that, okay, let us find and focus on to let the statistics guide us and allow us to identify those tumor suppressor genes, those were most significantly altered. and we came up with a signature of 17 tumor suppressor gene. What did we do? Now we take the technology and we go ahead to validate our hypothesis with a liquid biopsy approach. This was done in collaboration with One Cell Diagnostics at Pune. And essentially what is happening over here? Here again, there is a bunch of like 25 to 26 odd patients, and these patients were longitudinally blood was collected from these patients. We know the baseline data, and the blood was collected over a period of time to an extent that 243 samples were collected across these 26 patients. And what was done? Then these were analyzed using an in-house comprehensive genomic profiling called as OncoIndex, developed at the One Cell Diagnostics. So, and the analysis was performed in my lab there at ACTRAC. Cutting a long story short, because I want it to be like as short as can be, we performed the QC, because one of the things that you would really want to do that, okay, you're doing a liquid biopsy, but how good are you in the liquid doing biopsy? Are you consistent with what you would expect to find? So what did we do? This is a QC to kind of like show that our concordance or the mutations that what we expected to find, we did find at the frequencies that were supposed to be, which kind of like gives confidence in our own samples. Cutting a long story short, now that what we have done, we have gone longitudinally across different tumor types. And what we are wanting to see, we are wanting to see what is happening to those 17 tumor suppressor gene. So we go ahead and we perform clonal analysis. And in the clonal analysis, we were essentially wanting to look for the truncal clones. Truncal clones are those clones, those are the founder clones, and they remain as it is as the tumor evolves. So that is shown over here. The very interesting part is like here, this is the time point that there is a relapse in this patient, and then you see that there were clones which were positive or they were kind of harboring for the resistant mutation, but that was not exactly the focus. We were primarily interested over here in the truncal clone, and what did we find? That the truncal clone was again enriched in tumor suppressor gene. So, which is kind of like now being consistent, a coherent story that is kind of like emerging up. When we look at the intermediate relapse, again, the tumor suppressor genes were present, but albeit at a lesser number. And similarly, here is how the clonal evolution happens on the patient where there is a no relapse. This patient was a responder, and you see that the clonal evolution is completely slightly different, and so is the tumor suppressor gene profile. Thank you. I will just finish in a minute. This is how quantitatively it looks like. These are the early relapse patient, enrichment of tumor suppressor gene, intermediate, relatively less, and in no relapse, no significant finding of like a tumor suppressor gene alterations. We also went ahead and do the clonal analysis of the individual clone, and we go ahead and we kind of like see how they are kind of like really evolving, but that's besides the focus of like my talk over here today. And what it is kind of like really telling us, it is telling us that indeed these tumor suppressor genes, when they are mutated, and now a clinician would know upfront that if these 17 tumor suppressor gene, any of those are mutated along with the EGFR, they are able to stratify the patient. Stratify the patients who are likely to relapse early, who are likely to relapse intermediate, and who are likely to not relapse at all. And how does that help a clinician? That guides a clinician to decide the treatment regimen that they are offered. Here is a set of patients who can only receive a single small molecule inhibitor that is specifically directed against the EGFR, or you name it, any of those tyrosine kinase inhibitors. And here is a set of patients who are having co-occurring alteration. Let's get more aggressive. Let's also give them chemotherapy along with the targeted therapy. So this is something which is kind of like practice changing, and this evidence kind of like suggested on over there. So and when we look around with these 17 tumor suppressor gene and we look for the survival, we again find that these 17 tumor suppressor gene, the marker that what we have kind of like identified, a signature, was enough to identify those patients who are going to survive poor. But the reviewers were not happy with this. The reviewers said that, no, we don't believe in this. Go ahead, go back and look at a larger data set and go back at an independent data set. You're looking at your own data. So then we now kind of like got back, and hopefully now this should be kind of like getting accepted soon. So here it is about like a 1800 odd patient from MSK. See, and then again here we show a clear signature is that these are the folks who are having a co-occurring alteration and they are significantly different. And right here at the baseline now, a clinician would know it upfront that this patient is likely to follow this route and this patient is likely to follow this route, and accordingly the treatment option can be offered. So this was done by a bigger team at the Tata Memorial Hospital and my laboratory at ACTRA. These are the people in highlights who have kind of like actively contributed onto it. My laboratory has always been well funded by the Tata Memorial Center, by the DBT Wellcome Trust India Alliance, DBT VNCI, SERB, DST, Terry Fox, Tata Innovation Funds, Fellowship, and more recently by the ICMR. Thank you very much. I hope I could stick on to the time, and I should there be time at the end.
Two short questions. Yeah.
Thank you very much.
Yes, yes sir. I will come to you. Yeah. Yes, go ahead.
Thank you very much. I have just one small query because the baseline, written, and the relapse one you have classified down, but you have to mention that is the treatment parameter. It's a single treatment parameter. Yeah. Even mutation to mutation, the treatment parameter also differ. So how you have taken the clear conclusion about that?
So what defines the baseline, the patients those are, they are primarily mutant for EGFR, irrespective of the treatment that they were kind of like offered, and they were all offered EGFR-directed therapy. So were those patients also offered chemo along with them? So that's something that systematically that we have not looked for. As yet, what we know as a single agent EGFR-directed therapy is being offered onto the patient, so is the outcome.
Dr. Amit, just two quick questions.
Okay.
So that EGFR mutation, what you see in NSL, non-small cell lung carcinoma. So EGFR also gets tyrosine phosphorylated. So the mutation, what you see, is it hinders the phosphorylation of that EGFR, or these mutation they are distinct and different than the tyrosine residue
so
of
what
EGFR?
we know today is that somewhere around to the order of 20 to 30 different point mutations or different kind of mutations, compound mutations that affects EGFR. We know that they are differentially activating the downstream phosphorylation of not just the EGFR per se, but also the downstream signaling. So the strength of activation of different mutations are found to be in groups to be like distinct. We know that depending on the kind of like exon, which is where the mutation.
And second quick question, this next generation of TKI, there are many TKI, they are in the clinical trial. So if you use some of those TKI, do they repair the mutation status of this EGFR?
Sorry, do they?
Repair the mutation.
Perhaps repair, I'm not exactly sure how would that happen if so. Yes, they do eliminate them. We know that the clones which are positive for EGFR mutation, if they receive erlotinib or gefitinib in particular, or even osimertinib, which is a second generation, as what you already alluded to, they do eliminate those clones which are positive for those mutations. And if we would sequentially follow them up, you will see that there is a depletion, or as what we showed, that there was a decrease in the allele fraction of those specific mutations, and also those clones get depleted.
Thank you.
Okay, Amit, you want to go first?
Good question. Great talk.
Thank you.
One thing is that we noticed it's known in the clinic that the LA58R mutations actually do poorly than the exon 19 del. And that's seen in the osimertinib data. It's also seen in your data. It's interesting, all the early relapses are there. Is there a different co-mutation profile with those two different genotypes?
So that's an interesting question. We are working on to it. We are looking at the mutation-specific co-occurrence and the mutation-specific co-occurrence if it has an invariance on a site-specific metastasis as well. Those are still under transition, so I wouldn't kind of like comment on to that, but that is something under actively that we are looking at.
Amit, a good talk and good study. Often people are shown recurrence or relapse for EGFR inhibitor therapy is associated with the additional mutations in the EGFR, making them not sensitive to the inhibitor anymore. Have you found such mutations in the EGFR in your patients? The relapse has occurred?
So I did allude to it, but I kind of like very tangentially mentioned about it. So there are, yes, you're absolutely correct. There are 4 different mechanisms. One of that mechanism is, known mechanism is that the second mutation in the same EGFR molecule. And what I alluded to is a mutation called as T790M. So this T790M is a secondary mutation that it what kind of like accrues. What we did is that when we were recruiting these patients, and that's why I call them to be a rare set, they were all T790M negative, so that we can enrich our population for those mutations other than the known, which T790M occurs at 50% of around 50% of these resistance that kind of like relapses. So you're well spot on that the secondary mutation does happen. Our sample was T790M negative, and from so that makes our sample set more rare.
So thank you, Dr. Amit.
Any more comments from your side?
No, thank you so much, and privileged to work with you.
I would request Dr. Prakash and Dr. Tanveer sir to please felicitate our second chairs. Dr. Vishwas, please join us on the stage.
Sorry for one quick amendment in the program. So it's the next keynote session speakers. Please restrict your talk for 30 minutes because of the time constraint. Yeah. Thank you. It would be very, very kind. Thanks. Yeah, Denny, this is just a note for you. Yeah, of course. They are online. They will. That's something for you.
So I would like to invite Dr. Kumar back to the stage and Dr. Flats as well.
Okay.
Requesting Dr. Kumar, please join us on the stage. Thank you. So now we proceed to the keynote lecture. The chair for the session is Professor Danny Welch, and he is having his career highlights with significant contributions to advancing oncology study. This session is also chaired by Professor Gopal Kundu. Gopal Kundu sir is basically the director for R&D at KIT University and holds academic positions in both biotechnology and medicine. I welcome you all to the stage, sir.
And we'll get started since we're short on time. It's my pleasure to introduce Dr. Luca Gattinoni from the Leibniz Institute for Immunology. He'll be talking about counteracting T-cell exhaustion, T-cell therapy meeting organelle medicine. He's a graduate from the University of Milan School of Medicine with medical oncology residency at the National Cancer Institute, also in Milan. He did a postdoctoral training at the U.S. National Cancer Institute, was a staff scientist, Stodman investigator there, and he's been chair of the immune cell modulation at the University of Regensburg, and currently directs the Division of Functional Immune Cell Modulation. Dr. Gattinoni.
Thank you very much for the introduction, and thank you to the organizer for inviting me. Sorry I could not be there in person, and I'll try to be short and try to recover the time that was lost during the day. For today talk, I would like to speak with you about a recent story coming up from our lab, where we are trying to counteract the problem of T-cell exhaustion using mitochondrial transfer technology. So as you probably know, one of the major hurdles that characterize and face T cells once they invade and infiltrate the tumor bed is the loss of mitochondrial content and impairment in their function. And this is as a result of the environmental problems that the T cells encounter, that like an hypoxic environment with accumulation of noxious metabolite and nutrient deprivation. This cause dysfunctional mitochondria content with loss of mitochondrial mass, depolarized mitochondria, loss of biogenesis, and increase in ROS and PAU. Ultimately, Ultimately, this lead to a reprogramming, epigenetic reprogramming of the cell, and an exhaustion profile with the cells that lose the proliferative capacity. They are unable to display cytotoxic and effector function, and upregulate a variety of inhibitory receptors that are typical of the exhaustion. In addition to this, recent work has found out that cancer cells can actively sabotage T cells through mitochondrial transfer mechanism. On one hand, they can siphon in healthy mitochondria from the T cells in order to support their metabolic needs and needs for growth. And at the same time, they are also depleting healthy mitochondria from T cells. On the other hand, they are also able to donate their dysfunctional mitochondria to T cells, so that the T cells get a further impairment in their function. So we sought to leverage some of this intercellular mechanism really to promote metabolic function in our T cells and equip them with exogenous mitochondria that could be used to obtain better immunotherapy. There are different mechanisms of intercellular mitochondrial transfer that have been described in the literature. The one that is most studied is the tunneling nanotube mediated mitochondrial transfer. Essentially, the cells form a bridge, an intercellular bridge, using this tunneling nanotube through which mitochondria can travel from one cell to another. But they can also travel through cell adhesion mediated membrane adhesion mechanism, through gap junction, and also through dendritic structure mediated. Furthermore, also the mitochondria can be released naked or free mitochondria, or within extracellular vesicles, and then uptaken by an acceptor cell. So for our purposes, what we set up was a co-culture of T cells with bone marrow stromal cells, which has been a cell type that has been frequently described in the literature as a very good mitochondrial donor cells. And the first things that we did was to understand whether we could, during this co-culture, we could observe the presence and the formation of tunneling nanotube between T cells and bone marrow stromal cells. And indeed, we could observe this in using both human and mouse co-culture setting. Here shown with the arrow are some example of this intercellular connection. And interesting also, if we go along the nanotube connecting mitochondrial mesenchymal stromal cells and T cells, we can see some enlargement of the nanotube, indicating a potential presence of organelles trafficking along this nanotube. If we measure the size and the length of this nanotube, generally the murine nanotube are shorter and thinner compared to the human one, which show a more distributed variety across both length and depth. So what we were observing was a connection between the two cell type, but we weren't sure now if there was a transferring of mitochondria happening from mesenchymal stromal cells and T cells. And to monitor this, we generated a bone marrow stromal cell donor line in which the mitochondria were tagged by a fluorescent protein DS-red, so we could monitor the presence of mitochondria by confocal microscopy. And in this picture, we can see again a nanotube highlighted by phallodyne green staining, connecting a large bone marrow stromal cells with a small T cells on the top. And what we can see along the tube, like I showed you before in the electron microscopy picture, there are this enlargement, structural enlargement. And inside the structural enlargement, we can see all this red signaling indicating the presence of mitochondria. And if we hypersaturate the DAPI staining in the area of the nanotube connection, we could also detect DAPI signal within this pocket, this red pocket, indicating the presence of DNA, and this is compatible with the presence of mitochondrial DNA traveling along with the intact organelle. So we spent a lot of time in our lab to try to optimize the co-culturing system in order to see robust transferring rate between mitochondrial stromal cells and mesenchymal stromal cells and CD8. And we came up with a setting in which we co-culture both cells inside a transwell in order to have the mesenchymal stromal cells at the bottom of the transwell that are bathing in their own media, while the T cells on top are preferentially bathing in the T cell media to maintain higher viability and better mitochondrial transferring potential. What we found out was around 10% of the CD8 cells after the co-culture acquire DS-red signaling. And we can easily sort this population by flow cytometry and have a pure population of DS-red positive cells that we will call mitopositive cells, so cells that acquire mitochondria. And their counterpart are CD8 cells that did not uptake the DS-red signal. And if we measure the mitochondrial DNA content in this two subset, sorted subset, we can see an increase in mitochondrial DNA about 30% more on average in mitopositive cells compared to mitonegative population. We wanted to be more strict and check really that the mitochondria that were transferred were really internalized. So we perform additional confocal microscopy on sorted cells and show that mito-DS red signal is indeed internalized within the CD8 on the cell surface membrane of CD8 T cells. And by staining cells also with mito-D red dye, we could observe the and confirm the presence of healthy mitochondria and show that co-localization of the two signals, indicating that really the transfer mitochondria are real. We did this also genetically and took advantage of a SNP present in the mitochondrial DNA that can distinguish C57 Black 6 strain from bulb C and allow the presence or absence of an ASP1 restriction site. So we set up this co-culture, mixed co-culture, in which we use bone marrow derived stromal cells derived from C57 Black 6 and CD8 from bulb C. So you can see in the bulb C setting, the SP1 restriction site is lost, and there is only one band that can be detected at 385. In the donor population, we can see two bands due to the activity of SP1. And in the mitonegative population, the cells that do not uptake mitochondria have the unique 385 band similar to the original CD8 that were co-cultured. But in the mitopositive CD8 T cells, we could observe all the three bands. So the endogenous bulb C mitochondrial DNA, plus the two bands derived from the mitochondrial DNA derived from the Black 6 donor cells, indicating also providing additional evidence that we were really transferring mitochondria. We perform also CLEM studies and show that the DS red really co-localize with mitochondrial structure within the cells, cytosol of T cells, and is not diffused in the cytoplasm. And the mitochondria show normal morphology with crystal, with the presence of crystal inside. So to test the impact of this transfer on T cells, we need a strong and careful control because of course once you co-culture two cell type and this tunneling nanotube form to connect one cells to the other, not only mitochondria can transfer between one cells to another, but other cytoplasmic factor molecules, RNAs, other organelle type. So to measure the downstream function in CD8 T cells and to be sure that the effect was due to mitochondria, we need a good control. And to do this, what we established was a bone marrow stromal cell line that was treated with ethidium bromide for several days at low doses to induce mitochondrial DNA damage. In this case, you can see that the bone marrow stromal cells treated with ethidium bromide still retain DS red, so this mitochondria can be tracked from one cell to another. But if we look at the functionality of this mitochondria at the polarization status of this mitochondria by using the dye mito-deep red, we can see that the mitochondria in ethidium bromide treated cells are dysfunctional. So the dye doesn't stain well, is only punctuated. Furthermore, we confirm a loss of mitochondrial DNA by qPCR by measuring MTCO2 quantity. And we further showed that the mitochondria in ethidium bromide treated stromal cells are dysfunctional, performing a C-HORS assay and measuring oxygen consumption rate in the cells. So here we clearly show that the bone marrow stromal cells have normal respiration and with high spare respiratory capacity, but if they are pretreated with ethidium bromide, this mitochondrial respiration activity is almost completely abrogated. So we had this control. And so in the following experiment, what we did was to test the mitochondrial respiration in recipient CD8 T cells using all this variety of control. And we show that in red here, the mitopositive cells, so the CD8 cells that acquire mitochondria from healthy bone marrow stromal cells, have higher basal respiration as well higher spare respiratory capacity compared to all the other control. Compared to the cells that do not uptake mitochondria in gray, CD8 T cells that have never been co-cultured with bone marrow stromal cells in black. And also when we look at the cells that receive mitochondria but from a dysfunctional donor cells that was treated with ethidium bromide, this benefit in metabolic activity and mitochondrial respiration was lost. So indicating that the improvement in mitochondrial function that we observe in mitopositive cells is depending on the transfer of mitochondria and not other factor that could have been traveled from one cell to another. When we transfer these CD8 T cells in a melanoma model using the PML-TCR transgenic model system, what we saw was that both mitochondria positive and mitonegative population were able to induce a regression of B16 melanoma. However, the mitochondrial negative population could control tumor growth only for a limited amount of time, and the tumor started regrowing after 3 weeks after transfer, while the mitopositive cells were able to induce a more profound and prolonged control of B16 melanoma. And this resulted in a prolonged survival of the animal. But how this is working in vivo? So, and what are the main effects of having in adaptively transferred cells with higher content in mitochondria? So the first things that happen is that these extra mitochondria boost a better expansion of the T cells in the entire animal. So this is our data from the spleen showing higher frequency of mitopositive cells in the animal after transfer compared to mitonegative group. When we look at the tumor bed also, we found higher numbers of mitopositive cells compared to mitonegative cells at the tumor site. And what was interesting to see also by confocal here is that the mitopositive cells, so cells that receive this exogenous mitochondria, were more able to migrate deeply inside the tumor tissue, while the mitonegative populations of T cells were restrained outside the tumor, at the edge of the tumor seems to accumulate. So the extra mitochondria really confer an advantage of mitopositive cells in their ability to infiltrate deep into the tumor tissues. When we look at the metabolic function of T cells at both spleen and the tumor site, what we found out was that mitopositive cells also retain a higher metabolic activity. And to do this, we perform a single cell flow cytometry based assay using puromycin as a readout for metabolic activity. So essentially, during protein translation, if we provide puromycin, puromycin can be incorporated into the protein and stained by flow cytometry. And since the majority of the ATP produced by a cell is dedicated to protein translation activity, we can have a surrogate readout for overall metabolic function of T cells. And indeed, in the spleen, there was a trend for higher metabolic and protein translation, but in the tumor, this reached significance, indicating that the effect of extra mitochondria and the benefit provided by extra mitochondria are continuous in the time, and they are not lost early after adoptive transfer. We wanted to see also if the cells receiving mitochondria could undergo genetic reprogramming. And what we did, we performed a single cell RNA sequencing here in the tumor bed. We could detect 4 major clusters from 0 to 3. And if we look in the mitonegative group of animals, we can see an accumulation of cells and higher concentration of cells in cluster 3, while the mitopositive cells, not only there were more cells retrieved from this animal, but also tended to cluster more in the cluster 0, 1, and 2. And so what this cluster represent? To do this, we took an unbiased approach, and we map our single cell RNA sequencing on a TIL atlas that comprise 16,000 over 16,000 single cell transcriptome derived from both B16 melanoma and MCA38 colon adenocarcinoma. And what we found out was that the mitonegative positive, as I showed you before, they cluster more in cluster 3. And this cluster is mostly comprised of exhausted cells, either the terminal exhausted cells in blue or the precursor exhausted in orange. While the mitopositive cells were more enriched in all the other cluster. Of course, there were also in mitopositive cells some precursor and terminal exhausted cells, but a large fraction of the cells were highly proliferating effector cells, here in purple, and also strong and highly functional effector shown in red in cluster 0. And we confirm this also by flow cytometry, and this showed that in cluster 3 there are more inhibitory molecule like PD1, LAG3, and TIM3. If we double stain PD1 and LAG3, we can see in the mitonegative population a higher frequency of these terminally exhausted cells compared to the mitonegative population. On the other hand, the cluster 0 was enriched in effector molecules like granzyme B, A, Fas ligand, and by flow cytometry we were able to show that mitopositive cells also contain higher frequency of cells that were PD1 low intermediate, expressing high level of granzyme compared to mitonegative cells. So we wanted to move this concept also toward the clinic, and so we started testing this platform on human T cells. And what we did first was a CAR T cells. We use a CAR T cell platform using a CD19 CAR T cells. We show here in the left that the presence of extra mitochondria in mitopositive cells enable CD19 CAR T cells to kill more efficiently target NALM6 cells in vitro. And this I10 killing capacity is lost if the mitochondria that the cells receive are coming from an ethidium bromide treated donor. Here, the mitopositive ETBR in white. We also perform a repetitive killing assay in vitro and show that mitopositive cells were able to eliminate completely NALM6 leukemia cells after repeated round of stimulation, up to 6 rounds of stimulation. There was an entire killing of the target cells, while the control cells, the mitonegative population, were initially able to treat tumor very efficiently. Starting from the 3rd round of stimulation, they start losing cytotoxic activity, and by the 6th round of stimulation, they were all dysfunctional, and this across all 3 donors tested. We move these cells then into an in vivo model using an NSG animal carrying NALM6 leukemia that is expressing luciferase, so that you can see the tumor burden of the animal by luciferase. And we could observe that, again, here in vivo, the mitopositive group was able to control the leukemia burden more efficiently than both the mitonegative and the CD8 that were never co-cultured with bone marrow stromal cells. Lastly, we sought to evaluate the mitochondrial transfer platform also for therapy involving the use of TILs, tumor-infiltrated lymphocyte. So we co-culture our bone marrow stromal cells with mitoDS red, with TILs that were characterizing for having high specificity for the tumor-associated antigen MART1. And we could see also in TILs transfer rate around 10%. And when we look at the ability of TILs in killing melanoma target cells, we could observe an increased capacity of mitopositive cells to eliminate melanoma tumors using both immortalized bone marrow stromal cell donor, but also when we use primary bone marrow stromal cell donors. Lastly, we could observe around 10% rate of transfer, but for clinical translation, this level I think there will be still insufficient to move this technology to the clinic. So we wanted to understand more the mechanism of transfer and to find the potential molecule that could be targeted to in the future to improve the transfer rate. So we did, we sorted mitopositive and mitonegative cells in both human and mouse setting. And what we observed that molecules involved in focal adhesion and membrane protrusion, like TALIN2 and LPXN, were highly upregulated in mitopositive cells in both settings, mouse and human.
Dr. Gunn, you have about 1 minute, please.
This is the last slide before the conclusion. So we knock out TALIN2 as a proof of principle, and essentially we show that in the TALIN2 molecule is important for really establishing this tunneling nanotubule connection and have a mitochondrial transfer on both cell sides. So when it's knocked out from CD8, we have an impairment. Also when we knock it out on the bone marrow stromal cells, the impairment even is more severe. If we knock out the TALIN2 on both CD8 recipient and bone marrow donor, we have further decrease of mitochondrial transfer. So to summarize the talk, here is cartoon, we see, the T cells are fighting jet, and the bone marrow stromal cell as air fueling tanker, so that can connect with T cells and donate their mitochondria, improving their functionality and fighting ability for cancer. And with that, I would like to thank all the people involved in the study, especially Shiladita Sengupta, a strong collaborator that provided the electron microscopy and confocal picture, Donato Inverso and Matteo Iannacone for the CLAM study, Kilian Schober for the Senate metabolic assay, and the most important person for sure is Jeremy Baldwin in my lab. Is a highly dedicated postdoc to the project. He moved across continent from US to Germany to follow this project in the middle of COVID pandemic, and thanks to him, I was able to tell you this story today. Thank you very much, and I'm ready for questions if you have.
Let's think, Doctor. We have time for one short question.
Hi, Luca. This is excellent talk. So, talin is expressed in the immunological synapse, and also it can influence the serial lysis of CAR T cells. So, have you, what do you think about, those mitochondrial transfer and its consequence to immunological synapse of CAR T cells?
So we didn't investigate the impact on talin-2 on the establishment of immunological synapse. What now we use in this co-culture system is really to allow CD8 T cells to acquire extra mitochondria from a donor bone marrow stromal cells. After that, the cells are put in another context of transfer in vivo, tested in vitro with tumor target cells. We don't know if we are going to manipulate talin-2 expression on CD8 T cells. If we could, in a permanent way, we could also have some issue with the targeting of tumor cells. So if now talin-2, for example, overexpression might be more important to boost the transfer rate, given the role of this molecule also in T cell immune synapses, it probably will be better to modulate and modify this molecule on the donor cells and not on the T cells counterpart, in order to have a T cells that is functioning properly in the future.
Thank you very much for an interesting talk. We have to move on to the next one.
Thank you very much.
Thank you so much.
Bye-bye.
Thank you. Our next speaker, Dr. Keith Knudson. He is from Mayo Clinic, Jacksonville, Florida. And Dr. Keith is a professor of immunology with primary and joint appointments as a consultant in the Department of Immunology, Clinical and Research Laboratory, Biology. He holds PhD in pharmacology from University of Georgia, BS in microbiology from University of Washington, Seattle, and AA in business administration from South Seattle Community College. He completed postdoctoral fellowship at the Division of Medical Oncology, University of Washington, and Department of Medicine, University of British Columbia. Dr. Keith's research focuses on the immunology and immunotherapy of breast and ovarian cancers, spanning basic immunology, clinical translation, and clinical trial. Dr. Keith will be talking today on ex vivo engineered dendritic cell cancer vaccines. Dr. Keith, please, over to you.
Keith, you're on mute.
Okay, can you hear me okay?
Yes, we can. Thanks.
Oh, good.
Are you sharing your screen?
Yes, it is. Let's see. Should
We're on
be.
your disclosure slide.
Oh, good.
Okay.
Okay, so thank you for the opportunity to speak with you today, and I hope you can see the full screen slides and hear me okay. I'm broadcasting from southern Florida today. And I want to talk about ex vivo engineered dendritic cell vaccines. A few disclosures I can speak to in more detail if needed. First of all, let me tell you a little bit about the Mayo Clinic Cancer Vaccine Program. It's a robust program that we've developed over the past 10 years, evaluating a number of different vaccine approaches that brings together a number of individuals across a spectrum of different expertise at Mayo Clinic in Florida. We have a number of different individuals that range in terms of their expertise that assist with development of computational immunology, vaccine discovery, vaccine formulation and manufacturing, clinical trials, and immune monitoring. And that's my acknowledgement slides of all the important individuals that are associated with this program. So the cancer vaccine program at Mayo Clinic initially developed by developing vaccines to treat early stage disease to prevent relapse, but with newer technologic and developments and innovations, we've been starting to evaluate vaccines in the metastatic setting as well as in the prevention setting as well. We have a number of clinical trials ongoing now. I'm going to talk about essentially just two of those in the context of dendritic cell vaccines, but we have a number of other types of approaches, such as peptide-based approaches, nucleic acid-based approaches, as well as viral approaches and nanoparticle approaches for the treatment and prevention of cancer, mostly focused on breast and ovarian cancer. Today, what I want to talk about is ovarian cancer and the approaches that we're taking to combat ovarian cancer. So worldwide, there's 313,000 cases per year. And as you can see, there's 207,000 deaths per year. So it's a disease with a high rate of mortality, and there hasn't been much in the way of improvements of therapies for ovarian cancer over the past couple of decades. And the primary reason, of course, that the mortality rate is so high in ovarian cancer, of course, is that it's diagnosed in very advanced disease, usually stage 3 and stage 4, where it's very, very difficult to manage. So we've been very much interested in looking at the development of a variety of immune-based approaches for the treatment of ovarian cancer. And there's considerable rationale for the development of vaccines, which we've been moving forward to the point of phase 1 and phase 2 clinical trials now. And some of the rationale is listed here. Certainly, we know that pre-existent immune responses are associated with improved survival. We've known that for over 20 years now. This is an example of data from George Kukos' laboratory that was published in the New England Journal of Medicine in 2003 that shows that elevated levels of T cells in the tumor are associated with much improved survival in patients with ovarian cancer. We also know that patients develop immunity to multiple tumor antigens, and those are, of course, potential targets for vaccine, and that pre-existent immune responses are linked to better responses to conventional therapies. So there's a number of different experimental studies that have really positioned us into thinking that immune-based approaches may be effective in ovarian cancer once we untangled the ovarian cancer microenvironment so that the immune effectors that we generate with the vaccine can be potentially effective. And despite the fact that there is elevated T cells in some patients, and those are associated with improved survival. Certainly, we know that the tumors grow out, and there's a number of reasons why they grow out, and perhaps dominant among those are regulatory T cells that infiltrate into the tumor microenvironment. This is an area that we've done many studies over the past couple of decades that have shown that high levels of regulatory T cells are associated with much worse survival in ovarian cancer patients. There's other mechanisms, which I'll talk about a little bit later, that also suppress the immune response, but certainly at first diagnosis in a number of patients, or a high fraction of patients, regulatory T cells appear to play the dominant role in immune suppression. So our interest has been to target CD4 T cells due to really, how we're positioning ourselves for treating patients with ovarian cancer, and that is preventing largely disease relapse after conventional treatment. So individuals with ovarian cancer, as I had mentioned, are diagnosed at stage 3 and stage 4 and undergo surgery and chemotherapy. And for the most part, most patients respond with a complete clinical response to those therapies, but the large majority of them, ultimately relapse, about 85 to 90%. So what we want to do is we want to intervene at, the point after patients have completed conventional therapies to prevent relapse. And we've been very much interested in targeting CD4 T cells due to their central role in the development of the anti-tumor immune response. So CD4 T cells orchestrate the development of immune responses, not only in cancer, but infectious diseases as well. And they are capable, due to secretion of a wide variety of cytokines, activate other arms of the immune system, such as cytotoxic T cells, which can directly kill tumor cells, as well as activation of B cells that lead to the production of antibodies, which may result in antibodies that could make the tumor look more foreign. Another reason too is that we're interested in targeting CD4 T cells is that ovarian cancer tends to show up very late in life, with a median age of around 65 to 70. And it's at that point where the naive CD8 T cell compartment in individuals, because of age, significantly declines, which is in contrast to CD4 T cells, which is a stable population throughout life. Now, what we know from decades of researching CD4 T cells is that there's multiple subtypes. And this is always a matter of debate, but the well-recognized subtypes of CD4 T cells are Th1, Th2, follicular helper T cells, TFH, and Th17, with a lot of interest in another subset more recently, and that is Th9 T cells, which also may have anti-tumor activity. So the approaches that we're taking are focusing, as I'll get into, Th17 T cells, as they seem to be effective in combating ovarian cancer. And another reason too is ovarian cancers express high levels of MHC class 2 molecules. So if you'll recall from basic immunology, CD8 T cells recognize peptide complex on MHC class 1 molecules, which is a prime target for many different types of cancer and vaccines and other types of immunotherapies. In ovarian cancer, MHC class 2 is expressed very high and is the target for CD4 T cells. This is example data published several years ago in PNAS showing that ovarian cancer tumor cells express high levels of MHC as well as high levels of, or class 2, as well as high levels of MHC class 1 in the tumor microenvironment. So there's a lot of data that would support the development of CD4 T cell, CD4 helper T cells in combating ovarian cancer. So there's a number of ways that we think about the development of vaccines for targeting cancer. A lot of emphasis today is due to the fact that we can, sequence rapidly tumors is targeting neoantigens. This wasn't the case several years ago when we were developing vaccines where we have been limited to the targeting overexpressed self-antigens. And the rationale for targeting overexpressed self-antigens, something that goes back into the early 1990s with a number of different discoveries that as tumors grow, they overexpress a number of different proteins. We can identify what those proteins are, but what's relevant here is that the overexpression leads to the presentation of subdominant epitopes that are not ordinarily expressed in MHC class 1 or class 2 molecules at the cell surface. So this is just an example showing the blue epitopes that are dominant under normal expression of proteins in the cell, and then you have overexpression, deregulated localization of tumor or proteins in the tumor microenvironment that lead to upregulation of subdominant epitopes, which we can identify. So we've been very much interested in evaluating vaccines to folate receptor alpha. This is just a collection of data from our lab and other laboratories that have shown high level of overexpression of folate receptor alpha. It's normally expressed very compartmentalized in the body, with some expression in the kidney and some expression in the choroid plexus. This is normal expression in the kidney that's shown in the upper right here, shown on the proximal tubule. In ovarian cancer, it's expressed at very high levels, and it can be found being secreted into the bloodstream. It can be found in the nucleus. It can be found in the cytosol. Normally, it's a cell surface protein that's involved in capturing folate so that your body doesn't become deplete of folate and putting that folate back into the bloodstream. So this seemed like a viable candidate to us for identifying potential epitopes, and we developed work streams that we are able to identify what we call degenerate subdominant epitopes, and we do this using bioinformatics to parse out the different epitopes that may be present, and then we conduct MHC class 2 binding studies, T cell activation studies, and then we narrow down a long list of epitopes based on natural pre-existent immunity in patient population. So you can see here data from our Journal of Clinical Oncology paper back in 2006 showing that patients can have elevated levels of T cells to the folate receptor alpha epitopes that are shown here with the arrow. And we can look at binding studies too and show that these bind to various HLA class 2 molecules. And we can also see that the epitopes that we've chosen, just based on the processes that we've developed in the laboratory to identify those epitopes, bind to multiple different subtypes of HLA class 2. And so are degenerate in that sense, so we can use those in a broader population. So we've developed tools that can be used to target these particular epitopes in individuals. And we first went into phase 1 clinical trial showing that this could be safely done, which was the first of its kind. And this was published back in 2018, that we could take these to generate epitope vaccines and generate immunity in patients with breast and ovarian cancer. You can see the epitopes are here in the box, and we can induce with a course of vaccination over the course of 6 months immunity to these folate receptor peptides that ultimately lead to the generation of immune responses that can recognize naturally processed antigen in the tumor microenvironment. So the overall findings from the studies, we generated immunity. Immunity was durable. The vast majority of patients developed immunity to folate receptor alpha. There was no safety concerns despite the expression in various tissues at lower levels. And so this was a peptide vaccine, and really paved the way for us to try to understand how we could apply this in the future to improving survival in ovarian cancer patients. But we didn't really want to stop there and use a peptide vaccine, largely due to a number of pieces of data. One that I showed you previously, which is that regulatory T cells were a dominant immune suppressive T cell in the microenvironment. And data here from Wei-Ping Zhu's laboratory back in 2009 showed that individuals that had high levels of IL-17 in the tumor microenvironment, indicative of high levels of Th17 T cells, so one specific subset of CD4 helper T cells, had greatly improved survival relative to those individuals that had lower levels. And what was important from these studies is that there seemed to be a reciprocal relationship between the numbers of Th17 T cells in the tumor microenvironment and regulatory T cells. So we wanted to start structuring our program so that we would specifically tailor the vaccines to generate Th17 T cells, which seem to be, from at least the preclinical data, associated with better outcomes. And so about that time that data was coming out, Martin Cannon, our collaborator, had published in Cancer Immunology and Immunotherapy that using engineering ex vivo dendritic cells with p38 MAP kinase inhibition coupled with IL-15 co-stimulation of monocyte-derived dendritic cells, he could elicit Th17 T cells ex vivo, or in the culture dish. And so we worked with Martin to identify an optimal p38 MAP kinase inhibitor, coupled that with IL-15 co-stimulation and the regular recipe of generating dendritic cells ex vivo to come up with an approach that we could show in animal models was effective at specifically inducing Th17. And so interestingly, so when you block p38 MAP kinase and co-stimulate with IL-15, that suppresses IL-10 and IL-12. And so, number one, you don't get regulatory T cells that are induced by IL-10, and you also prevent or down-modulate the generation of Th1 T cells as a result of reduced levels of IL-12. And as you can see here in the right-hand part of the slide, this resulted in the generation of dendritic cells that could be used in vivo in mouse models, in this particular case, to drive specific IL-17 production, which we've captured here with an ELISA, but certainly we can see that with a wide variety of other techniques. And this IL-17 was largely in vivo, the result of activation of Th17 T cells. As you can see, that we eliminated CD4 T cells with an anti-CD4 T cell antibody that's shown here, and we could eliminate the increased IL-17 production that's associated with vaccines. So we were confident that we could moved that forward into survival studies and asked the question whether or not this was superior to standard DC vaccination approaches that are routinely used in the clinic. And this is an animal model of ovarian cancer where animals are treated with Th17 DC vaccines here shown in blue and compared with conventional DCs. And you can certainly show that there was improved survival relative to the standard dendritic cell vaccination approach. And we can show in panel B here that if we eliminated CD4 T cells, that reversed the disease protection, indicating that that was the dominant cell type that the vaccine was activating and that had anti-tumor activity. Show high levels of IL-17 in the tumor microenvironment. We also showed with this approach that we can induce high levels of CD4 T cells that migrated into the tumor microenvironment, but not CD8 T cells. And I should note that in this model, like in humans, MHC class 2 was elevated in or on the tumor cells in the tumor microenvironment. So we worked with our manufacturing group here at Mayo Clinic and developed a GMP strategy that mimics what we had seen with the animal models and what Dr. Cannon from the University of Arkansas had seen in his ex vivo models, where we isolated CD14 positive monocytes and PBMCs of patients with ovarian cancer, treated them with this cocktail of cytokines and inhibitors as shown here, adding on the folate receptor peptides and confirming that we can get a good stable product that we can take into phase 1 clinical trials. And we established a phase 1 clinical trial that was based on activating the immune system through a series of priming vaccinations given every 3 weeks in patients that had no evidence of disease after conventional treatments, and then every 3 months giving booster shots in these individuals for up to 2 years, looking at whether or not this is safe, targeting the folate receptor alpha, and whether it's immunogenic, and then looking at secondary outcomes such as survival, other adverse events, and a number of correlative goals that we wanted to look at in these patient populations. So to put it in a nutshell, the vaccine was found to be safe. We have 19 patients in general with no significant adverse events, mostly adverse events that were associated with other vaccines such as fatigue and injection site reactions. But notably, we could induce in nearly all of the patients high levels of IL-17 T cells, which is shown right here. In addition, we also induced Th1 T cells. So we have this polyfunctional immune response that's being generated as a result of vaccination with this particular platform. And we also induced antibody responses to the folate receptor alpha. And importantly, we based on, even though it's a small population, we showed that relapse-free survival appeared to be improved in these individuals. So normally at 24 months following the completion of chemotherapy, you would have about 15 to 18% of patients surviving with progression-free survival at that time. So we observed about 40% relapse-free survival, and in fact, we're out at about 8 years in these patients, and none of the patients that initially did not recur in this clinical trial have not recurred as of yet, whereas all of the patients that did recur have unfortunately died. And one of the important things that we saw is that higher levels of immune responses were associated with whether or not the patients had recurrence. And we also found, in addition to the T cell responses, that antibody responses were also correlated with survival in patients as well following immunization, and that the antibodies that were generated and circulating through the blood had cytotoxic activity when in ex vivo cultures of NK cells and target cells looking at cytotoxicity. So in summary, the patients seem to be safely immunized against the folate receptor alpha, high levels of Th17 T cells that were circulating in the bloodstream, and also appeared, at least in a subset of patients, to have improved progression-free survival. So we just recently opened up a phase 2 clinical trial here at Mayo and Jacksonville. Actually, it's going to be a 3-site clinical trial in which we're evaluating whether or not progression-free survival is indeed improved in patients at first diagnosis with ovarian cancer. In this particular case, I'm not going to go into all the details, but just point out a few highlights that there's 2 arms. So we have a placebo control arm and we have a vaccination arm. 2/3 of the patients will go on to the vaccination arm, and it will be the vaccination schedule that I previously showed you, where patients will be immunized with a series of priming immunizations and follow that up with boosters for a total of 2 years. The primary goal, of course, is to see whether or not indeed we can improve relapse-free survival, and we have a number of other correlative goals. So this clinical trial actually is funded by the National Cancer Institute, and just started within the last couple of months, and we have a number of patients that are on the docket to receive vaccination. We also had the opportunity to look at recurrent lesions from the phase 1 clinical trial, where we evaluated lesions in patients that had recurrence to determine if there was any evidence of changes in the tumor microenvironment. We didn't see any significant downregulation of the folate receptor alpha in general across the board in those patients that recurred, indicating that we weren't generating antigen loss variants. We didn't see any evidence, for the most part, of activation of CD8 T cells, and that aligns with our mouse models, which showed predominantly CD4 T cell activation. That reciprocal relationship between Tregs and Th17 was potentially observed here, where we showed that in recurrent lesions in those patients that recurred, there was much lower levels of regulatory T cells, indicating that despite the fact that these patients recurred, vaccine potentially had activity. And what was notable here is that all of the recurrent patients had PD-L1 expression in the tumor microenvironment. This indicated to us that perhaps these recurrent patients actually had a compensatory mechanism of immune suppression beyond regulatory T cells that was operational in the tumor microenvironment. So we then
2 minutes remaining, please.
Okay. Yep. Just about done. So we conducted. We started to become interested in combining this with immune checkpoint blockade, and of course in ovarian cancer there's been some significant failures of clinical trials with immune checkpoint blockade, and this is in part due to the fact that IL-10 leads to additional suppression in the tumor microenvironment. I can't go into all of the detail, obviously, here, but interestingly, what happens in patients in animal models with ovarian cancer is that treatment with anti-PD-1, anti-PD-L1 leads to upregulation of IL-10 in the tumor microenvironment, and this IL-10 actually suppresses T cell and dendritic cell activation in the tumor microenvironment. So we tested the combination of Th17 vaccine and anti-PD-1, and as you can see, it led to improved survival. Some of these animals even surviving out to about a year with a large restructuring of the tumor microenvironment and some very interesting findings there. The combination of anti-PD-1 plus vaccine led to a robust increase in granulocytes, eosinophils in the tumor microenvironment as well as dendritic cells. But what was important is that the combination led to a reversal in the compensatory IL-10 release in the tumor microenvironment. So we think that's why that the combination is working effectively in this particular case. And with funding from the NIH, we recently started a clinical trial, and we're in partnership with Merck as well, where we're investigating a combination of folate receptor alpha vaccine, dendritic cell vaccines, plus pembrolizumab in patients at recurrence with ovarian cancer to see if we can actively shrink the cancer. So we're looking at potential opportunities as I close it out here for what would be, you know, some future directions. We have data showing that multiple antigens are better than a single antigen, and that may be important for some of the patients, particularly if there's evidence of tolerance to, for example, the folate receptor alpha, which we observed in patients. So in this particular right-hand graph here, we showed that higher levels of folate receptor alpha are associated with reduced Th17 T cell responses to vaccination. So there's some level of tolerance. So there's a lot of interest in coming up with a multi-antigen cocktail. So we're trying to figure out how to do this. And one of the ways that we have been investigating future approaches is to develop neoantigen-based vaccines that we can integrate with this. And so obviously I'm not going to go into all of this, but we've developed algorithms to detect neoantigen vaccines in patients. And this is just an example of one patient where we immunized with vaccine and saw sharp reductions in tumor generation of immune responses to multiple antigens. And in many cases, these tumors shrink up completely and are completely dead, look like scar tissue with heavy duty infiltration of T cells and do not grow back. So this represents an opportunity for us to, interrogate the genome of ovarian cancer patients in their tumor microenvironment and identify a multi-antigen strategy. So in conclusion, vaccination with degenerate HLA class 2 epitopes results in 100% immunization rates in patients. We can develop customized dendritic cell manufacturing and reprogram dendritic cells to lead to optimal levels of specific subsets of T cells that are effective in the tumor microenvironment. We still don't know exactly what all of the mechanisms are with respect to the efficacy of Th17 T cells, but there's strong evidence that it'll protect from disease relapse, and in combination with immune checkpoint blockade, foster better outcomes in patients. So we'll be looking at mechanistic studies to identify those patients that don't respond and how to improve that, but also multi-antigen strategies that we can take into the future. And so with that said, I appreciate your attention and happy to take any questions.
Thank you. We have time again for just one short question and a short answer. There's a gentleman in the back.
I don't think I'm hearing.
They're waiting to get a microphone to him.
Oh, okay.
Just say the question and I'll repeat it to him with the microphone here.
Hello, sir. I wanted to ask about a question that kind of follows from Dr. Flatt's presentation earlier. in his presentation, he said that sometimes when we treat the cancer, it results into lesion formation in some other area in the patient. And as we know that the cancer has pretty much all the same antigens as the rest of our body. How do we ensure that the same does not happen, the same reaction does not happen after vaccination?
So I missed part of that, but you said that the last presentation results in what?
What I wanted to say was that after treatment of a cancer in a patient, that after the treatment, the patient may develop skin lesions like dermatitis or psoriasis. So after vaccination, how do we ensure that the same reaction does not take place?
Well, so that may be, limited to antigens that are present in melanocytes or other skin cells, leading to some on-target but adverse events that are in other tissues, and we've been closely monitoring that. So with the folate receptor alpha, for example, as I had previously mentioned, there is expression in the apical surface of the proximal tubule of the kidney. There's also expression of the apical surface of the epithelial cells of the choroid plexus. We've monitored that quite carefully. The immune responses don't seem to interfere with those particular cells. For reasons that aren't clear, but there's no intersection. Perhaps they're in a privileged environment so that there's no immune responses. We haven't seen any type of adverse effects, and we've been following the patients probably now for about I guess about 8 years, as I had previously mentioned, and there's many cures in these particular patients, and they don't have any consequences as a result of being vaccinated against these self-antigens. So it would just all depend on what antigens that you're targeting and where the tumor is with respect to adverse events.
Thank you, sir.
Thank you very much. We have to draw this to a close because of some time constraints afterwards. Thanks for a fascinating presentation for both of our keynote speakers this afternoon. Let's give them a round of applause.
Thank you.
I would now request Dr. Prakash, Dr. Tanveer, and Dr. Navkiran to please felicitate our session chairs. Okay, there's a small announcement. So bus will be available from block I2. So it would be available at the I2 entrance, and it would be leaving in next 15 minutes from now. It would take you to the golf course, which is the venue for the gala dinner. Thank you for joining us today. See you tomorrow. Thank you.
Yeah, so finally, one last word for the day. So this was a fantastic day, and I think we concluded the whole session with a very nice bi-directional interaction. So I hereby close the first day of the conference. So look forward to see you all tomorrow morning.